What's up, everyone? About to start up on YouTube. Just so you know, we're live on YouTube right now, and everyone's here getting ready. About to start up on YouTube. Just so you know, we're live on YouTube right now, and everyone's here getting ready. About to start up on YouTube. Just so you know, we're live on YouTube right now, and everyone's here getting ready. About to start up on YouTube. Just so you know, we're live on YouTube right now, and everyone's here getting ready. About to start up on YouTube. Just so you know, we're live on YouTube right now, and everyone's here getting ready. About to start up on YouTube. Just so you know, we're live on YouTube right now, and everyone's someone got an echo in there, so I'm just trying to get it out of the audio.
Okay, look at that. We got the whole gang. And it is 12 p.m. So, okay, look at that. We got the whole myself gang for just a moment because I've had some weird Zoom stuff. It is 12 p.m. Okay. So, and we have Bob with us. Okay, look at that. We got the whole myself gang for just a moment. Because I've had some. Can you hear me okay? I haven't done the intro yet, but
you are super crystal clear.
Okay.
Vision and audio.
At some point, I got to iron this shirt. My Zoom shirt. I haven't done the intro yet. My official Zoom shirt.
I deliberately let mine a little bit crease so I didn't upstage you.
Okay. There you go. There you go. Yeah, I do this shirt all week for meetings, and then I just kind of toss it to the side. You know, after I'm done with each meeting, I just toss it to the side. Okay, there you go.
I see. It's just
I mostly clean the house. I actually, yeah. Well, I have a 12-year-old, right? So
yeah,
it just
I
piles. It piles up.
I see. It's just
okay. Well, let me mute you out. Let me see if Jeremy's here. Well, I have a 12-year-old, right? Yeah. So it just piles. It piles up.
It's just
we're running. Hey, Jeremy. Let me mute you out. Let me see if Jeremy's here. Yeah. How's our stream going, sir? Hey, Jeremy. Let me mute you out. Let me see if Jeremy's here. Yeah. Well, you should. Well, why don't I? Do you want me to just get started and you can get it going when you on the fly, or? Well, you should. Well, why don't I? Do you want me to just get started and you can get it going when you? Okay. On the fly, well, yeah. Let me do that. Let me just get things started. I think Jeremy's. Well, you should. Well, Jeremy will get on when he is able to get on. But in the meantime, I'll get the archival version going. Well,
Sorry, we're having some technical difficulties. I'm waiting for him to let me back in the meeting now. He's probably doing the intro right now. This is so stupid, dude. Oh my God.
Recording in progress.
So really, fire away with your questions. My answers will be focused on what I know. I will bat away questions that I have no expertise in, if that's okay with people. But I'll take a stab at some more general questions. So without further ado, I've got a lot of materials ready to pull up should questions necessitate some corroboration. But with that said, fire away.
Awesome. Again, we're doing things a little bit different. So Bob, I have you spotlighted. Let me take the spotlight. I'm going to remove the spotlight there for the time being. And I think I removed mine as well. So yeah, again, we're going right into Q&A, which is throwing me for a loop here. Option Y on Mac or Alt Y on Windows. And I will start, let me start with the first one. Doug Lindstrom is having audio problems. He was wondering if you could comment on the trails left by EVOs on photographic paper and if the Instamatic photo packages would work for that application.
Okay, so you're gonna put me full screen? I don't know. Actually, I discussed a bit about this last night, and I have purchased a Instagraphic camera for this purpose, and I did a sort of discussion about it. We are going to actually use those films in a number of experiments, so I may be able to give you an answer before the end of the year as to whether they panned out. But certainly, if you're aware, Kodak found out that there was some nuclear testing going on because their films way back in the day were showing these spots all over them, and people were buying their films and only to find that they'd already been exposed. And so Kodak was actually let in on the fact that there was nuclear testing going on before the general public was, so that they knew when and where, if the wind was blowing in their direction, they could avoid doing a manufacturing run for a period of time until the ambient radiation was below a level where their product would be useless. And so there was a guy, I can't remember his name, but if you go to the MFMP YouTube channel, you can see a video I did on this, where a guy took some instant film and he found that he actually had an X-ray source, and it was something for making X-rays, and he actually took films and found that the Instamatic film was susceptible to X-rays after it gone through the camera for a period of time, like 20 seconds. So then you actually expose the film with a no actual light going into the Instamatic camera, and then you could then take that film and expose it to the source. However, that's not really very useful for the work that we're looking for. We're looking for accumulation of things over a period of time, rather than trying to find the right 20 seconds of your experiment to expose a film to. So I actually am proposing that we take the film. So I have these mini Instax here. This is a wide angle one, and this was just one for testing when we're doing testing. So actually they come in packs of 10, and the idea is that you would expose, because we're looking for things that would ordinarily go through the shielding that would shield normal material. And in fact, on the outside of Instax cameras, it comes in a foil packaging, and on the box it says avoid being exposed to X-rays. So they are aware that X-rays will cause some damage to the film. But we're not just talking about X-rays, we're talking about charge clusters, and charge clusters can be in the neutral way. They can pass through a range of materials until they get excited to such a point that they dishevel, and then they throw out their electrons and the ions that they're carrying. And this has been studied by the group at Dubna since 2009, and earlier from the group in Moscow Nuclear Physics Institute, Bogdanovich. And they have found that, and other Russian authors principally, but they have found that it goes through a number of sheets of material. And this was also observed by Matsumoto. So I don't know if you're aware, but since we last spoke, we have produced a facsimile of the Matsumoto steps to the discovery of electronuclear collapse. So you can go to remoteview.icu and download this full PDF. I think it's about 310 megabytes, 289 pages. It's a faithful one-to-one reproduction. But in this, I think you will find that a number of his experiments, he actually had an electrode, and below the fluid, he would have some metal, and then behind that, he would have a stack of actually real nuclear emulsions. But he found that it would go through a number of them, and then it would get to the point of being excited, and it would bounce around between two of the emulsions, and you would get tracks on both. Other authors have found that you get coincident tracks as it goes through a number of layers. For instance, I think it's Perovstikov was looking at harnessing these electron clusters by having the south pole of 0.4 Tesla magnets under a bowl of water in a sealed chamber and exposing it to the sun for 10 days. He thinks it's some sort of solar photon, but it is actually clusters coming from the cosmos. And they aggregate and they bind to the oxygen dissolved in the water. And then you can fire a small domestic sort of $5 milliwatt class laser at it. And this excites and decouples these clusters. And then he used standard 400 ASA film. And he would see the same kind of tracks that Bogdanovich and his team at the Moscow Physics Nuclear Institute and the Dubna Science City group has observed. So my view on these is you take off the foil wrapping, and then you take the stack of 10 and you sit it next to your reactor. And I would choose to have a strong neodymium magnet behind in some stacks with a south pole and some stacks with a north pole, because you get clusters of both. And also you could have no magnets. And then once it's exposed to a reactor for a long period of time, then you would then put it through the camera, but in this case you would blank off the lens and just pass them, run them through the camera and let them develop. So it's a non-known entity at this point. There's an opportunity for someone to be a first to demonstrate this, but then you have to have a reliable way of making exotic vacuum objects charge clusters, and that is a different subject. So I hope that answers your question.
Awesome. Well, thank you so much. I mean, that's, yeah. And again, his audio is down, so maybe he'll ping me again on that. And I had a couple others in chat also, but let me go to Aiden now.
Hey, Bob. First question's fairly innocuous. It was in one of your YouTube videos. You had a really useful website that showed nuclear physics, or you could go up and look at like element 115, 116 and get proton and neutron count on it.
Well, you can go to ptable.com, and that is an extremely useful site. And it shows many of the artificial nuclear tides that were synthesized, actually mostly at Dubna, the science city north of Moscow. And typically they take a very, very heavy element and they fire alpha particles at it until they make something super heavy. And so, yeah, so if you go to ptable.com, I'll do it right now. And maybe not on the screen you're seeing me on. I'm going to move you off so I can actually see. And if you're thinking of ptable.com, yeah, if you're thinking of element 115, is it what element you after?
Yeah, it was the mythical element 115, but they
so that is, funnily enough, Moscovium.
Right.
Because it was developed by this team at in Dubna. In fact, many of these elements above Hassium were developed there. In fact, I think 105 is called Dubnium from Dubna, Science City. So you know, the Russians are very, very good at this kind of thing. So
then the other question was the vacuum capacitor, or EVO enabled vacuum capacitor.
Yeah, so there's a group that came from a Russian person, and I've actually contacted them, and I actually have some of the ones that are listed in their patent over here on the shelf in this little package here, and they're made in the old Soviet Union. Maybe I'll get one out for you. But this is the one that they claim was the test sample for their awarded patent, or the patent that's pending. I don't know whether it's actually awarded, to be honest with you. Let me gnaw my way into this for a few seconds. But essentially, the idea is that you create the conditions for charge cluster formation, and you just add the energy. And when you've seen some of the videos that we've shared over the years with what they do, so this is a vacuum triad. This is I think it's a what is it? It's a V078. It's a 6A/B, or that's what it looks like in Russian. I don't know if you can see that, but this is the thing. But it has a thermionic emitter, I think, and it has what you would need for this kind of concept. And then what you would do is you would put like your counter electrode on the outside, and you're effectively, it doesn't ever get discharged. You're building up the charge in there, and then you would discharge through one of the leads. And that's essentially kind of what they're doing. They're looking at types of ceramics, and I suggested to them boron nitride because of the way that EVOs like to eat anything covalent, ionic. You need to have covalent materials to store them. But even those will fail at some point. So I don't know. They said that they were advancing their work last year, and that there would be opportunities to maybe interact with them after that. But no real advancement has been there. And one of my colleagues working on the Vega set of experiments, he contacted them again and got a bit of a deadpan response. So you know, they are building their technology based around exotic vacuum objects and the reality of them. And I wish them every success, because the potential for storage of electrons in an incredibly small volume is just breathtaking. the only question I have is how do they keep them stable such that they don't do random destructive events? So, you know, they might get away with it 1,000 hours and then they might not. So, you know,
a Hallback array around that.
Sorry?
I mean, a Hallback array. So you have, you know, magnetic confusion, magnetic confinement within.
Well, to do any type of confinement for EVOs, you have to keep them in a non-neutral state. And so you have to feed them electrons. So you need to have them so that they express a magnetic and electric, or they are able to be controlled by electric and magnetic fields. Shoulders used a penning trap, which is a combination of both. But to be able to trap them, you have to keep them fed with electrons. Alternatively, you can bind them to nuclei. So, but they live in according to Shoulders, they can live in metals indefinitely. And in our research, a researcher Lion was able to revitalize some that were apparently in his copper oxide of his Lion reactor 9 months later. And when I showed this to some Russians in Sochi in 2018, they said, "Oh, that's nothing. We've managed to get them to come back to life after 18 months." And all they did was they put it out into sunlight to re-excite them. And so there's a range of ways you can re-excite them. Obviously, you've got IR photons in sunlight. In the case of the Lion researcher, he heated it up to 800 degrees, which is by his thermocouple, which is actually 1040 degrees in reality. And that was for a period of time, and that was able to re-excite them. So he could see these tracks again on X-rays post that event. Now, other researchers have found, so for instance, Bogdanovich found that when he used plasma flow discharges and captured the things flying out, it's Leonid Uritskev, when he exploded titanium foil, and he produced ball lightning, and he produced strange radiation tracks, and he produced the magnetic monopoles that changed the fine magnetic moment of iron 57. He found that faded away after 2 days. Now the question is it still bound to the 57 nucleus, or is it in a state of not being able to express that change to the magnetic fine moment of the nucleus? Is it still there and it just needs to be re-excited? I don't know. But certainly when I was looking at ultrasonically produced ones in the work of Suhas Ralkar, his fuel was very active and then not very active in terms of strange radiation emissions over a period of a couple of months. But I imagine that if I take that fuel and treat it in one of the aforementioned ways, like exposure to sunlight, exposure to direct thermal photons, it might re-energize it. So yeah, so the short answer is you have to keep them alive to be able to control them. When I say alive, you don't want to make ghost particles out of them. If they're ghost particles, they'll go literally where they want, and then they might get excited somewhere else, and then you have a problem. Does that answer your question?
Yeah, I think you got it. Aiden muted himself out. So let me go to Robert next. Robert, sir.
Thanks, Tim. Hey, Bob, how you doing?
Hi, Robert. How you doing?
All right. I can't believe how much time had passed since you did your talk in January. You were talking about neutrons interact with other matter, which cause a lot of gravitation. And then shortly after, you would talk about Matsumoto.
No, not neutrons. Cold neutrinos. These are they're not relativistic nuclear-derived neutrinos. They are the same. Firstly, you've got a vast amount of material left over from the supposed Big Bang, but I don't believe that's necessary for this to occur. But anyway, there's a lot of this material out there at about 2 Kelvin. It's already in a coherent state, and it apparently is at a density where it's one coherent condensate across the entire universe. And this rains down on the Earth, and this might be the infinitesimal corpuscles that was referred to by Tesla that were not solar derived. And these things have more mass potentially than all of the luminous matter in the entire universe. and it fits to the pressure model of gravity. And so, and in fact, there was a 2010 article by the CERN theory group that suggested that these relic neutrinos could, their properties and how they interact with matter could account for all of the observables of what we know as gravity. Now, you can technologically produce these according to the author that I've worked with, and I translated his book, Alexander Parkhomov. He had started to research this following doing the equivalent of Hal Puthoff in the Psychic Spy program. The skills that he learned in that, he then took forward into observing this type of radiation. He worked on atmospheric research, and he was a nuclear scientist doing radiation monitoring as well. And he was able to lens some type of matter, which at the time he called N radiation, onto beta isotopes. And he chose particularly strontium-90, yttrium-90, and also cobalt-60. Cobalt-60 because it has a much shorter half-life than even tritium, but also it's a solid target. So the density of atoms that you are interacting with is automatically much, much higher than those people that are using tritium as a neutrino, cosmic neutrino target. And so, yeah, so basically the neutrinos can be technologically generated, it would appear, by any matter, any dense matter or dense plasma that's over 1,000 degrees centigrade. And the higher you go, so for instance, I discussed in early 2020 with him about the possibility of using tungsten to generate these in the form of tungsten filament, partly because Langmuir had observed gas production in the 1910s, and that was probably related to this. But a 100-watt filament light bulb will be around about 2,600 degrees centigrade at full brightness. And so that is well above the threshold of 1,000 degrees centigrade. And at that point, you get something like, I think it's around about 50% of the dense matter producing the relic neutrino equivalent cold neutrinos. Now, these things are actually produced by the sun, but their velocity isn't high enough to escape the gravitational wave, the push down on the sun itself. So they just stay on the sun, according to Parkhomov, and participate in the nuclear reactions that go on there. So we get almost negligible flux from the sun. It comes from the cosmos. So you can use the cosmos ones, but then if you're technologically producing them, you're going to get a lot more. And so he's run some experiments last year using tungsten filament. In fact, he used halogen light bulbs, and then he had it in literally a halogen light bulb. And he had this in a mass flow calorimeter, which is just flowing water through he just silicon sealed the electrical parts of the halogen light bulb and then immersed the whole bulb in water. And then separately from that, he had a range of materials. And I realized that fluorine, because of its nuclear magnetic moment, and also because it's a single isotope, is a perfect fuel for charge clusters. And we would potentially demonstrated that by using PTFE with HHO, a Marsal gas variety, in Japan in 2019. But he actually used lithium fluoride, and that's a twofer. And he had that in a chamber next to the halogen light, and got a significant, it would appear, thermal gain over a control substance, and accounting for the weight, sort of calorific properties of the materials and their variance. So lithium fluoride seems to be a fantastic target.
So when you say cold neutrinos, are you comparing the temperature to, say, a plasma or the sun?
So no, when you think about cold neutrinos, you can imagine a gamma ray and what a gamma ray can do, and you can imagine a thermal photon. They're both photons, but their properties are extremely different because of the energies and velocities. Okay, so the fact that the de Broglie wavelength of a cold neutrino is in microns to millimeters. So if you've got them in a cluster and they're sitting there with unstable isotopes that really don't want to be, so basically the fact that a material is unstable, it says its ontological will is to become stable, right? And the idea is that there's some random process and no one knows what it is, and that causes a thing to decay. Well, that random process, in my view, is the statistical flux in any given location of relic neutrinos on the radioactive matter. Now, you can increase that by putting a magnet. You can put your nuclear radioactive material through in between a magnet, okay, two magnets. And there's even patents for this, for increasing the rate of nuclear decay. And in my view, that's because it's pushing an increased flux of these relic neutrinos through the nuclear material. Now, if you can then synthesize relic neutrinos, and what happens in this dense matter over 1,000 degrees, you get enough energy, it's 0.5 of an EV of electrons or other atoms colliding, that it synthesizes a relic equivalent of a relic neutrino, but a cold neutrino and anti-neutrino pair. And that's his understanding. And we have a calculator based on that, and it's rudely good at predicting outcomes in the field in terms of what has been historically observed and what you might predict would occur if you put several things together in a future experiment. So it helped me to understand that if you use lithium and fluorine, then that would give you a good outcome, and that's what he got a best outcome with. You know what I mean?
Okay.
It's like,
Thanks for correcting me. Thank you.
that's okay.
I thought it was interesting. You went directly to an application of lightning. I have a note. This is what Matsumoto said is what all lightning is. Can you elaborate on that?
Okay, so in the case, if we step to what Shoulders did a lot of studies on lightning, and he said that the leader, the feeler at the head of a lightning bolt is actually a ball lightning, and this is an exotic vacuum object. And I would be fairly confident in saying that Matsumoto would agree with that. We actually have his email of a few days ago, and we're starting.
You talk about step leader?
So basically, it's like it's the tracer that traces out the ionized channel
Before the light from the lightning.
So
occurs,
and if
when
you actually
see.
watch it slow down lightning, you get a ball that comes down, and then it gets, in my view, it does exactly what we're seeing in the Vega Valley. It gets overexcited, it consumes too much matter, and in this case it's probably nitrogen, because it's 78% of the air, nitrogen 14. And it comes down, it's consuming that matter and oxygen, 20-something% of the air. And it's building more and more coherent matter. And as it comes down, it then splits. And then you get another feeler going out. And then it splits. So you get forking and forking and forking of the feelers. But then the first that hits the higher potential, let's put it like that, depending on whether it's cloud to cloud, cloud to ground, or ground to cloud, will then provide the discharge channel. And then through that discharge channel, you'll have multiple pulses going through.
Because I understand through Feynman's lectures of physics, the step leader goes from ground up, and then the lightning comes from the clouds down, following.
Well, it's interesting because now there are some extremely good. I think the high speed guys did some took some material off the 3-tower boat thing in Singapore, and you can see where it comes down. I've actually had the pleasure of standing up there, but I never got to stay in the hotel. But also in the
may interject.
I know exactly where it is, and so the lightning comes down, and the feeler comes down, the ball lightning comes down as I described, and then spreads out into multiple channels. It hits the ground, or the other way around, or between the clouds, depending on the potential differential, and then you then have something going back up. Now, yes, that could be the exotic vacuum object. Coulombically exploding, and what you're seeing is it riding up the channel
before the lightning.
So because we've actually produced these Coulombic explosions from EVOs in the Vega experiments, so you can see them very clearly. And in the presentation I gave last night, you can actually see what's going on in terms of the structures that form the core of ball lightning, and you can actually see the breakup products and stuff. So.
Yeah.
One more question.
Actually, Robert, if it's okay, let me go to Harold next, and we'll come
I can
back.
come back later.
Yeah, we'll just loop around here. Loop around here. I just want to make sure everybody gets equal time. Let me go to Harold next. Harold.
Oh, thank you.
Hi, Harold.
Hi, Mr. Greenyer. Obviously, I mean, after watching your presentation, you obviously offer a banquet of food for thoughts. So that makes me wonder, what drives your research, what is your research methodology and what purpose drive it to do what you're doing? Because you have a lot of interesting things. Now, the second part of my question is related to more specific is, can you address on the application of element 115 in propulsion, like it has been discussed about Bob Lazard and others? Can you elaborate on that second part?
Okay, so on the first part, why am I interested in this? Frankly, and it might sound a little bit weird, before I was, I think, 7 or 8 or whatever, certainly before I was 10, I had a series of dreams, and I was told I'm going to have something very difficult to do. I have no choice. It's going to be a burden, and it's going to be in my 40s. And so I've always known that I would have to do this job. It's something that I couldn't take a profit from. I couldn't become fantastically wealthy from, but it would be my 40s, and I'm going to be 50 on September the 23rd. So if anyone wants to send me a birthday card, that'd be nice. Yeah, so I actually started the project, and it really hit the ground almost on my 40th birthday, which was surreal. And I really didn't know what I was talking about in any degree for the first 6 years. And it's kind of like an iterative process. What makes me tick? Well, I had one child and I desperately wanted more children. But in 2006, I'd gone to the Peak Oil Conference in County Cork, self-funded. And I walked away from there and said, there's literally no hope for planet Earth. I mean, one of the speakers formerly worked at CERN, and he says, you know, to get enough fissile material, fusion material to run a 1 megawatt reactor for 1 year, we'd need to process 3 times the volume of the Zambezi, which is the 3rd largest river in the world, to just produce that amount of material to run 1 reactor. Of course, there's different methods that have been developed since that. But I walked away from there, and he touted the phrase where at CERN or other areas, they were saying that the Russians gave the tokamak to the West to waste all their research dollars. And I'm probably pretty convinced that that's the case now. So yeah, I came away thinking, because it was a peak oil conference, like the oil's going to run out, nuclear fusion's never going to come. I had witnessed the 1989 episode with Martin Fleischmann and Stanley Pons, and so I had in the back of my head, you know, if I get an opportunity to make a difference with my skill set, then I would. And I realized I'd have to walk away from everything I'd done. And honestly, I can say it's the best decision of my life, other than personal decisions, family-wise. And I couldn't imagine meeting more interesting people. The science is incredibly engaging, and you're meeting, I mean, the opportunity to meet the top scientists in Japan, in the US, in basically every country on Earth. It's been a real pleasure and an honor to do this thing that I had to do. And I think we're nearly at the end of it in terms of establishing it as a real thing. And so I just can only say that thank you to people like John Hutchison, to Ken Shoulders, to Takaaki Matsumoto, and to the characters like those who went out on a limb when there was no one else to reference. In fact, the first papers I received from Takaaki Matsumoto were from a guy in Denmark, and he was noting on those papers. He was a collector of papers in the cold fusion field, and he was noting on the fact that Takaaki Matsumoto, and you'll see it in his book, he was only referencing himself for the first 4 or 5 years. And that's because no one else was doing the work. Everyone else was trying to make neutrons and gamma rays and helium, but they weren't looking at what was happening in their reactors physically. Mm-hmm. And he was a person whose entire education was to look at nuclear emulsions. And so he did what he knew how to do, which is look at a nuclear emulsion. He goes, well, that's not an X-ray. That's not a triple track. That's what's going on there. This is crazy. This went all through all this apparatus and it's left this weird blob. What is it? And he started publishing these things, and he was able to publish them in the American Nuclear Society's journal until 1994, when he mentioned ball lightning. And then they stopped. They changed the rules. So he couldn't publish. Boom, not allowed to talk about that. Unfortunately. Okay, so about element 115, the Muscovium as synthesized in Dubna, I believe, probably, most likely, by some of the people, in fact, one of them probably Shishkin, that I'm translating his work right now. That would almost certainly be unstable. I think it is very unstable. Now, there is a question where if you add a certain number of neutrons, you might get to a point of stability. So is element 115 a mythical thing? Is it a combination of elements? Is it that you take Muscovium and you load it to death with exotic vacuum objects and that becomes stable, i.e. the Muscovium is able to stabilize exotic vacuum objects? I don't know, but I'm pretty certain that all exotic technologies, all exotic energy technologies will be using exotic vacuum objects, charge clusters, itonic clusters, ball lightning type coherent matter. So maybe it's a combination of the two. Because the descriptions, for instance, of Boyd Bushman of these material that's recovered from spacecraft, where they're able to run, a whole lab by connecting it through the equipment to ground, does talk of something that is storing either a fantastic amount of charge or it's able to cohere energy from the vacuum. When I say that, I mean cold neutrinos or relic neutrinos and convert them into electrons or whatever. So I don't know. That's all I can say on that, really. I mean, I deal mostly with what I can physically see and repeatedly produce. That has a long tradition of observation by third parties who I respect. I don't know Bob Lazar. He has this experience that he lived through, and I'm sure what I found in this journey is that there's always an element of truth, and I've thrown the word element in there and it's not meant to be a pun, but there's always an element of truth in statements. But if he's working for a covert operation, I can pretty much tell you for certain that what he was told was not necessarily what it was.
Oh, thank you. But in your conclusion, will it produce a propulsion force? Will it be useful for propulsion, even if you add the exotic vacuum object to make it stable? Is there a possibility, let's say, a way in which you can make element 115 to produce a unidirectional propulsion force? Because that is...
if that was his claim, then that was his claim. But I think it probably was an energy source for the equipment that otherwise produced the vectors.
That looks like, I would agree with that. There seems to be more energy, because he claimed, okay, it may be producing energy. He didn't say that is producing a propulsion force. I mean, he kind of vaguely speculate on that. And that is the question. Is the element 115 the element that would produce the force that generate the propulsion? And that's a part, but I would agree with you on that part, that it may be like a battery, a supply of energy, if it can get energy from the vacuum, something like that. But there is still a mystical open question. Hey, thank you. Keep up the good work. You're doing great.
It's a pleasure, Harold.
Harold, thank you as well. Let me go to chat real quick. Kate had a question. Longtime lurker Kate, who has been at these conferences for months and months. She asked, what would Bob need in order to build an actual SEV utilizing the potential of EVOs?
Well, firstly, a willing team. And when I say a willing team, I don't mean people that just want to get paid. My father always said a volunteer is worth 10 forced men. You need to have a team that have the aptitude. And so it comes down to people, and people that are on the same page. I do know someone that actually spent 7 months going through my previous videos to learn my journey, the errors that I made, and so on. And now I can have a sensible conversation with them without having to repeat myself over and over and over. So I wouldn't wish what I've had to go through on anyone, but I can say that I can help people get more immediately to the answers rather than making all the mistakes I've made. So what would I need? Firstly, a tolerant environment. So for instance, we are trying to get some tritium to demonstrate the tritium remediation for fixing the 1.3 million tons of Fukushima tritium-laced wastewater. And I identified a process where we can take HHO generated from, and it would be TTO in part, from a generator, ideally with some sound involved. So it's similar to a Marsa gas if it's not a Marsa gas. And then expose that to calcium carbonate in a way that the carbon dioxide is driven off and you get calcium oxide. This is already known to work in Lena, but from the 1820s, this is actually exactly limelight. And there's a phase transition around about 2100 degrees C. This allows for you to get a lot of relic neutrino equivalents being synthesized and the remediation of the tritium. And also, because calcium is mostly calcium-40 and it can go all the way up to 48, it can be a huge neutron acceptor. And so this has a lot of grounding, and they didn't buy it. And so we then went to, we found a solution. They said that we want some more qualitative and quantitative data. And we said, well, we can pay to come and test at your facility in Fukushima. We will pay your scientists to use their equipment or not to analyze what we're doing. They're not interested. So we had to find another way. So we found a device, it's about 20,000 euros, and it's actually used for testing radioactive elements in, say, water, right? And it actually comes with 10 mil tritiated water as a calibration source. So the proposal that we're making is to use a calibration source, multiples of it, process the calibration source, have another bit of calibration source, and see the difference in radioactive output using the device that is used for testing radioactive material. So it's an absolute slam dunk. And you know what? We can't get any university anywhere, any company that has one of these devices or anything, because you know what? You have to have a radiological license to receive radioactive material in order to do the test. And there's a nuclear authority in the UK, and they want to help advance new technologies in nuclear research. We wrote to them, and their response was, this is too advanced for us. So it might not be that there's a conspiracy by most people to prevent this from happening. It might just be that the rules are in place such that everyone that could enable it to happen automatically prevents it from happening. It's not that they are talking to someone. The rules are already set in place globally. So you can't find out that, for instance, atomic hydrogen can do all this magical stuff. Okay, so the most important thing is the right kind of labor. The second, and willingness and actual determination to find out the answers. The second thing is a location that is capable of doing the kind of research we would need to do. And if you look at what happened to TL Carr, as soon as he started claiming that he was getting things flying around, it was shut down. You know, so you've got a real problem with these things. So you need to have a friendly, the right people, the right legislative environment, and the right location. So the only other way you can do it is to do it completely in secret. And that's not me. So that's not going to happen. It's going to be completely out in the open all of the time, whether you like it or not. That way you can't undo, you can't put the toothpaste back in the tube. It all becomes public knowledge, right? So those would be my prerequisites. It's not that necessarily you need a lot of money. Actually, you don't necessarily need a lot of money. You need the right amount of money. If you give people too much money, they stop working. If you don't give them enough, they can't work. So you need the right amount of money to match the team in the right environment with you know, it really is a tough cookie to crack. But you know, if there's something we can find a solution to, let's do it. Let's do it as a group.
Awesome.
I agree.
Oh, sorry. I think that might have been Kate right there. Sorry. Okay. You know what?
I have a question.
Well, actually, Lulu, if it's okay, I'm trying to do these in order. Let me go to It Is Possible next.
Okay, sorry for no cam. I do have a question for you, Bob. So glad to see you here again today. Your last presentation was such a mind blower that at the end of it, I was laughing because the audience was silent. It was just such a plethora of information. But today I want to ask you an interesting question that maybe you haven't thought much about, and that is antimatter. in relation to this system. Let's take a look at, the Schwinger limit is a quite fascinating phenomena. And when we talk about electron neutrinos and electron clusters, these things have so much momentum and they have so much energy concentration, it might be very possible for them to surpass the Schwinger limit, which I believe is perhaps part of the explanation for why you're getting transmutation of elements. But I wanted to ask you about antimatter and its production. Have you looked for it? Have you tested for it? And have you done anything regarding, say, positrons being produced or anything on those lines?
So if you actually look at what the theory is for Takaaki Matsumoto, what he says is you get an electron cluster around your nuclear matter. Now, for every atom, regardless of what atom it is, you have at least one electron for every proton. The neutrons are neutrons, right? So if we start with protium, which is one proton and an electron, you've got a proton and an electron, okay? If you've got deuterium, you've got a proton, a neutron, and an electron. So for every positive charge, you've got a negative charge, okay? Now, what he's saying is if you force an electron bunch, a lot of electrons, into a electron cluster, you get coherence, and that is enabled by two electrons becoming Cooper pairs, which then become a boson and can form a Bose condensate. And this gets to the point where it gets so much intense field in the coherent electron cluster that it polarizes the protons. And that causes the emission of a neutrino, not an antineutrino, and a positron, the antimatter of an electron. And the antimatter of the electron, the positron, and the electron that was already there become bound to the neutrino that's emitted, and you get what's called an iton. And that is a new type of particle, which is a positron, an electron, and an iton in a stable cluster. And that forms a coherent matter, and it tends to arrange itself in a web-like mesh. And then what you have is just neutrons. You literally just have neutrons. So what do you have? You have a neutron cluster in the core, and you have a positron and an electron that cancel out each other's charge without canceling out each other, and you have a fully neutral particle with however much matter is in there. And that is the itonic cluster. And if you drive this harder and harder, it gets to the point where you have self-compression and matter collapse. And that is the electronuclear collapse process. And from that, you get effectively prima materia, and atoms get reborn through what he says is probably a wormhole about 10 to the minus 33. And it comes out and gets born into new matter. So, yes, I've considered antimatter. The most useful antimatter that I've considered is the positron. And when you think about it, a positron and an electron are both folded and toroidally, probably zeta Bewegung orbiting structures that are closed loops of light. And we know this because if you get a positron and an electron in, and you collide them into each other, you get two photons coming out 180 degrees from each other at 511 keV, and that is the mass of the electron. So you get a photon with the energy of the mass of the electron, okay? Two of them, from the annihilation of one's matter and antimatter.
Like,
sorry?
So that photon is effectively the electron neutrino? Is that what you're...
What I'm saying is when you get a positron and electron and they annihilate each other, you get two photons flying out 180 degrees from each other, because if you could imagine them as two tori, however they come together, when they get together, they unravel each other. One is the Gozer and the other one is whatever it is from Ghostbusters. And you get the two beams coming out. They're not crossed, they're now coming out.
Yes.
Yes.
Like, the only effect would be from a canceling field like that is you get a space-time compression locally at the event, at the event of where these two opposite charged particles came back into recombination. I hate to use the word annihilation because I think it's a misnomer, but I really like the word recombination because it's like they never really technically go away. They're there.
The energy is converted into vibration of whatever the ether is.
Man, that was a way better answer than I could have ever asked for. That was amazing, Bob. Thank you so much. Friggin' fantastic, and I'm so glad to see you here again, man. Plenty more questions to go, so I'll step off. Thank you very much. I'm
Awesome.
watching your many times over. in the replay.
And Jeremiah, thank you, sir. Thank you. So let me go without any further ado here. I'm going to go to Michael Boyd, who has been patiently waiting. I'm trying to get through these as fast as I can.
Can you hear me okay, Bob?
I can, yes. Pleasure to speak with you.
Good. I appreciate it. I have 3, possibly 4 questions. My first is regarding relic neutrinos. Would a black hole's jet be a source of relic neutrinos?
Probably, because, well, firstly, I kind of disagree with the existence of a black hole. I kind of think it is just a large EVO. And what EVOs kick out is, if they're at the level of what would be considered a black hole, is this protomatter through this filament. And the filament is at this 10 to the minus 33 scale, according to Matsumoto. I think he does this electronuclear collapse diagram. Let me grab it. It's on it's early in the book, and like I say, you can download this and review it at your pleasure. It's show you here. Give me a second. And so basically, he has what looks like an accretion disk going into a point here, and then you get an ejection. And then on the outside, you get hydrogen, carbon, oxygen, and on the inside, you get from the spout, which would be your white hole, you get your generation of iron and titanium and things like that, heavier elements.
So it's basically proton flux.
No, it's more subatomic, subnuclear. Yeah, it's gluons, quarks. It's actually just raw energy, and then it just. The vibrations, like if you smash a wall that has several resonances, or anything that has several resonances going on. I kind of described this at a conference meeting, I think in 2015, 2016 in Italy. And it's like, you have Jesus, you have Muhammad, and you have Buddha, right? And they are the first things to crystallize out of this raw energy matter, right? And they're very charismatic, and they provide a template like a crystal does in your salt crystal experiments when you were 5 years old. And so the energy then starts crystallizing on these different things. And some are more likely to occur earlier, and some are, they're not very good leaders, and so they fall apart. So you can kind of think of it a bit like that. The matter, whatever settles down, whatever vibration gets to a stable state, that then provides a template for more energy that's coming out of this kind of protomatter, this prima materia.
Okay, my thank you for that answer. My other question is you were talking about lightning earlier, and I'm curious about 2 forms of positive lightning. One being the sprite, and the other being what's called an elf, the little circles that show up in the upper atmosphere of the Earth.
So do you mean things like these sprites?
A lightning sprite, like, is a positive.
Yeah,
form of positive
actually,
lightning.
I was very, very surprised because in Matsumoto's book, he talks about that.
Oh, cool.
Literally as one of the manifestations of this phenomena.
So
it's actually
the question was similar. Is that a source of a relic neutrino? Can we make them here? Is my point.
Yes, we can make relic neutrino equivalents called cold neutrinos, and we make them by getting solid matter or dense plasma above 1000 degrees centigrade, whereupon the particles of that matter, including electrons, protons, and neutrons, have a kinetic energy sufficient to synthesize electron, neutrino and antineutrino pairs of the cold neutrino type, where the wavelength, the de Broglie wavelength, is of the order of microns to millimeters, in which case they can interact with ordinary matter in such a statistical way that it's likely, or more likely, much more likely than relativistic neutrinos. Relativistic neutrinos, you need 9 light years of lead to get any sort of meaningful interaction, right? We're not going to have that in a lab anywewhere. That's a lot of lead. That's a lot of lead.
How much gold?
I would take that to the scrappy, and I'd be made for life.
Gold, I see. So the idea of cold, that kind of leads to my last question, which is, I'm like studying different unidentified aerial phenomena. You've probably heard about the like Tic Tac UFO that they saw in the Nimitz encounter back in 2004.
Okay, can I step on that one first before?
Well, I just it's a general question though. I'm just using that as an example because what we're looking at there is infrared imaging made with infrared sensors on the aircraft. And so basically my question is not what it is or if it's real, it's something we can observe. So in my review of all the different objects, I've come across a couple where, unlike the Tic Tac, which shows up warm on the IR compared to the background, the ambient background, I found several where it's actually cold. It shows up cold on the IR. And I'm curious if you have any ideas on why something would show up cold on the IR. And
well, I've already told you that the exotic vacuum object was able to be re-energized by putting it into a heater element from the researcher Lion. And what that is effectively doing is it's absorbing thermal photons. And so it could be re-energizing itself by extracting energy from the environment. And in fact, using this process, you can do what's called single bath thermal extraction at a distance. And so if you go and look at the Lockheed Martin patent that was awarded in 2013, they use coherent matter production. It's called coherent matter waves, something like that, by Lockheed Martin 2013. And they actually, without actually admitting it, they are absolutely categorically generating these things, initiating them from electrode points in the same manner as shoulders. So it's a shame. I can't recall whether they credit shoulders, but they should credit shoulders in that patent, and it's a bit off for them to have avoided that.
So it's called coherent matter waves?
It's called in fact, if you go to remoteview.icu, it's the absolute first article on my blog, because it's of that importance. And I just discussed it on there.
Remote View ICU.
Remoteview.icu, the letter ICU. It's like .com, but it's .icu. So if you go there, it's the very first article that I list. You get a link to the patent and related patents, and I've discussed other patents that led up to, I think, that learning by them. And they say that one of the uses of coherent matter is single bath thermal extraction, so where you can extract temperature at a distance. And I believe that this is the way that you can control weather. You create a cold area and a hot area by creating, when you create an electron, an exotic vacuum object, as the matter condenses, so you need to think of it like this. If you've got a plasma and it condenses to a gas, you have to release thermal energy. If you've got a gas and you have to put it to a liquid, you have to release thermal energy, IR photons. If you've got a liquid and you want to make it a solid, you've got to release IR photons. And in every stage, you're having to release thermal photons, right? If you did it the other way, you would have to capture them, right? So in the environment, it is completely replete with nascent charge clusters. We only get night lightning in part because there are charge clusters in the environment. So we know they exist, they're everywhere. Static electricity is what it's at, right? So they already exist in the environment. And what you can do is use interfering electromagnetic waves to both cause extra clustering, which will raise the thermal temperature of the environment, or to blow up the existing clusters, which will lower the local temperature. And if you have a high temperature over here above the Atlantic and a low temperature over here, you can produce a vortex, and that will create your weather system. So if you want to know where Hurricane Katrina came from, using the low frequency radar antennas, the Duga arrays, then there's your answer.
Very cool. Thank you so much for your answer. And I'll check out that webpage, and I like the very I enjoyed the last part, because if you look at the Tic Tac data, that's exactly what it looks like it's doing.
But the Tic Tac is the absolute perfect shape if you didn't want a sphere. In fact, what you have to do is you have to have structures of minimum curvature because you don't want to, you don't want to have any points at which you get a discharge. You need to have an even structure to have the clusters all over the surface to be able to control it in the right way.
So just as for
you have three options. You have a pill, which is the Tic Tac. You have the sphere, which is all the spheres, and you have a torus. Those are the three objects that you can make that have this curvature in a single surface.
Yeah, and there's a torus there's toruses showing up in Tic Tac too. So.
Well, maybe there is, I don't know, but that's what you would have to do if you use this technique.
Yes, that's very interesting, and I enjoy it. Your answers very much, and thank you for your time.
Awesome. Okay, well, Michael, thank you. Let me move along here to Charles. Charles, go for it, sir.
Hello. Video. Yep, big fan of yours and John Hutchison's. So I was kind of trying to categorize the different effects of the Hutchison or the EVOs, and I've kind of made a list here. So please tell me if there's any more, or if some of these maybe aren't accurate. So there's anti-gravity lift, there's disruption of material, there's transmutation, invisibility. There's fusion of dissimilar materials, there's time dilation, there's weather control and neutralizes radioactive material, distorts half-life of materials. There's even communication with spirits, and there was a view of an entity from a different dimension, and somehow uses 0-point energy. Was that correct?
Okay, do you want to just list one and I'll deal with that and we go on to the next one?
Okay, so starting from like anti-gravity lift, the Hutchison effect with like the cannonball lifting, you think EVOs are causing?
So essentially you get coherent matter. Coherent matter forms these north and south pseudo-magnetic monopole structures. They can skin surfaces. This is stated by Ken Shoulders in his interview, which I transcribed from 2010. And once they skin surfaces, if they are negating the action of the mode of whatever allows for gravity, then they will prevent the action of gravity on the thing that's contained within that skin. And so I believe that he used an iron cannonball. That's one of his most famous examples. And that's one of the heaviest thing that's been caught on camera. And that is the perfect object to skin because it's effectively the structure, shape of a ball lightning. And ball lightning, as I said in my previous talk, has been known to carry matter. And in that, for instance, there was a ball lightning that came into the view of someone and it disheveled, and out of it came a couple of gallons or so of water, which means the inside of the ball lightning is below 100 degrees centigrade, and it was negating the action of gravity on those couple of gallons, which weighs, let's say, 9 kilos or 8 kilos, depending on where your gallons come from. And then there was another example where sand came out of one. And if that's the case, the sand hadn't sintered. So we know it's below 360 degrees centigrade or something. And it's also a lot heavier than water. And so here we have two examples of historical accounts of ball lightning. And absolutely, 100% certainly, the ball lightning is coherent matter, and coherent matter is what's going on in the Hutchison effect. So there's no reason to not expect the Hutchison effect to allow for a negation of the action of gravity.
Okay, another one was invisibility of materials. Some metal samples would turn transparent.
Okay, yeah, so there's a couple of things about that. There's a classic triangular one, which has a curved section on top. That one, and because I did a huge amount of video editing, and always with the best video editing equipment that was ever available at any point since video editing became a thing that you could do, I know that there's some transcribing gone from the original footage through a number of steps. And what you've got in that particular video, and I've discussed this at length with John, is frame blending artifacts that lead it to look like it's transparent. I don't believe that it was ever transparent. There is then another one, I think it might be a molybdenum bar, which is in a later period, and it comes up and it curves and it moves around, and it's very clear that the central section of that has gone transparent. I believe that probably is a genuine transparency. Now, if you have coherent matter, then light will it will interact with it in a very, very different way. So whether it's wrapping around it like a black hole, or it's just passing through it and changing the translucency, either would do. I believe that though, if you have intense electron clusters within matter, the light can pass directly through the material. And so, it's kind of, it changes its refractive index and loses its opaqueness. Let's put it like that in the case of a metal. And so when you look at that particular video, how I'm seeing that is like, if you take, there's a guy called Thunderfoot, and he took potassium and calcium and mixed them into a liquid, and then he dropped them onto some water for this Coulombic explosion. Well, what is Coulombic explosion? Well, that's when you get a lot of charges going into the metal. What did he observe? It went from silvery to black to transparent, and just before it exploded, it was in the transparent state. And that is the point which is at, in my view, the highest coherence in the matter. So you physically see a metal becoming transparent in that Thunderfoot experiment. And I discussed this in my matter manipulations lecture that I gave in Copenhagen in 2017. You can go and look at that if you want on the MFMP's YouTube channel. So the transparency one, I believe, is a real thing, and I believe it's easily explainable by coherent matter.
Great, thank you. And for distortion of half-life, sometimes materials would seem to oxidize quicker. How would EVOs maybe cause that?
So if you can imagine an electron wants to grab an oxygen with a certain level of intensity, right? Now imagine you have an electron that has very many orders of magnitude more desire for oxygen. Because two reasons. One, oxygen likes to give up, have an interaction with other materials that want to have an interaction with it ordinarily. But secondarily, oxygen, as I've argued in my monopole clutch presentation to the Russian community in 2020, it is the most paramagnetic most paramagnetic molecule of all of the elements before you get up to some of the lanthanides. You're looking at things like chromium and stuff like that up at that end. And so it's unique in that nature. And I believe that that's why it's so important to life in general. It's so important to ball lightning. It's so important, you know, for instance, Sundaresan and Bockris in, I think, 1994, they did a replication of the George Ohsawa carbon arc experiments underwater. And they found that if they had no dissolved oxygen in the water, they were unable to synthesize iron. And they argued that it was the fusion of two carbons and two oxygens goes to iron 56 and 1,4 helium. But whatever, without the oxygen, you don't get that. And so I believe that the oxygen is absolutely critical because of its paramagnetic nature.
Great, thank you. And I think you mentioned a lot of this research not only require like one department in university, but would require multiple departments to study EVOs. And I agree. I'm a PhD in electrical engineering, and if you ever need help, I have access to a scanning electron microscope, for instance, and we can maybe do some for tests.
Well, that's absolutely fantastic, and we can never get enough time on a SEM. I've spent at least one day in each of the last 2 weeks on SEM, and I really seriously encourage you to look at what I've shared last night, for instance, because I believe we've categorically proven and can repeatably at will produce the magnetic core of ball lightning, and we can show the entire life cycle. And this is the same thing that did all the damage in the disruption in Hutchison samples. And tomorrow I will be giving a short presentation looking at some optical microscopy I took in Scotland in July last year with the collector that acquired the knife that fell into the aluminium. And you will see on the boundary layer the same structures that I shared from our Vega experiments in Holland. And you can also see that it's likely that the synthesized material is carbon, and that's the predominant output from these systems. And so that is on, and it's of the right amount of distance around the metal. And of course, you've got a paramagnetic element. The actual clusters will form on the aluminium because it's paramagnetic. Iron becomes magnetic when it's, sorry, steel becomes magnetic because enough of the atoms of iron collect clusters and then they find each other, and then you end up with areas becoming magnetic because it's not in the steel state. It changes like martensite or whatever. It changes its crystal structure to become magnetic, and so eventually the steel will be affected as well. So I'm going to be sharing that, and also going to be sharing some SEM of steel that where it has these golden ratio triangles, and that's the cone that goes into the pseudomagnetic monopole, and as it's capturing the material, and that's eaten out of the bit which split on iron. So iron magnetic materials behave much more differently to things like paramagnetic materials like aluminium, and for the same overall properties of the thing that's causing it. And so what you will find is transmutations occurring in this area where the material has disappeared. And so I'm going to be publishing that for the first time tomorrow. And so it's just, it never surprises me. Sorry, it always surprises me how much everything is logical and consistent between anything that you look at, if it's a genuine thing.
Great, thank you. Yep, review your video and try to reproduce some of your work at my lab. Thank you.
Okay,
awesome.
Fantastic.
And Charles, thank you as well. Let me jump right along to Gerald, sir. And Gerald, could I get you? Yeah, turn on your camera if possible.
Hello, everybody. Hey, Bob. It's finally nice.
Hi, Gerald.
It's WP Enlightened for Truth here.
Oh, wonderful! Finally, I get to see you.
Finally, it's been a while. Yeah, I don't have much of a question, unfortunately, because my main question was answered. All this group of amazing people
Ask
here,
another one.
They already asked it. You know, the only thing I have is have you seen David LaPointe's new primer videos? They actually... Okay,
I was going to do a separate video on this, and but since you asked the question, I'll do it now. As long as I get a recording to share this, and I'm happy to do that. Essentially, I don't understand how his patent was granted. Patent, depending which side of the pond you're on. Basically, it is an nth degree extension of the Boyd-Bushman directional magnetic beam pattern for Lockheed Martin. So that's my first thing. One could argue that the hole, i.e. where there isn't a magnet, which is the back end of the bowl, separates is from an nth degree variation of the Lockheed Martin Boyd-Bushman patent. However, in that pattern by Boyd-Bushman, he has the option to have an electromagnet there to pulse the magnetic flux. And this then causes a problem because you can have that off, and in which case you have exactly a Le Pont bowl, right? So that's not on the bowl. So I unfortunately, I don't think his patent, even though it's been awarded, is valid. And the reality is patent investigators rarely look at the historical patents. And by that, I mean a long way back, or even in this case, a short way back. And so it's kind of like, sometimes I believe that they're letting these things through. So someone spends their life investigating what they can do with it. And if it yields anything productive, the military will just come in and take it anyway in the US. You can forget actually, you know, so I think the most useful thing, I mean, we were told this when we set up the MFMP, so don't base anything important that you research in the US. Because if they just have these strategic laws with everyone that trades in dollars, and basically they can shut you down. So we had to be an international organization, and for most of the key discoveries to effectively be developed outside of the US. It's a really sad situation. And the number of people I have coming to me who've said, oh, I did this and I discovered this and then they locked it all away, and that's my life's work. And it's like, okay, sorry, mate. But this is the reality. So you only have a choice to be public about it and open. That's it. If you're working in the States or you're working already for the military. So there we go. So now when I'm looking at his current work, he's making all these claims about boron and hydrogen fusion, which is a known aneutronic fusion. However, there's no evidence. He's just showing some plasma, and you know, everyone can be forgiven for showing pretty plasma and making bold claims about pretty plasma. You know, I don't want to discourage him in any way at all. It's absolutely essential that people like him do the brilliant research he's doing, and it is different from any other research that's out there in the public domain. And I must credit him with producing out few but quality videos. I should learn from that. But anyway, the last point is that he's got a tungsten electrode in there in his second video, and tungsten 1910s, as I've already said tonight. Langmuir observed the tungsten producing gas. Now, what he's showing in that second video is exactly what we've been showing all day long in Vega experiments using tungsten, and in fact other materials as well. And you have David Hudson in the 80s blowing up two thumb-sized tungsten electrodes in a electric arc furnace when he was trying to deal with Ormus, right? Yep. There's nothing to do with the Ormus. It was electron clusters vaporizing the tungsten. Nothing to do with the ormus. Okay, so interesting, but nothing to do with the ormus. Okay, then you have well, there might have been some interaction, to be fair, but you don't need the ormus in there to achieve that effect. And the Sapphire group has shown that, because they had their Langmuir probe, which is interesting that it's called that, Langmuir probe coming into their double layers, and it vaporized in a few milliseconds. And then if you, Mizuno observed the same thing in, I think, 1996, where his tungsten electrode blew up, and the COP was calculated about 800 times the input power. But it's the tungsten that is fissioning. And we've shown that categorically what it does, because we've created a controlled and less intense, but on a surface layer, exotic vacuum objects clustering electron clusters, matter clusters, by using a Mars gas on a tungsten welding rod. And we've observed the transmutation that occurs. And we have replicated it in a self-built system by David Boutillier in Canada, based on the learning that has happened since. And so it's fissioning. And so if he yields any excess heat when he's got a tungsten electrode as his core electrode, it's not only that the most of the excess heat will be coming from the transmutation, fissioning rather, and transmutation of the tungsten. And if you look at the energy yields, it's in the hundreds of, over 100 mega electron volts for tungsten fissioning, and far, far less for your boron proton interaction. Okay, so there's much more that could be coming from that. Secondly, he's talking about this giving a house the possibility of having energy for an extremely long period of time. And that's useless when the principal electrode will be failing, and either failing periodically or instantaneously all at once, and you don't know when that might happen. It might all disappear like that. The whole tungsten electrode, bong, gone. So he's starting on the journey of finding out what was found out by many authors, starting with Langmuir in the 1910s. And all I can do is, what I intended to do was produce a video to reach out to him and say, look, this ain't going to work, mate. You know, you're going but keep doing what you're doing, because it's freaking fantastic. Don't stop, but be aware that your tungsten is going to, and it's provably where most of the energy will be coming from, because you can see the things flying off. And on a last note, I'll say that the things that are exploding off that he drew attention to in that second video do not care about the magnetic or the electric field. Why? Because they're charge clusters.
Thank you for that answer, Bob. That was awesome. I'm still hoping to get you up here, Canada, to view my work.
Well, they have to change those silly fascist rules that don't allow someone that's had COVID twice, but can't, but won't take an experimental jab to travel to anything on that side of the pond.
Yeah, me as well. Thank you very much. I've seen all your work, and I continue to watch it, and I won't stop. Please keep on.
Thank you. I'm really looking forward to see what you've done there.
Awesome. Awesome. Well, and thank you as well. Let me go back to Robert now. Robert?
Thanks, Tim. Hi, Bob.
Hi, Robert.
Hi. I just have a quite interesting how you can apply. You mentioned toruses or two tori. You referred to see how eddy currents cause a vortical phenomenon. You can see it because there's moving material in the ether. It was when you were talking about this experiment, very simple, where you could use an ultrasonic cleaner to see the patterns, where the antinodes, where pseudo-monopole.
I think it's actually at the nodes, but I always correct myself and say it's either one or the other, because I'm not thinking too much when I'm doing a live presentation. But I think it's actually at the
Excuse me for asking these questions. It happened so long ago. I'm not sure if you remember discussing it, but that's part of my research is vortices and torus. And I was just wondering if you remember how you could elaborate on that.
Yeah, so you can go and look at the MFMP YouTube channel. There is I think 18-minute or something video, which is in Ultra HD, showing you exactly how to walk through that process. Now,
okay, all right.
Ultrasonic experiments have been known to transmute since the early part of cold fusion. One of the leaders in this field is Roger Stringham, and he's worked out of Hawaii. And he has most recently worked with Tom Claytor, formerly of Los Alamos National Laboratory. And in their most recent publication, I think it was in 2019, but I think the work was done earlier, he'd moved from the 24 to 46 either 24 or 46 kilohertz ultrasonic transducers to a 1.7 megahertz transducer. The reason being is that he identified in a paper in 2012, that the transmutation was occurring around nodes. Now, he says that at that point in 2012, he's very close, I think, to good understanding. He's saying that electrons form a condensate, and they encapsulate the deuterons, which also form a condensate inside the electron shell. And then that causes self-compression, and you end up with two deuterons fusing. But the reality is that is not what's happening. A vast number of nucleons are being transmuted simultaneously and progressively by a condensate that is stable until it eventually blows up if it's driven too hard. But the reality is that he was observing this on the nodes. But because they'd moved from, the design of their experiments were a transducer in a small resonant cavity with a small amount of deuterium because it's expensive and you want to be able to monitor it, blah, blah, blah. They were never looking for something that was as trivial as vortical structures. And the sort of, how can we put this? It's like a cyclone and an anticyclone. That's exactly what's going on. And you have an impression and an outpression, and things coming down and things going up. And you get to a point where you essentially have compression and decompression, probably of the structure of the thing that holds matter together. And in one case, it synthesizes heavier matter. In the other case, it synthesizes lighter matter. And if you look at what I talked about last night, which was a 2005 or 6 paper by Rodionov and Savatimova, they're saying that there are these strings that are present throughout the universe. And on one end, you get a flux of neutrons being put, neutrinos, relic neutrinos being pulled in. And on the other end, you get them sprayed out. And this produces a system where you have heavier elements and lighter elements at either end of the chain.
Sounds like a lot of duality to me, which happens a lot in nature.
All of nature is this. You can fight it, you can say it isn't this way, but that's how it is. I'm sorry.
No, it's interesting that nature is full of dualities.
Absolutely.
You know, it's like balances each other out.
The universe is binary. Opinion may vary.
Yeah. You were mentioning about spinning materials that creates gravitational or anti-gravity.
So what I'm saying is, if you have something that's able to effectively prevent the normal interaction of relic neutrinos, if you consider that they are the means by which gravity is affected, if you're able to either prevent them from interacting, or basically it doesn't see the matter in a normal way, like the light can travel through, the relic neutrinos effectively travel through. So there is no push. So it doesn't matter where you are. There's just no influence of the normal mode of how gravity occurs.
Is this along the lines that gravity could be radiation instead of?
No, it's more. I'm subscribed quite reasonably, in my view, based on what I've seen, to the push model of gravity, and I believe the thing doing the pushing is the relic neutrino flux, which exceeds the mass of all the luminous matter in the universe.
I see.
And it's a superfluid condensate through the entire universe. This is energy available at any point in the universe. It is the wheelwork of nature. And the paper that I will be translating of the Russian Shishkin, with his permission, is arguing that the thing that keeps electrons spinning around atoms is this flux.
Okay, is this on the website?
It will be on remote view.
NFAI?
There will be a series of about 7 or 8 articles. I'm working with a Ukrainian to do the translation.
So I'll just do a search on your name then, and add vortices next to it.
Well, yeah, you can see lots of things on remoteview.icu. Yeah.
Okay.
Well, so I recommend everyone see the presentation from last night, because we've got SEMs which are absolutely, absolutely crystal clear, showing these tori, which are predicted from looking at John Hutchison's work in 2020 and published on February the 17th. And I've shown you guys in the previous presentation that I did. But that I was blown away on Tuesday this week when I literally saw them all over this material. It's like different clustering sizes. It's like, how is this even real? It's become too easy and too predictable. It's a bit boring now.
Okay. Well, and Robert, thank you. Let me go now. Actually, let me see if Thomas Anderson, because Thomas has been posting stuff. Thomas is muted out and he has his video off, but I want to see if I can get him in here, and then we'll go to Gabriel after that. There we go.
Mr. Anderson.
Because he's been blowing up chat, so I want to see if we can get him on to just ask the questions.
I don't remember the questions except the first one, which was well, it wasn't a question, but more of like a supposition based on what he showed with the black hole and white hole concept, that it seems like anything that goes to a denser state is a careful balance, from what I've seen, of just the right amount of gravitational force to confine the energy and compress the matter in order to get it. If you go too far, then my guess is that most likely it's actually compressing it to the point where it squeezes the energy out of it, and it drops to such a low energy state that it begins reacting to even gravity the way material does when it hits its Curie point, where it loses its ability to react to a magnetic field to be attracted to it. So basically dark matter, meaning black holes are most likely, if that's the case, they're recycling matter.
Oh, this absolutely is. I think the whole universe is, in fact, I would argue that any vortical structure pair, they work together, vortex and anti-vortex, as mother and father, and they take all the dross that's out there and they churn it up and make it into fresh material. It's like a recycling plant.
Well, I could also see too, if you squeeze stuff enough, instead of compressing, you end up breaking it down. So
that's exactly what Matsumoto is saying. It's exactly.
Yeah, I was gonna say, kind of like running through one of those grinders that they use to turn, what they call mechanically separated chicken, where it looks more like strawberry ice cream, where everything comes out as the right material to create a massive amount of hydrogen in
case you
area,
missed
and
it,
get a star.
I'll read you the second paragraph from the preface here. Recently, the author discovered a nuclear collapse which was induced by electromagnetic force in laboratory during studying the mechanisms of so-called cold fusion phenomena. Several kinds of nuclear reaction were directly induced by the electromagnetic force called electronuclear reactions, ENRs. They were found so far to occur in a special state of hydrogen clusters, which I explained how they form, called itonic clusters or microball lightning. The nuclear collapse was one of the most remarkable reactions among ENRs, called electronuclear collapse, ENC. Furthermore, very amazingly, completely broken materials by ENC were found to be regenerated again to thin tubes and films of conventional elements such as carbon, oxygen, and iron. The latter process was called electronuclear regeneration. And we were showing that all over the SEMs yesterday. And the actual thing that does it.
They have this whole thing where basically they believe they see where like the Big Bang happened. It's like, it could possibly be that we just had a moment where basically enough stable black holes had formed almost the equivalent of like a shell moving towards each other with such gravitational force towards a central point that they were literally exceeding the speed of light limit and slamming into each other and then causing an eruption. That's what all they're seeing is a remnant of that. Not meaning that that's the beginning or the end of the universe, but just they're close.
It could be that in our local environment, a 10 to the minus 33, one of these wormholes happened to spit out enough protomatter to create a universe in our part of space. And it's just like a bubble, and there's another bubble somewhere else, which is a quite separate universe.
Well,
but of course, it's the whole universe.
The stuff that they're talking about tracking too is the energetic material, meaning like whenever that attraction and slamming happens, there's plenty of material that it's exploding into that we consider dark matter.
Well, our dark matter is relic neutrinos are dark matter. Itons could be considered dark matter. In fact, EVOs could be considered dark matter if they've lost all interaction with all other types of matter.
Right.
That's
the thing is, it's literally something that has dropped to a state where it's become transparent to everything. So getting it to react again and turn into something would probably take a tremendous amount of concentrated energy, like that event that you were just mentioning. So it ended up fluffing up even more material than what was initially ejected.
So Shishkin says that if you create torsion fields in the environment, they're very damaging to human body. And the only way to get rid of them is to have a disruptive discharge, i.e. the sort of thing that Tesla would do. And that's how you restabilize your local ether structure. So I think it's useful to have regular discharges in your environment. And I think part of nature, what nature is doing when it's doing discharges, it's re-disorganizing the local environment.
Right, like the what are they? I can't remember what they're called. The field effect that's created when a lightning strike happens above the cloud. Like you get the lightning strike below, and then
we were talking about yeah.
Right.
Yeah.
Basically, they found that it basically stabilized all that radioactive material they thought was going to be lingering around for God knows how long once they had done atmospheric bursts. So.
Well, I mean,
instead,
one
within 6
way
months
to
it's all gone.
track where people are trying to make nuclear weapons is to look at Krypton 85, because it's 0.3% of the fissile material when you are producing nuclear weapons, when you are producing plutonium.
It's not normally found within our environment anywhere. near
No,
that
and
level,
because of
so-
its half-life, it's not normally found in the environment. But Krypton 85 then produces a lot of charge clusters in the air, and the way you detect is that there is an unusual amount of lightning storms. That's how you detect.
Wow. Okay. Kind of like that. What I'm trying to remember what was it thorium? I think that they were doping lightning rods with to get to basically work as a better.
That would make complete logic, because thorium, of which I have a whole bunch of it.
Well, they put it in welding rods to make the
in
welding
this
rods.
Kerala sand here, and this is why when I put
effective.
this is thorium sand from Kerala in India, right? And I've been putting this on the SEM last week, the week before, maybe last week, and I actually took this sample in 2017. I had no idea that I had no way of checking whether it was radioactive, but the local fishermen told me, oh, the sand on that beach is really radioactive. So I thought I'll have some of that. I do know that this is 35 cc and it weighs 35 grams approximately, all bar the plastic. This weighs 99 grams, right?
Wow.
And there's a lot of air in here. And so I predicted it was heavy, but since I got this wonderful Russian-made radio code scintillator, handheld scintillator. And it absolutely goes mental when you put it on here. I've turned off the alarm because it's just too scary to hang around. But it really is radioactive. But I used to go and swim for 8 years on this beach and surf on it. So I'm not overly fussed. If it was going to kill me, it's already done it.
So does that discern what it's picking up? Kind of like the
Yeah, so
XRF?
actually, no, well, I have
like a really cheap method to avoid spending a couple $100,000.
Okay,
on
so
XRF.
this is another device you can't buy because it's made in Russia. It's a radio scan 701. This is a radio code. So this is a scintillator. This tells you the gamma energy. So what you're looking at on there is the thorium energy peaks from that sand. Okay. This will do the alpha. Now, if I turn this on, there's basically no alpha in here. But when I take the top off that plastic container, there's 600 counts per second, right? There's nothing, and then there's 600. So this kicks out a bucket load of alpha. It kicks out a bucket load of gamma and a bucket load of X-rays, right? It's a wonderful material to test HHO with when you can't get access to tritium because of all the rules. You with me?
HHO.
So, yeah. So we're going to do Brown's remediation of nuclear waste, but no one will give us the nuclear waste. So I'm starting with something that I can get from the environment, which I got in case I needed to do it in the future.
You know, something that might help with the concept of electrolysis to break water down. And the guy who gave me the idea for this has passed away the second, unfortunately. So he never got to realize even trying this. His idea is to run the electricity down a deep well, crack it down there, and then use the rising gas to, collect the energy of it rising, kind of like the reverse of gravity of something falling, to run a generator. You know, like the containers that are collecting the two gases, while it's separating it and rising up to go to its final destination to be stored away and be used. The mechanism is attached to a belt that's basically attached to a generator, so you're generating electricity as that rises. Never mind, reclaiming the energy in the HHO. Of course, my original idea was to use them separately, and start with something like a
Well,
carbon source?
you've got a lot of ideas there, but when you're comparing what you get from one of the photons coming out here, let's say it's 62 kilo electron volts. That's one of the lower energy photons coming out of here, and you only need 4 point whatever electron volts is to split hydrogen, right?
Right.
And that's the highest amount of bond energy that you can get. Then you know, you can split a lot of hydrogen bonds with one decay. And there's bucket loads of decays coming out here. And I tell you,
well, that'd
the
be a good way to safely
Kerala
discharge
is
that
insane.
radiation too.
You what?
So that'd be a safer way to discharge that radiation too, rather than just laying around somewhere to, you know, bake somebody's feet, or being breathed in, or who knows what, trap it and use it.
Ask yourself what the original PAP engine was. It was radionuclides in a little shell, which then produced charge clusters, and then he discharged and blew up the charge clusters. Done. PAP engine.
I thought he was kind of
unlimited kinetic motion energy and an EMP that you can get a lot of direct electricity from.
Right. Well, I was going to say, every time somebody talks about generating power from, you know, from cracking water, I keep going back to basically like Tesla's little box he built out of stuff he just got from a hardware store, and he was able to run a car back in his day when they were much more power hungry off of that. And it's like, that sounds an awful lot like basically what they're building with the rainfield generators, where they're basically taking a negative material and a metal electrode, and then a positive material and an electrode, and as the water runs across each of those components, it's getting charged by the material before it hits the electrode and gets discharges. You build that inside of a box, that would probably work to, you know, to generate the power you need, but you could also probably use those two materials to attract the hydrogen and the oxygen. Instead of just being the electric charge, back it up with the charge of like the fluorine that's built into Teflon. You know, you could probably use something even more positively charged than like urethane by using cesium, because that's supposedly the highest positive charge out of all the elements that we've got. Well, out of all the
it has
ones,
the lowest work function, which means it will release an electron with the lowest amount of input driving energy.
Okay. So the fluorine is basically
the fluorine's almost the opposite. It wants an electron more than anything else.
Right. Okay, so you put that on the positive side to basically assist the positive draw of power, creating a deficiency of electrons. So,
fluorine's really nasty stuff.
Right. That's why it's probably much better that it be tied up to something.
You heard of chlorine gas in the First World War? Oh, don't give me fluorine gas.
Right. Well, and they're getting more and more of it every time they go digging in the ground and pulling more oil up, because those salts dissolve in the oil. A lot of people don't get that. It's a solvent.
Yeah, but
they got to figure out what to do with it.
The thing is about the fluorine, it's so reactive, it'll always be something else very quickly. Just hope it's not part of your body.
Or it doesn't form something like hydrofluoric, what is it?
Yeah, that's really nasty
rain,
stuff.
Acid rain, yeah. So we're having problems with that in Oklahoma because the fire blew
That's the same.
at the top of the refineries. Like, oops, you're supposed to keep that flame lit.
Yeah, so let me actually let me go to Gabriel now, who has patiently had his hand up, and then I'll go to Bernie after that. But Gabriel, go for it, sir.
Hopefully, I covered it. So,
thank you,
thank you,
Mr. Anderson.
Hello.
Yes.
Hello, Bob. It's
Hi,
a
Gabriel.
pleasure. It's a pleasure for me talking with you. I am asking this question reading the Google Translator because I speak Portuguese. I am Brazilian. My question is, what is the relationship between EVOs and longitudinal electroscalar waves, per scalar waves, and torsion waves? If I don't come back thanking you for the answer, it's because I don't understand English, but I will see the answer translation on YouTube. Sorry. And thanks in advance for the reply.
I'm not entirely sure I caught everything that you said. I'm very sorry.
And he pasted a bunch into chat as well. That was why.
He?
Yeah, he did. Let me kind of scroll back up there.
I see lots of laugh.
Yeah. Well, you mentioned the Jesus, Buddha, and Muhammad. I pasted a joke in there. So let me see. So he was asking, what is the relationship between EVOs, longitudinal electroscalar waves, pure scalar waves, and torsion waves? I think that was his first question.
So in the case of how Shoulders viewed this. The exotic vacuum object is both a receiver and a transmitter of whatever scalar waves are. So there is a direct relationship with how you can interact with them through scalar waves. I'm not an expert on scalar waves. I'm an expert on things I can see and repeatedly see and produce. In the terms of torsion waves or fields, I believe they are in possibly the Relic Neutrino condensate, which, being a condensate, it means that every part of the universe can immediately know when part of that condensate is affected, because it's all effectively, no one knows which particle is which. It's all the same particle everywhere, right? It's like that whole theory about was it Feynman? I don't know. Someone said that there's only one electron. Maybe it was Wheeler. Wheeler said there was only one electron, and it's everywhere. Well, you could argue that because the Relic Neutrino condensate is a condensate, from here to the other end of the universe, if you influence the condensate here, you influence the other end of the universe, and it's an instantaneous thing. A torsion wave would be in this superfluid, superconducting condensate. Or certainly superfluid, not necessarily superconducting. And so once that torsion is set up, it spins. And it spins and it spins and it spins. And because it has a very low level of interaction with ordinary matter, and you are not designed to live in a torsion field, I believe that's why people like Shishkin are saying this is not good for health. And when you get any vorticity going on, you will have some focusing of that vorticity, which will lead to condensation. So Shishkin has done a number of experiments where he's taken a 5,000, I believe, RPM motor, maybe it's 20,000, and he's put cones of different materials, everything from titanium and iron to PTFE. And he's then had X-ray film at a distance from these, and he's seen these birdies, which are the explosive witness marks of an exotic vacuum object. So spinning the ether, spinning the Relic Neutrino condensate, which is both in the environment and through all solid matter, then using a cone will naturally lead to a focal and a condensation of that and a production of exotic vacuum objects. So that is, in my view, the relationship between torsion fields and EVOs. And so if you can spin a solid material such that you create EVOs, then EVOs in turn, if they were clustered enough, you could imagine also spin influence the environment around them. And so there's just like a transmitter and receiver, one influences the other. So I have more to say with certainty on the relationship between torsion fields and EVOs and the relationship between them than I have to say on the first part of your question. So I think that's what I can offer at that point.
Awesome. Well, so let me go to, and we're starting to push closer to our time. Let me go to Bernie next. Bernie?
Hey, Bob.
Hi, Bernie. How you doing?
Very good, my friend. I'm gonna have to admit I'm gonna have to catch up on your most recent work. That sounds pretty awesome. Discoveries there.
Honestly, I think it's probably the conclusion, really. All I'm going to be doing is finessing the next time on the SEM, but I think we now can repeatedly produce the core of ball lightning, which is, in my view, the core behind coherent matter is the core behind all exotic technologies. So, and to see it repeatedly, having predicted what it should be, and that prediction be in line with all the Russian, the Japanese, and the American, and whoever's looked into this with any serious length of life, it's been a deep honor. And thank you for your support over the period.
Much love, brother. I can't wait. I'm excited. I regret that I haven't kept up on it lately. I've been out the last couple of weeks fighting strep throat, but I'm over it now.
Sorry.
And good. That really excites me. And what sort of conditions, like, do you think it would be possible to reproduce that core through in the electrolysis process in water, or only in like an air plasma?
So if you want to, it's nicely detailed in Takaaki Matsumoto's book to produce itonic clusters. He used a 1 millimeter lead wire. He used 120 volts, I believe it was, a number of 8 millisecond length pulses in potassium hydroxide. I think it was 1 molar solution. I'm just going to the page right now. And then he used a copper accretion plate and counter electrode. And the reason you use copper is because you've got no carbon in there. It's highly conductive. Copper doesn't absorb hydrogen, so it can't readily be damaged by this in the way that he did it. So yes, he in experiment S70 he used potassium hydroxide 1.5 molar per liter and 80 millisecond pulses, 20 second off, and only 4 pulses. So the experiment was 80 milliseconds plus 20 seconds times 4. You should probably be able to do that in your lunch break. You need a short length of lead, access to 120 volt socket, and a small cup of coffee, and a bit of potassium hydroxide, and an SEM would be good. So that's probably the simplest and lowest cost method to do this. If you want what we have seen to have been producing in the Vega experiments, you need 2 millimeter sheet brass. Brass has a number of properties that are advantageous. It's highly conductive. If you go and look at Lafferty's book, I haven't really discussed this, but Lafferty's book, which was the principal reference of Ken Shoulders when he started to look at John Hutchison's work, it lists after tungsten as brass as one of the most advantageous electrodes. I've already talked about the conductivity of copper that's in the brass, but you've also got, and I talked about this yesterday, you have copper oxides, which are photoelectric emitters, and you have zinc oxides form, which are both piezo and pyroelectric. And so you have all of the things that you would want in an environment as a cathode to be able to synthesize exotic vacuum objects. Then what you need to do is bunch them. So what we had is we had a flat plate. In fact, I'll show you. It's here.
Nice.
So Hank, we had this flat plate. So this is the thickness of the brass.
Okay.
And then there's 2 pieces of brass on top with a little gap in between, right? And a few centimeters above that, you have the anode. And it was 4 microwave transformers in a roughing pump level of low pressure air, okay? Why do we want air? Because we want oxygen in there for its paramagnetic nature and to produce the oxides on the brass that do the funky work with the photon and piezo and thermoelectric emission. And we want the oxygen to play a role in clustering of the charge clusters because of its unique paramagnetic nature. And so when you have the electrons, and the experiment actually, to create this sort of worm-like pattern, if I get it out and make it clearer to you, to create this worm-like pattern on here, like woodworm, okay? So this is a magnetic electron fluid condensate, and it has alternating north and south magnetic poles. And you can go and see this in incredible detail, the structures that it's producing. And what it's producing this vortex matrix, which essentially was as predicted by Maxwell in the 1800s. And there's very much more current research on condensates that point to the structure being the only structure that could be forming that does this. And so you get this electron bunching in that gap that starts producing this Bose condensate of electrons as a fluid, and that captures ions. And in that zone, you have such a density of this condensate of electrons that there basically is no Coulomb barrier. And this, I talked about this in my presentation last night, the 2005-6 paper of Rodionov and Savatimova. And they talk about this, and their first reference is this book that no one's seen, but now you can get. That was their first reference. In that zone, you can have mass numbers of transmutations occurring, and as it falls down, and it produces a hollow sphere. And the hollow sphere is, it has about a 1 micron internal skin, and then it has these cellular structures on the top, and the cellular structures are actually smaller toroidal clusters or individual spherical clusters that are clustering, and then it grows and more come on and grows. But what you are looking at is the collapse of the overall wave function when the coherent matter has finished. When it's actually happening, it actually looks like a little plasma ball, right? It's only when the coherent matter collapses that you see the overall structure, and that's when the music stops. And so the ball can get bigger, and it just reorganizes. So you can imagine, how should we put this? Imagine the surface of a pond, right? And you've got little balls, and you can put them on the pond. Well, they can organize themselves wherever. If you keep putting more balls on, they end up trying to organize themselves into a completely sealed unit. In fact, they use these to prevent evaporation from reservoirs, okay? If you can imagine that on a sphere, that's what's happening. More of these charge clusters are coming in, they reorganize themselves, their wave functions, and the sphere can get bigger and bigger and bigger. But it's still hollow. There's craziness in the middle. And only when the wave function of all of those structures collapses, when it runs out of electrons and the music stops being fed electrons, then you end up with this solid thing being formed. But all the time that it exists, it can transmute matter. And the Russians calculated it's out to about 100 microns. On our analysis over very many systems points out that it's over about 100 microns outside of the event horizon.
That's fascinating. That's awesome. So myself, all of my experiments are like through electrolysis. I see it as alchemy, and I've gone from two approaches of like David Hudson's as well as Mehran Keshe's monoatomics and aspects of it, and then connected it with Sir Isaac Newton's writings and translations of alchemy, and then going from more of the ancient alchemists aspects, but putting it through minimal amounts of both AC and DC electricity, as well as just small circuits with no electrical input at all, using like many different coils, and then nano coating layers, as well as pure elements from, I only used lead once, but I found it had a very heavy presence and energetical drain just from entering the room when I had used it one time. So I haven't really gone back to it too much, but like I make monoatomic gold, silver.
I would like to look at that. I have some monatomic gold in here as well. That was made in Hungary. I have analyzed that, and it is super fluffy. Like the nanostructures we couldn't look at, we couldn't find a scale that we could see something that wasn't more fluffy. We actually analyzed the leading brand of monoatomics, and it was rubbish. So the commercial thing, in my experience, the one that was most leading was just nonsense. It was just whatever, a calcium carbonate or something with, I don't know. So anyway, that monatomic you've got there. So as I said with this Buddha and this Jesus and this Muhammad, right? What you do is that is your template. The monoatomic is the template. Why is it the template? It's because it is vibrating at the frequency that the nucleus of that atom can vibrate. And it can only vibrate at that precise frequency when it's a monoatomic, okay? So that is your philosopher's stone for whichever element you're trying to synthesize, okay? That is the crystal nucleus on which you want to grow. Now, you have to do the electronuclear collapse of Takaaki Matsumoto, or however which way you want to do it, to create the protomatter that then is in search for something to follow. And, what the alchemists were doing was raising a body of material over 1000 degrees centigrade. And what you would want to do is ideally hit a resonance. And that's basically what I can offer.
Exactly. So that's exactly what I theorize, is that you can get cold fusion of elements, as Isaac Newton states, when they're in their crystalline form. And I've turned copper, gold, silver, zinc, and a few other metals into this pink crystalline form. And then the atomic hydrogen coming off of the cathode side of the electrolysis reaction will bond and make the cold fusion into the next metal if you're putting in that right resonant frequency of that metal. For instance, like these pure tungsten rods I have, that when I've had copper.
Bernie, we're almost out of time, sir. I want to try and get to Jared real quick.
We'll talk.
Okay, so Jared, do you think you can go really quick? We got about 2 minutes left.
Yep.
You got a UFO over your right shoulder.
Oh yeah, that's what I'm going to be talking about later. So just one quick question about the EVOs and ball lightning. Has any of your research led you down looking at solitons and how they might be responsible for it? Some of mine has suggested that ball lightning may be a cavitation of solitons in a confined space. Just wondering if you've seen any correlations between solitons and EVOs.
Well, the basic toroidal EVO is a soliton. It's a solitary wave. So straight up from the bat, it is a soliton. And basically it's a standing wave. So if you go and look at the 1954 paper by John Archibald Wheeler, he talks about geons. And geons are a standing wave, one going one way and one going the other, that creates a structure which is like a bead chain, where you have enclosed spaces of electric field, and between them you have magnetic field, and the whole thing is held together by a magnetic by a gravitational vector. And so that effectively is your soliton structure. That is your, in my view, something similar to that. It is what is building the basis for EVOs. And when you have one wave going around one way and one wave going around another way, and you add more energy to it, if you can make coherent matter, then you're adding the same energy into the same space-time. Okay, so it doesn't occupy any more space, but it has a lot more energy within it. And so that's how you get some coherence. And the only thing is when these get to a certain point, they eat up, in my view, the relic neutrino flux from the environment. And I've already talked about this when Shishkin had a cavitator. The reason for this cavitator in 2001, I believe it was, which rotated at about 5,000 RPM. He was trying to produce something, I think, to contract for mixing oil and water, producing an emulsion of oil and water. But he had felt very, very bad around having been exposed to it. Really, he felt quite ill having been exposed to it. So being a nuclear scientist, he decided to throw on a whole bunch of X-rays films. And then he saw these first birdies structures of these solitons coming out. And he says they are string vortex solitons, and they are the neutral form of exotic vacuum objects. And he credits Ken Shoulders. He says when they explode, the electrons come out with a velocity of up to 10 kiloelectron volts. And the matter that has been captured within them, which can be neutral as an overall cluster and passes through the water in the chamber, through the metal of the chamber, through the air, through the packaging on the X-ray and into the X-ray, when they explosively unpack, as he describes it, they eject the ions that have been captured on their passage through that material. And they eject them with such velocity that the number of grays produced is sufficient to destroy red blood cells and cause DNA damage to white blood cells. And this is well characterized. The research started in earnest in 2009 in Dubna, and they've researched on mice as well, and also plant and other types of living organisms. So they know very well that this can damage. So anyone working near a spinning thing, welding, ultrasonics, all kinds of different systems that people use all of the time, they will be kicking out these clusters at various levels of intensity. So, but you can put them to good use. You can put them to good use for remediating nuclear waste and so on. So, yes, and he calls them solitons, string vortex solitons, and he says at least that they are most likely condensed relic neutrinos. Now, why is this? Why would he know this? He didn't publicly say this, but I have said this publicly since. In 2018, at that conference in Sochi, he said off the cuff that his device would produce this flux of these string vortex solitons up to a period of time, and then it wouldn't. And then he found the only way to produce them again was to physically move the generator to another part of his lab. What does that tell you?
So it's not a constant source of neutrino flux. He used up all the local flux and had to go somewhere
this is
else.
why you can't put people in solitary confinement, because it's your connection to reality. That's why it's unbelievably cruel to put people into solitary confinement, because this relic neutrino flux cannot travel through glass. It gets reflected partially by like sunlight. So if you're in a confined space, you will, all living organisms use these things. So you will literally lose reality. People go mad because they don't have connection through reality, through the relic neutrino flux. It's unbelievably diabolical to do this. I don't know who worked out that this is what it does to consciousness, but it's really cruel. So that's my personal beef with the abuse that goes on with isolation in that sense. But so the cohering structures are capturing the relic neutrino flux. Now, why do we know that this is in the environment? There was a researcher from China and a team called Xu Enju, and he worked between 1989 and 1999. And he found that during three-body alignments, that's solar eclipses and lunar eclipses, there were 4 properties that he could observe that changed in the environment. 1, there was a sideways movement in a tensioned piece of metal. That means something that was diffusing from outside of the penumbra in was able to exert a force on a metal plate. This is the pressure force of gravity. This is the relic neutrino flux. He didn't know it was that at the time, okay? Second thing, the spectral emissions from elements changed either inside or outside of the three-body alignment field. So light traveled at a different, or the light that was coming back was different.
And Bob, we're over time, sir.
Okay.
Okay.
No worries.
Oh yeah, I mean, if you want to wrap that statement up,
There's 2 more factors. Nuclear radioactive material. He had atomic clocks. He went into the American records. They use rubidium-87 and cesium-137. They changed their decay rate in a three-body alignment. Okay, so that's a neutrino interaction. Therefore, it must be some form of neutrino doing that. And the last thing was, metals, in his case a lead tin alloy, crystallized in a linear diffraction pattern when it didn't outside of the three-body alignment. All of these are due to the diffusion of relic neutrino fluxes, in my opinion, and that is why Shishkin observed that he condensed all of the relic neutrinos within the event horizon of his generator, and he had to physically move it.
Wonderful, wonderful. Okay, well, let me do this, Bob. You've blown my mind like 20 different times here. I'm putting this on speaker view. Everyone, let's give a giant applause to Bob Greenyer. Bob, that absolutely tremendous. You have such an amazing wealth of knowledge. I mean, I've really never seen anything like it. I cannot thank you enough for doing the Q&A with us. I'm so glad we were able to get you back in.
It's a pleasure, and I would really seriously encourage people see the work that was presented this week. It's now a science. It's a reality. People can replicate it, and I look forward to a time when whole universities are researching different aspects of what this technology can do.
Wonderful, wonderful. Well, thank you again, sir. So what I want to do now is, let me see. I want to go to Dr. John Brandenburg. Let me do an intro first, though. So physicist Dr. John Brandenburg is joining us again. He will be discussing the hypothesis that ancient Mars suffered a bizarre nuclear accident, as indicated by samples of argon and xenon isotopes detected across the planet's surface. John suggests that the prevalence and balance of those isotopes is consistent with artificially generated nuclear activity, and he explores various scenarios that could lead to the creation of this evidence. So, John, let me see. Are you with us, sir?
Pardon me. A little rusty on this. Yes, here I am.
Perfect. Thank you, sir. Thank you.
Sorry, I missed the previous talk. I myself figured out how to make a facsimile of ball lightning in microwave ovens reproducibly and published that. and it became my most cited article for a while. So that was great. So yes, it can be done, and it's very strange.
Wonderful. Well, John, yeah. So I'm all set, sir. Do you have a PowerPoint that you want to share?
Yes,
or...
I do have a PowerPoint. Pardon me. Let's see.
And I've spotlighted your screen. And so if you do there's a share screen button that should be the very bottom.
Screen.
Yes, sir.
And it says, it says share screen.
Yeah, and then it will make you pick the window to share.
Okay. It says window to share. You see this? Pardon me. Okay. I can't see myself anymore. Oh well, that's okay. I know what I look like.
Yeah, and it looks like it hasn't completed sharing yet. Is there another prompt?
No, just a second here. And I'm sorry, I normally go through all of this before, long before but we had some difficulties with our legal department at Kepler Aerospace where I work. You'll see what I mean in just a minute. Okay. Okay, I think we're making progress here. And once again, I apologize. I normally get
Okay, and John, are you still with us? Looks like your screen went off. Okay, well, I should apologize to everyone for some of the technical issues that we're running into. John is working on things. Let me, since I don't hear him, I'm going to actually call him on the phone. Let me mute myself out for just a moment.
Mute. Okay, sorry, guys. Like I said, we had a little last minute argument
Okay.
about
What? Yeah.
content.
So John, why don't you hit the share screen button and get started with the PowerPoint?
Okay, yeah. Let's go. Okay, window. Okay, share.
There we go. Oh, well, look at that. Okay.
Okay.
Perfect. And then
squared away?
yeah, looks like we're there. Are you able to do slide mode? Yeah. Just I guess play from beginning.
I'm doing slide mode now. Okay. I'll just have to.
Yeah,
okay.
no, you're doing great.
Anyway,
you're doing great.
Okay. Once again, guys, sorry for the technical difficulties. Here we come to the great non-disclaimer disclaimer.
Okay. Well, yeah, and do the
Kepler has to have something to do.
Do the
And
from
so-
begin, John. It's showing it's really small and it's showing a giant window. Can you do slide mode? That way people can see.
Yeah, that's what I'm doing, supposedly.
Try hitting from beginning. It's a big button.
Okay.
It's an enormous button up on the top left.
Okay, very good.
Do you have two monitors?
I'm trying to get out of the slide mode that I'm in and get back to okay. Here we go. Okay, it says sharing window. It says
And okay, you just stopped your share.
oh God.
Okay, just hit the green screen share button again.
Okay, hold on a second.
You could just, you know what? You could
here we go.
Just do share screen and just share your main screen. That's okay. And then you can just maximize it. Just do
Okay,
share screen and share the.
Okay, it says entire screen.
Yeah.
Or, okay, well here. Okay, so you're not seeing a large image of this. Okay.
Yeah, it's not sharing quite yet. Yeah, just there. Okay. Now we're
is that
getting
better?
started. Give me
Okay.
just a sec.
Here, let me expand this.
Yeah, that's much better. Okay.
Okay.
Slideshow from beginning.
From beginning. Okay, here I go. Can you see everything? Can you see a big slide now?
You know what? Why don't we roll with what we currently have? We'll do that. No,
Okay,
because it
okay.
started in a new window.
If you can see the slides, then I'll just start. Okay.
It's on number 70. It's on number 74. It's starting on number 74. Is that the one you're on?
No, that's not the way it's supposed to work.
Okay, that's because you didn't share the screen. You shared the window. So
I shared the window. Okay.
Okay,
Like
so
I said,
let's John, let's do this then. Let's do this. Stops here. Let me. I will stop your screen sharing.
Okay.
Okay. So hit the screen share button again.
Okay. Hold on.
It's the green button at the bottom center of your screen.
Okay.
Okay, and then share the entire screen. That should be probably your top left option.
Yes.
Okay, try that. Just everything. Just
it won't respond for some reason. I think there's been an upgrade to the Microsoft system since I last did this. And now nothing works. How about okay, that's small. Okay, so that's okay, here I am just to share screen again. Oh, hit entire screen. The legal department must have overheard me complaining about them.
Yeah, just share screen and is there a way to share the entire screen?
Well,
or if you could go back into what you were in before, just so that
yeah,
we can see your
let me just
slide
go
deck.
back to what I was in before.
Yeah, and then don't play, and then don't
slide.
press. Yeah, don't press play. You just keep it in design mode, and you can scroll through them.
Okay. Are you seeing this?
Not. It's just showing you, sir.
Just showing me.
Green screen
How about
share
this?
button. And then it will ask you to select a window to share. You can share a window, you can share the entire screen.
Yeah, that for some reason.
Yeah, are you
we
able
did
to?
all this a couple weeks ago, and everything worked fine. Something has changed. I don't know what. Okay, share screen. I'll go. Okay. Entire screen. Are you seeing anything now?
No. Is there a button to confirm that? Is there a button that?
Yeah, the buttons are being blocked for some reason.
I
went through this last week, and everything was fine.
Is there a way that you could share? Is there a way you could share just the PowerPoint window again? We can kind of roll with that.
Yeah, let's see if we can do that. Okay, I'll go entire screen. Okay, it says view, speaker view, gallery view, full screen. Okay. Can you see a Kepler slide now?
No. Is it asking you to confirm that?
No.
Okay. Are you able? So maybe you could try sharing the screen, sharing the PowerPoint.
Yeah. Okay.
We could just go back to what we're doing last time.
Okay. Okay, share screen. It says window. Share.
Okay.
Are you seeing this?
Perfect. Yes. And now you're on slide 1. So what I would suggest
Okay,
is,
great.
yeah, just
Not doing anything else.
Yeah, and then just.
Okay. Okay, friends.
And John, try
I
hitting.
apologize for this.
Okay, try hitting the. No. That will start a new window.
Okay.
Try going to the next slide. Just try clicking on the next slide to see if it follows you.
Oh yeah.
There we go.
Here.
Okay,
Is
sir,
a
I will.
Disclaimer.
I'm gonna mute myself out. Yes. And go for it. And my apologies for all of the technical challenges.
Great. Let's go for this thing. Yeah, I'll try to move through quickly. Very good. Is everybody seeing this okay? You're all
Yeah,
muted.
yeah, we can see you
Anyways.
now and it's working. It's working. Thank goodness. And thank you for
Okay,
your
great.
patience, John.
Well, thank you for your patience. I'm just surprised. The last time was very easy, and this time it's just it's been much more complicated for some reason. Okay, anyway, so disclaimer by saying that this is my opinion. Yes, it's my hypothesis. Everybody knows what a hypothesis is, apparently, except the legal department. So anyway, the title of my talk is Evidence for Past Nuclear Explosions on Mars. I consider this to be an important piece of information about the universe for the human race at this point in time. Okay, this is of course our planet. You go into the solar system, you'll spot this planet immediately because it's covered with water. And the presence of liquid water basically says life environments, at least for Earth-like life. Okay, now the first Earth-like planet in the rest of the cosmos was Mars, and still is Mars. I mean, it's more Earth-like than any other planet in the solar system, and apparently was much more like Earth in the past. Okay, so I'll be talking about Tesla and Mars very quickly. Mariner 9 and its Zeitgeist, meaning the spirit of the times. Viking and Cydonia, reconstructing the past climate of Mars. Mars polar lander results. New Mars synthesis, taking together all the Mars data from the meteorites and landers and orbiters and putting it into a new picture of Mars in the past. New images of Cydonia and Utopia, and then what destroyed Mars? What made Mars what it is today from a planet which apparently was very Earth-like in the past? Okay, in 1901, about the same time that Lowell was doing his work on the Mars canals, Tesla got all the governments around the Earth to go radio silent so he could listen to signals from Mars, and he believes he picked up some. Now, I wasn't there. I don't know what his data looked like, but he insisted that he had received signals from Mars indicating technical civilization there. Now, this is part of the search for extraterrestrial intelligence. Here we are in our here we are in the galaxy. Nothing could be more average than where we are in the universe. We're in an average spiral galaxy. We're in an average place in that galaxy. And this is in keeping with what's called the principle of mediocrity, which mediocrity means average. We're C students. We're not an aberration on the cosmos, though some people would like to think we are. We can always do better, but mediocrity says that if you want to know what Earth-like, intelligent beings in the universe, intelligent civilizations and life environments look like, just look around you. We're average. This leads immediately to the feeling that we are not alone in the universe. And there's more and more evidence that life environments like Earth are very common in the universe. Every star, except for a few oddballs, apparently has a family of planets, just like hens and chicks. Question is, how many other civilizations occupy the galaxy, or how far would we have to go to find signs of civilization, past or present, on another planet? Do we have to go light years? Do we have to go light minutes? Well, in 1970, Mars, which had always been the object of great fascination since the Victorian era, became the focus of a bunch of Mars probes. And the Zeitgeist of the time, the spirit of the times, held that Lowell's canals and Tesla's signals suggested that Mars had been inhabited. And this was a very persistent thought, not only among the public, even if the science community rejected it, but among the government officials. Remember, the government officials listen to scientists all day, especially when they're asking for money. And unfortunately, they know science and its foibles. They don't believe everything that scientists say, especially when they're projecting miraculous results. And so there was a certain amount of skepticism for mainstream science rejection that Mars could have been inhabited in the past. So despite new probe data in the 60s, the Orwellian view of Mars persisted. For one thing, when they first got to Mars with probes, they found a bunch of craters like the moon. But then they also realized that, gee, Mars has a lot less craters than it should have if it was moon-like. Then in 1970, Mariner 9 went into orbit around Mars and found past Mars water channels, indicating an Earth-like climate in the past. Liquid water defines what an Earth-like climate is. And thoughts of a dead civilization on Mars were renewed. They were especially renewed because of some of the things they found there. Von Braun suggested perhaps archaeologists should be the earliest humans sent to Mars. And von Braun was certainly in the loop at NASA. Now, what they also witnessed at Mars on Mariner 9 was a global dust storm that covered the planet from pole to pole. This led to the mission almost failing because the mission had to kind of mothball itself in orbit around Mars. But it survived just fine. But it helped end the Cold War because people realized that this global dust storm could happen on Earth in the aftermath of a nuclear war. So Mariner 9 survived the Great Dust Storm, and it mapped the Mars total surface to about 2-kilometer resolution. Then it took high-resolution images of about 1% of the Mars surface, and it discovered a Great Canyon system, the Valles Marineris, and extinct water channels. And some of the water channels indicated from their form that they had flowed a long time, and they were on lightly cratered terrain on Mars, indicating young terrains. So this indicated that Mars had had liquid water for most of its history. We knew the older parts of Mars were covered with water channels. So were the young parts. So Mars was much more Earth-like in the past for billions of years. They also saw at Elysium what looked like pyramids. And they came back, they were so fascinated by these that they came back and took another picture of them, which was very difficult for the Mariner 9 to do, but they did it. So they took a picture at sunset and a picture at morning locally on Mars. They were about 1 kilometer high and 3 kilometers at the base. Unfortunately, Mariner 9 couldn't investigate any further on that. Then in 1976, encouraged by the water channels on old water channels on Mars, they sent the Viking to look for life in the Mars soil. They found strange chemistry in the soil, which they attributed to not to life, but to oxidation. So anyway, but these are the Viking landers, which were very successful. But the orbiters part of the mission took this picture in July 1976. At Cydonia Mensa, they got a picture of what they called the head. And it was near the prime landing site. The reason they were taking such high resolution pictures of that area of Mars because it was Cydonia and they wanted to land at Cydonia. This was then changed. This mission objective was then changed. They also said that they took a picture an hour later of the Mars face and it didn't show anything. That wasn't true. There was no picture an hour later because it was nighttime had fallen on Mars. They took the head picture on at local sundown where the shadows are longest and shows the most relief. They waited till everybody had quit talking about it, which they did, and they waited for 30 days. Then they came back and imaged it a second time in the mid-afternoon. And this is what the picture at mid-afternoon shows. It shows it is a face-looking object, and also immediately noticed was a pyramid. This had been visible in the original picture, but no one noticed it. So, but DePietro and Molinar, who were investigating, found this picture and identified the pyramid. Pyramid is, the head is about 2 kilometers wide on the side and 1 kilometer tall. Actually, it's more like half a kilometer tall, pardon me. And the pyramid, though, is about 3 kilometers on the side and 1 kilometer tall, like the pyramids of Elysium. So this led to people thinking, well, what on earth looks like this? Well, the Olmecs, a very mysterious civilization in Central America that predated the Mayans, carved a bunch of heads like that. And of course, there's the Sphinx in Egypt. Now, this is what the Sphinx originally looked like. They've dressed it up a little bit. Any archaeology on Earth will suffer erosion. The same planetary environment allows life on Earth: rain, sun, moon, cycles of the seasons, winds, creates erosion. And also, so it erodes the artifacts of civilization that we create here on Earth. It would do the same on Mars. Ancient Mars looked like this, apparently. And by the way, the Mars ocean was discovered in the process of examining the pictures at Cydonia Mensa. It became apparent it would look like it was on the shore of an ancient ocean. And I was the first person to give a paper on that. I don't get any credit because of my connection to Cydonia. But that's what Mars used to look like. So how long did Mars and Earth share similar climates? I wanted to mention also that the ocean lay on the youngest part of Mars, the most lightly cratered. When you don't know the age of a planetary surface, you count craters and estimate the cratering flux relative to the moon, where we have rock samples from specific areas on the moon of a certain age. And what you find is that the more craters, the older the terrain is. So on Mars, the southern half of Mars is heavily cratered. Apparently it was a desert for most of its history, and the craters have been preserved from almost the foundation of the planet. But in the north, there was a lot of geologic processes, a lot of erosion, a lot of volcanoes, and the craters are actually very sparse, and that's where the ocean bed is. So that means that Mars ocean lasted for most of its history geologically. Okay, so how long did Mars, Earth, and share similar climates? Did Mars have life? Well, I think at this point, if Mars had an Earth-like environment, it certainly had life. We've found now fossil life on Earth dating from 4.2 billion years ago, almost as soon as the Earth had an ocean. So, and it didn't come from the primordial soup involving the first single cell with the enzyme systems and DNA and stuff like this. It was probably panspermic. So did Mars have life? Most certainly. It probably got life on it from the same place the Earth got it, from space. Did Mars' Earth-like climate persist long enough for Mars life to evolve? Yes, apparently it did, because the ocean on Mars, which is the signature of Earth-like climate, apparently persisted until late in Mars history. Mars is 4.5 billion years old, the same as the Earth. This ocean apparently lasted for at least 4 billion years. What level of complexity did Mars life reach? here's the Paleo Ocean of Mars, first proposed by myself in 1986 to an audience consisting of about 1,000 Mars scientists, none of whom can seem to remember that I gave this paper. I know my tribe, unfortunately, the tribe of scientists. Mars polar lander lands on the old ocean bed. Water and ice is found right under the surface. The soil can support life. It's got plenty of water. Soil is consistent with an old ocean bed. It's even salty. Old Mars ocean hypothesis is confirmed. Now, Mars, as it turns out, it was rather accident prone. It's right next to the asteroid belt. Here's, by the way, you can see the transition in terrain from here's where the ocean was, here's where the shoreline was, and of course, here's the highlands. And right on the boundary of the ocean, apparently this impact happened. It was as big as the one dinosaur annihilating Chicxulub impact on Earth. It would have changed Mars climate. It probably just came from the asteroid belt. What it did apparently was if you look at the rate of water erosion, it could be estimated from the pictures. Apparently in this epoch, Mars lost a lot of, Mars went into a deep freeze, but then it recovered. So Mars had a kind of its own Chicxulub impact, but apparently recovered and was eroding stuff with liquid water again. From this, you conclude that because of Mars' location near the asteroid belt, it was accident prone. So you can gather all this data together. We have all these Mars meteorites, we have all this orbiter data and pictures. We have all of these rovers roving around sampling things. It looks like Mars cratering rate is about 4 times what the lunar rate is, considering that Mars is next to the asteroid belt. That's reasonable. Mars apparently had a persistent CO2 greenhouse plus methane greenhouse like Venus for about 4 billion years. The greenhouse was stabilized by the Northern Ocean and oxygen. As it turns out, if you put up a CO2 greenhouse, the CO2 carbonic acid will start combining with the rocks, except if there's an oxygen atmosphere, like on Earth. Then the rocks oxidize and release the CO2 back into the atmosphere. So you can have a stable, chemically stable greenhouse, carbon dioxide greenhouse if you have a strong oxygen component in the atmosphere. Mars apparently had life long enough to have biological evolution like on Earth. Whoops, pardon me. Mars greenhouse destroyed by a LEO impact, causing mass extinction, but it apparently recovered. Then something else happened to turn Mars into Mars, the Mars we know today from being a planet that looked like Earth. It was apparently some sort of nuclear catastrophe. Now, why did Mars die? What was the cause to turn Mars into Mars? Well, there's evidence of massive thermonuclear explosions on Mars 180 million years ago. When I originally discovered the isotopic data, I thought it might be a bunch of large natural nuclear reactors that went unstable and exploded and caused Mars to lose its atmosphere. We had natural nuclear reactors on Earth. This was actually a well-received idea when I presented it at the Planetary Science Conference down in Houston. The evidence was a Xenon-129 spike in the atmosphere. Rocks, the Mars meteorites we got apparently were bombarded by an intense neutron bombardment, turning a lot of the bromine 79 into krypton 80, which is a gas. Bromine is a liquid, or would have been bound in the rocks, but it released this inert gas, krypton 80. And there's a lot of evidence for so an intense neutron bombardment late in the Mars history, about 180 million years ago, which is a blink of an eye in terms of geologic time. And there's thorium potassium scars. Potassium becomes radioactive when it's bombarded by neutrons, and thorium is naturally partly radioactive, So it can be, Mars' atmosphere is so thin, you can actually orbit a gamma ray spectrometer around Mars and figure out what the rocks are made of by getting the gamma rays out of them through the atmosphere. Now, here is the first sore thumb at Mars. This is the abundance in the atmosphere relative to Xenon 130. And it shows that the blue line is Earth, where Xenon 129 and Xenon 132 are roughly equal. Those are the two most abundant Mars xenon isotopes. So Mars and Earth match pretty well, except at Xenon 129, where Mars has this superabundance. Now we've probed the Mars, the atmosphere of Jupiter. We have Earth. We have the solar wind. We have Mars. We have a lot of meteorites. All of them show Xenon 129, Xenon 132 to be roughly average, except for a few oddballs, which I'll talk about in a minute. So what is the explanation in the planetary community for the Xenon 129 problem, they call it? Well, it turns out it's a coupled problem, because when the theory of the formation of the solar system was formed in the aftermath of a supernova explosion, just about the same place we are now. And so the solar system was kind of born radioactive. And it had a lot of unstable elements. One of them was iodine 129, which has about a 15 million year half-life. And then, so it decays into Xenon 129. We see that on Earth as a result of nuclear tests. However, another component of this is what's called plutonium-244. It's a very rare, it's not any good for nuclear weapons because it's so stable, but it's the most stable form of plutonium. It has a half-life of 80 million years. And when it decays, it produces a lot of Xenon 132. On Earth, Jupiter, and the Sun, apparently those two, the iodine 129 and the plutonium-244, create a balance between Xenon 129 and Xenon 132. That's average and normal. The mainstream view was that Mars lost its atmosphere early, and the iodine 129 trapped in the rocks then turned into Xenon 129 and filled up the atmosphere and produced this excess. But the problem is that they don't find any trace of the plutonium-244 decay products, which is principally Xenon 132. That's gone. So they have, and its half-life is so similar to Xenon in geologic timescales, 15 million versus 80 million, and it would have followed after. So there could have been a momentarily increase in Xenon 129 in the atmosphere, but it would have been, done away with by the decay of plutonium-244. So this is a big problem. The other big problem with this model, which kind of assumes that Mars' atmosphere has always been thin, is that early Mars atmosphere was dense and wet and was largely retained. There's water channels all through the southern part of Mars, which is heavily cratered, and up to the north. So Mars not only had liquid water and a dense atmosphere, which is required for liquid water from the very beginning, but it also lasted for most of Mars' history. There's no evidence for Mars losing its atmosphere early and not regaining it. Now, there's a process called R process, meaning R for rapid, means rapid intense bombardment by neutrons, by high energy neutrons. And if you compare Earth and Mars with the R process xenon products, which are worked out in simulations for supernovas, you find that the xenon 129 spike is reproduced. So there's a competing process, which is like, it's called the slow process, and occurs in ordinary stars or nuclear reactors that use thermal neutrons. And it hardly produces any xenon 129. It favors the heavier xenons, xenon 132, etc. So the slow process produces almost no xenon 129 relative to 132. But the R process, the rapid process, produces the xenon 129 spike versus 132. So xenon 132, 129 abundance in the atmosphere over the abundance of xenon 132 greater than 1. That's the signature of the R process, and that's in the literature. It's in the literature from supernova simulations. Now, there are only two known places where we know of that produce R process events. One is a supernova. If there was a supernova on Mars, it would have blown the planet to pieces. We wouldn't have a solar system. However, you see R process in thermonuclear explosions. In fact, they use some of the same codes to simulate supernovas and nuclear weapons. When I was at Livermore, that was done. So we now know where the 129 excess came from. It came from an R process event. At least that is the only known process that can produce the Mars xenon excess. Also, Krypton 80 over Krypton 84 is enhanced 10% over solar nebula baseline. Xenon 80 is believed to be generated by neutron capture on bromine 79. Bromine is a toxic element similar to chlorine, and it's bound in the rocks. But if it gets hit by neutrons, it turns into Krypton 80, which is inert gas, which slowly works its way out of the stones into the atmosphere. So a neutron fluence of 10 to the 15th centimeters per centimeter squared is required on Mars rock. They had to put rocks in nuclear reactors to simulate, to find results that were similar to what they were seeing in the Mars meteorites from 180 million years ago on Mars. So one of the first identified Mars meteorites, Mars meteorite ETA 7901, shows abundant evidence of this Mars neutron bombardment. And that was late in Mars history and geologic time. Now there's some other interesting things. Mars, such neutron fluence would have also activated the potassium in the rocks. Now, Mars has less potassium than Earth by about a factor of 10 to 3 in the Mars rocks. Yet there's these two hotspots on Mars where there's a lot of radioactive potassium. And not only that, it looks like it's consistent with kind of a neutron generating event here, an explosion. that created shock waves that wrapped all the way around the planet and created a deposit at the antipode on Mars from the explosion. If you look at Mars thorium, the same pattern persists. Though it's slightly shifted, there's a hot spot and then an antipode deposit. So it looks like something, this neutron event happened here, caused shock waves all the way around the planet, and they ended up at the antipode. Now, I spent about 10 years at nuclear weapons design laboratories, Lawrence Livermore and Sandia Labs. I didn't work directly on nuclear weapons. I worked down the hall from the people who invented the neutron bomb. That was really something. But I worked on controlled fusion. But thermonuclear weapons have a fission trigger consisting of plutonium, generally plutonium atomic bomb, which then fills a casing with radiation, which then implodes a hydrogen-rich secondary, which then creates the hydrogen reaction. So it starts out being fission and then fusion. Then the casing in what's called the tamper are made out of uranium or thorium. In the case of the W-71 Canakin space warhead, 5 megatons, the casing was made out of thorium. They declassified that in 2008. And this, even though that uranium is 238, or the thorium is not susceptible to making an atomic bomb out of, it's the wrong type of isotope. The high energy neutrons from the fusion split those nuclei, and they boost the power of the hydrogen bomb by about a factor of 2. So a modern hydrogen bomb goes fission, and then fusion, and then fission of the casing, which can be made of uranium or thorium or a mixture of the two. Now, if you look at the amount of potassium in the Mars rocks that we've received, the Mars meteorites, they all have very little potassium in them. They're down here, and they all have very little thorium, except on Mars, on the surface, there's a lot of thorium and a lot of radioactive potassium. So that indicates, how can the surface of the planet be more radioactive than the rocks from subsurface, which are the Mars meteorites? They were believed to have been subsurface rocks blown to Earth by impacts from the asteroid belt. Well, if you had a big nuclear explosion on Mars, especially if it was an airburst, that would do it. Here are these here are the sites of these hypothetical nuclear explosions. One was in Mare Acidalium, upwind of Cydonia Mensa, would have carried the shock waves, and also the fallout most prominently to Cydonia Mensa. There was a smaller nuclear explosion, the other hotspot, at a place near, it was upwind of Galaxis, a place called Galaxis Chaos. I'll be showing you pictures from there. And there are no craters in these hotspots. They're almost completely uncratered. This indicates that there couldn't have been an underground natural nuclear reactor that went unstable. It has to have been an airburst in midair, several kilometers up, so that it didn't create any craters on the surface. Now, if you look at Galaxis Chaos, or what is also called Utopia, because You see, for one thing, the pictures from Viking, there's a watermark on the lens. Here's some what look like ruins. And we're going to focus in, though, on these two objects here. Galaxis Chaos shows what apparently are two fake carved faces into the Mars landscape. And the second one, the lower one, is kind of low relief, so it disappears at certain sun angles. But the overall structure of the face is revealed in lower resolution pictures. And it looks very similar to the Cydonia face. It's about 2/3 the size of it. This is large. And it's now been found in multiple pictures. If you do a detailed comparison between the Viking pictures for the Utopia face versus the Utopia upper face versus the Cydonia face, you find they both seem to have cheek ornaments, a helmet, and an indentation over the left eye, or the right eye rather. Anyway, now in 1998, with great fanfare, the US government took a new picture of the face on Mars. This is what they released, unenhanced, uncorrected for, you notice the crater is elliptical, not round, indicating they're not taking this picture from above the face, they're taking it from the side. Here's an enhanced version due to Mark Carlotto. And you can see there are ornaments on the helmet, and there's nostrils in the nose. Then there's eyes, mouth, nose, mouth, helmet. It's all there. Dr. Carlotto was also able to use a three-dimensional model of the Cydonia face based on the Viking pictures and a shape from shading algorithm to then stretch the new image over that three-dimensional model and rotate it so we could see what it would look like from above. It looks like the Lion Man from Wizard of Oz. And you can see there are clearly two nostrils in the nose and more details on the helmet. Now, we've been taking a lot of pictures of this thing, and the nostrils have been confirmed in some of these new pictures. Here's Mars Odyssey, 2001. That's under control of University of Phoenix, and therefore didn't go through JPL, and they could release whatever pictures they wanted, the way they wanted them. And they took pictures of the face on Mars. Here's you can see there's a circular crater beside the face. That means you're taking a picture from straight above, like the original Viking pictures. And you can see the face is there, so is the pyramid. It's all the same. Now, one of the things that happened is in the new images, we have higher resolution pictures of the pyramid. It apparently has what looked like a square doorway. Well, actually, no, it looks like a place where a bunch of bricks have collapsed off the face. And you can see that clearly in the new pictures of enlargements of the new pictures of the pyramid. And once again, we have in recent Odyssey images over and over the same structures we saw in 1976. Now, they've also re-imaged the face at Galaxis Chaos, or Utopia, as they call it. Here's the Odyssey picture. Here is the Viking picture. As you can see, it is a, looks like a face and a helmet. And all of the details are there that were originally identified from the Viking picture. They've also taken them now with the Mars Reconnaissance Orbiter, a different sun angle. It looks like the part of the face may have split and sunk so you can't see it from above, but from the side. But if you zoom in, because the high MRO images are so precise, you can see that around the nose, there are symmetric nose ornaments. So we published a hypothesis in 1991 based on the Viking data that Mars had Earth-like climate, life, and evolution. Mars developed humanoid indigenous level of civilization, approximately Bronze Age level of technology. We don't know its level of technology. All we know is we see some massive ruins. It'll take a detailed investigation with boots on the ground to figure out what its real level of civilization was. The sites of the civilization were located near the shoreline of an ancient northern ocean. The civilization was wiped out by planetary catastrophe and consequent Mars system climate collapse. Now, based on the new images since Viking, it's been confirmed. Sidonian hypothesis, despite erosion of the objects, is confirmed by the new images. We see symmetric details, nostrils in the nose of the Cydonia face, which is the larger face, possible collapsed brickwork found on the pyramid. So friends, we're staring at a dead civilization on Mars. It is my opinion. So now, why did Mars die? Mars was like Earth for a long period. It survived apparently several traumatic events relative to impacts from the nearby asteroid belt, but still managed to have life and civilization occurring there, leading to a primitive humanoid civilization. At least it looks primitive. We don't know what its real technological level was. And by the way, this civilization apparently perished 180 million years ago, long, long time. That was before even the dinosaurs were on Earth. So I don't think there's any connection between the Mars civilization and Earth civilization, except maybe through the collective unconscious, Jungian's collective unconscious or something. For unknown reasons, Mars apparently was attacked by thermonuclear weapons from space. These were massive nuclear weapons as big as the Empire State Building. They were dropped from space. They went off as airbursts because that causes maximum shockwave damage to small structures on Earth. The only reason you use a nuclear weapon with a ground burst is if you're trying to destroy underground structures, but they were apparently aiming for the above ground structures that would be susceptible to a magnified shock wave from an airburst. The attack destroyed Mars' biosphere. Not only did it kill the civilization, it killed all of Mars and left so much radiation that Mars would never recover as a biosphere. There's probably a tattered remnant of bacterial life on Mars. There are many signs of that, which I won't go into here. But friends, therefore you are not alone in the universe. And not only that, you didn't have to go very far to find a humanoid civilization. You go out to the next planet, next Earth-like planet, and apparently there are remnants of one. And there's also remnants of a horrific tragedy. What does this all mean? Well, it means you aren't in Kansas anymore. In fact, you come to realize that Kansas was stuck right in the middle of Oz, a small island of the familiar in a sea of strangeness. You're not in Kansas anymore. You're actually in a dive bar in Mos Eisley Spaceport. But as Obi-Wan Kenobi said, but watch your step. This place can get a bit rough. The real location of Kansas is shown here on this simulated map of our galaxy. The rest of the universe is like Earth. If you want to know what intelligent life in the universe acts like, turn on the news, particularly now. The government has known this since 1976, apparently, and has faced up to it. You will too. So the hypothesis, a dead civilization on Mars has been discovered and kept a secret by the government. In 1976, we're in the middle of the Cold War. I understand why they would do that. It was a bad shock. It would have been a bad shock. The civilization was humanoid. It was destroyed by a nuclear attack. The same thing could happen to us. Technological level of civilization appears low, but is unknown. This discovery is of great strategic importance. The nation that is the first to explore those ruins will establish itself as the supreme space power. Access to the ruins is the hidden driver of the American Mars effort and the effort of other nations now. Data released to build public interest in Mars without confirming anything. Now, this is what I believe the future will look like. Hey, I grew up on Star Trek. I would not have any problem living in the Star Trek universe. Mars tells us that universe is like Earth, both good and bad, just like on Star Trek. Not only did you have the Vulcans and the Andorians and the other members of the Federation, but you had the Klingons and the Romulans. The future of human space exploration is bright. If we are diligent and persistent, whoever did what they did hypothetically on Mars is long gone. However, the same thing could happen to us, particularly if NASA keeps beaming messages out into Mars, out into space, saying the welcome mat is out, all ETs come here and visit. A dead civilization on Mars and its demise may be disturbing to humanity, but for us in the space community, particularly the ones who know we're not alone in the universe, this is good for business. And I say that in the sense that we will be seen as the frontier trailblazers, which is always nice. Humanity is part of a living cosmos, and we must boldly go forth and find our destiny in it. And don't worry, the force will be with us. Got to be an optimist. This is Kepler Aerospace's view of the future. We hope to be establishing moon bases 20 years from now, or maybe even sooner. Thank you very much. And now yield the floor back to our moderator.
Well, John, let me do this. Okay, yeah, stop your screen share, and I want to put this thing on gallery view. Everyone, please give an enormous applause for Dr. John Brandenburg. John, thank you so much. Thank you for your patience.
It's a great honor to be addressing you all.
Thank you for your patience with the technical issues. Thank you to everybody in the audience too. Here, I'm going to put this thing back on speaker view. So yeah, I mean, if you're up for it, let's go into Q&A session then.
Yes.
Yeah. And again, John, thank you so much. I know Zoom, the folks in the audience.
I'm sorry. I ended up in a quarrel with some people in the company who said they just, so I finally got to negotiate it down a non-disclaimer disclaimer.
That's okay. You know, what I wanted to let the audience know was I was on the phone with you actually while Bob was wrapping up the Q&A, and it forced you to do like a last minute upgrade on Zoom. So
yes, unfortunately.
Yeah, so that's kind of why we ran into these.
It's okay. No, it's great. I work for a great company. They're very supportive of this, but not everybody in the company is completely on board with this, and I understand that.
Yeah. Well, so let me go to Morgan first for questions. Morgan?
Yes, Morgan.
Yeah. Okay. Can you hear me? Okay. Sorry.
Yeah. Yeah.
Okay. So first question. Also, thanks for this presentation. This has always been a very interesting subject. This Martian business has been really interesting because it's kind of hard data.
Yes, it is. It's all NASA data. It's not some farmer out in his cornfield taking a picture of lights in the sky.
Where does the dates, the 180 million years ago, where does that date come from?
Oh, those are radiometrically dated rocks. Any rock you can use what's called potassium argon method, etc. Various other methods there are certain elements in the universe that decay very slowly that are in the rocks, and you can find how much you can estimate how much was formed initially in the rocks and then see its daughter products and estimate the age from those ratios. So they come up with 180 million years ago is when these rocks were molten lava. Now, this has caused a lot of trouble in the Mars community because almost all of the Mars meteorites are about that same age. They only have one very ancient meteorite at about 4.2 billion years old. That's ALH 8401. That was the Mars life rock. And now they've been waiting to get more meteorites of intermediate age, but it's been very hard. Mars is kind of bimodal. It's either very old or very young.
But all of them are going to come from the same. So even like if I guess I don't know this one that's in Antarctica, but whatever meteorites we pick up that are from Mars are 180 million years old, and then also.
Well, most of them are. Some of them are about 1 billion years old, so that's helpful.
Okay.
By the way, they also show the oldest meteorite from Mars doesn't show that it absorbed Xenon 129, meaning this Xenon 129 abundance was something that happened late in Mars history, not early.
Yeah. Oh, wait, late. What do you mean? Like as in greater than 180 million years ago? What do you mean by late by that? For the Xenon?
Oh, yeah, about 180 million years ago. I say that because that's when some of the rocks that have been exposed to intense neutron bombardment, like from a nuclear explosion, they're 180 million years old.
That's it. So you have, I mean, does this come from multiple sources then in the sense of?
Oh, yes. Please, I encourage you guys.
So everything's pointing at the 180.
Yeah, you can, there's called, one of them is called the Mars age paradox. And the fact is, we look at Mars and half of it looks like it's very old.
Yeah.
And half of it looks like it's very young. And then, so we seem to be getting meteorites almost exclusively from the young part of Mars. It's very odd.
Well, or go ahead, Tim. Sorry to cut you off.
Oh, sorry. Yeah, actually, I had a question, but go for it.
Okay. Well, I just wanted one quick follow up. In terms of these rapid processes, which could create these excesses, you had mentioned a solar source. So it's either nuclear or solar. And so what I wanted to ask is, I've always heard something about these like micronovas or something like this, and that on the surface of the moon, you see almost like a glass structure, which could in principle come from these micronova events. Is there any correlation with that what happened on Mars?
Yeah, I must confess, I'm certainly aware that they have evidence from the lunar rocks brought back by Apollo of some kind of solar flare-up at some point, like a micronova. But I haven't heard of anything resembling the neutron creating anything like the neutron bombardment that they see in the Mars rocks. So that's all I know about it. I have not, and it's funny, you don't see much discussion of that interesting event.
Yeah. Well. Okay. Yeah. Thank you.
I think the Romulans and the Klingons had a dispute near the moon.
So
I think that's what that's what that is all about.
If it's okay, let me jump in. I usually I don't have questions, but I do have a quick one. So on the Mars 2020 Perseverance mission, right? The Perseverance rover, the new one that just landed, it has something. Yeah, it has something called RIMFAX on it, which is, let me see, radar imager for Mars subsurface experiment. John,
Yes.
do you have any thoughts about whether they may detect like some kind of artificial structures with that, or?
Well, if they have kept those cards close to the chest. We noticed that the Mars rovers and landers all tended to avoid Cydonia Mensa and Galaxis Chaos. They landed as far away from there as possible. They still seem to find some odd things on the surface, suggesting a past civilization. But I've just concentrated on the orbiting, the pictures taken from the orbiters. Yeah, there's another probe they sent to Mars. I think it was Intrepid or something. They launched it from Edwards Air Force Base. Now, to somebody who's worked in the space business with the Defense Department for a long time, what that means is it had a classified payload. So they sent a classified payload to Mars. We don't know what was in it, but I think they were testing the soil for various telltale isotopes to see if my hypothesis was correct. And as near as I can tell, we're still going to Mars. So I think they've absorbed that data, and we're going to Mars.
Yeah.
Why are we going to Mars exactly, says the public to the government? For science. No, it's about survival.
Well, John,
Yes.
let me thank you. Let me go to Bob Greenyer next. Sir?
Okay, yes, Bob. Another plasma guy.
Oh, and Bob, you're muted. There we go.
Yes, Bob.
Oh,
How can we help you?
I think Bob. No, he's still there.
Yeah,
he's
but
still,
we
he's
can't
still
hear
muted.
him.
Asked to unmute.
He's talking with his hands. I'm using sign language.
There. Allow participants to unmute themselves.
Thank you.
My apologies. I don't know how that got checked. Okay.
John, thanks for an excellent presentation. And it's
Thank
nice.
you very much.
It's very nice to see some updated images of those faces on Mars. I wasn't aware of
yeah,
those.
yeah. They keep telling you, oh, they showed nothing. Move along here, folks. There's nothing here to see. And if you look at the actual pictures, it confirms everything.
Yeah, yeah. So I'm sure everyone who's thought about this long enough will conclude that there's a probability of one of there being life on other planets in some place in the rest of the universe.
The question is, how far would you have to go to find it? And apparently we didn't even have to
I think the
go
more
right.
important question is how much time would it take to get there?
Yeah.
Well, and the panspermia hypothesis, right? I mean, planet seeding and all that.
Without going off on a tangent,
yeah, that's a tangent.
DNA is able to transmit. Can it transmit torsion waves through Relic Neutrinos? If it can, then if it can receive, then you don't need to go anywhere to have DNA transmitted. And so you can look at the work of Luc
Life
Montagnier.
will find a way.
Well, and if you look at the work of Luc Montagnier, he was able to record the electromagnetic emissions from the AIDS virus, send that to a lab elsewhere, and use a PCR reactor to reconstruct the virus using the electromagnetic information. So you don't need to send the DNA, you just send the wave function. Okay, so that wasn't my question, but it's an interesting aside. So I had the pleasure of hosting, I think he's a Bulgarian, Stoyan Sarg, in 2014. he wrote this Basic Structures of Matter, Supergravitational Unified Theory. He also wrote a field propulsion book and is one of the few people to have replicated John Hutchison, at least inadvertently. Anyway, I think it was in about 2016, he sent out an impassioned warning because he's an atmospheric scientist. That was his expertise, and he's taught for many years as a professor at University of Toronto. And he calculated that if you had 2 nuclear explosions simultaneously anywhere on Earth, that would produce a self-sustaining vortex pair, and that would strip the atmosphere within a number of hours, which would boil off the oceans, and you'd basically be able to kill a planet with 2 simultaneous explosions near instantaneously.
What you're telling me is a global nuclear war would be a bad idea.
Just 2 nuclear weapons going off at the same time of sufficient size would set up this self-sustaining vortex. He'd done the maths. And it's very interesting because he then in this talk with a colleague, he said, I believe this is what happened to Mars and how it died.
Oh,
and,
interesting. Well,
and so this is the first time that I've heard anyone else talking about nuclear events on Mars. And it's also very important because you identified 2 locations. Now, I don't know whether he read your work and did the maths and realized that this is exactly what would happen. But it may have just been 2 warring parties, and they launched a bomb at each other, and they didn't realize they were going to strip the planet of the atmosphere.
I said, the civilization looks like it was roughly Bronze Age, Old Kingdom, Egypt, Mayan, Aztec. But we don't know. We don't know what this level of technology was. We have to have boots on the ground. Any archaeologist would tell you, by the way, JPL could send one of its rovers and drive around Cydonia Mensa for a year and not see anything. You got to dig.
Well, I can tell you from my own experience, if you don't look, you don't find, and you have to look in the right way, and you have to look in different ways.
And by the way, my experience also is that skeptics hardly ever discover anything.
They already know it doesn't exist, so why should they bother wasting their time?
Looking for something,
Yeah, so thank you. This is really interesting, and I think I'm going to reach out to Stoyan and point him to your presentation here. I think it's really a meshing of it's a very serious message.
It is
of this little blue bubble we live in, and how fragile it is. So thank you for alerting me to your understanding.
Avoid nuclear wars.
Just avoid 2 bombs going off at the same time.
Just involve nuclear bombs going off at the same time.
And Bob, I am working on setting up an interview with Stoyan, so I'm going to email you and pester you for questions I should ask him. So
fantastic, great.
Yeah. Well, thank you. Here, let me go to Michael Boyd next, sir.
Yes, Michael.
Okay, can you hear me okay?
Sure can. Loud and clear.
So I have a question about some features that I observed in crustal features, what appear to be magnetic domains. I have a request, Tim. I'd like to share screen, but not on this, but my other computer that's showing my acoustic levitator.
Yeah, go for it. Yeah,
okay.
Thank you, by the way, Michael. I have received my acoustic levitator that you got me. I'm going to start some experiments soon.
All right.
Cool.
Do some levitation.
Let's see here.
I naturally like to do electromagnetic fields, but you can do it with sound waves. That's great.
Okay, can you see that? Oh, wait, it hasn't showed up yet. Let's see. Should be showing up.
You can levitate water with those, right? Ah, there we go.
Oh, okay. That's very interesting. Yes.
Okay, so hold on. I got to reduce that down. And so now I'm showing you this, and you can all see that they're in the southern hemisphere. There's these interesting magnetic domains showing up. Now, what I want to do is I'm going to unshare and then I'm going to share a different screen. Where is it? This one. Now, do you see that?
Yeah.
So what we're looking at here is an image made with a thing called a magnetic force microscope. And what it's looking at is a written track on the surface of a magnetic recording disk, like in your hard drive. Okay, and this is what popped up in my mind. And now, so what I want to do is I'm going to show you that again. I'm going to change. Now, do you see? I have that. Can
yes.
You see how that's like? So now
Mars is a very interesting place.
The Earth has a dynamo type magnetic. It's kind of like a motor, and that's what produces our magnetic field, which is a shield, a magnetic shield of the Earth.
Yes.
So, like during if the Earth got hit, was in direct line of sight of a solar flare, for example, the atmosphere would prevent it's from getting exposed to X-rays essentially, and we're still subject to coronal mass ejections, which are basically proton flux.
Yes.
Now, the Mars, for example, if its atmosphere was CO2, like CO2 isn't a lot of our atmosphere, it would definitely, for one, it wouldn't shield the planet like ours does from the X-rays. And so the other thing I'm thinking is it possible that it was a coronal mass ejection event?
Could have been.
Something natural caused this.
I have not looked in that.
That's one hypothesis. And then
I would naturally,
by the way, that it was interplanetary nuclear war, and what we see today as Mars is a result of that interplanetary nuclear war. And what we call the asteroid belt is the other side.
The side that lost.
The side that lost. So, taking what I would call the non-binary view versus the binary view.
Well, because in my university astronomy class, they teach that one half of Mars is covered with craters, and then the other half is like where Cydonia and whatnot lies. And then I've often wondered, is the asteroid belt, because it doesn't fit into these like modeling scenarios of how solar systems created, could it have been a bigger solid fourth planet that Mars was a super moon to of, and then many planets that are also in the asteroid belt would have been also these moons of this possible larger planet? Is that a possibility?
Well, so my concern is the isotope analysis that you're talking about is if you could produce that isotope naturally without nuclear war. For example, you mentioned a supernova event.
Well,
correct?
Both thorium and radioactive potassium can be produced.
So in a supernova, isn't essentially what's going on in a coronal mass ejection the same process?
Well, the solar, you find almost no thorium being ejected from the sun or potassium. It's all mostly hydrogen.
I think, I mean, John, if I could jump in, I think what Michael is asking is if something like CMEs might be causing this as a reaction. But Michael, I guess something to consider would be, all planets are exposed to these, right? And so we would probably see all of this on the moon if it was caused by events in the sun.
Right. This is something unique signature on Mars in its crust. It's like it used to have a core, and the core is no longer where it's supposed to be.
Well, Mars,
And what-
remember,
and what-
Mars is 1/8 the mass of the Earth. So if it had a hot core, it lost its radioactive decay heat much earlier than Earth did. But
well, it's a unique
life is very
feature.
adaptable. I think that Mars probably was a good place to live in any case.
Right. So
But
I'm just curious
I don't know.
if you would look into this anomaly in the southern hemisphere with these magnetic domains showing up in the crust.
Well, it looks like there was this, you have a remnant of a south magnetic pole on Mars from this earlier period of intense magnetic field. But yeah, I haven't looked at the magnetic data simply because I didn't think it would, like I said, I originally thought this was due to underground natural nuclear reactors. So I basically followed the big explosion hypothesis on Mars.
So I'm gonna
Mars surface.
Just for the FYI, thanks for your answer. I appreciate it.
Okay,
But I'm gonna put in the chat a link to the Wikipedia site where the link to that image, so you can have the source of it. Okay.
Sure.
Okay. Thank you again. I appreciate your answer.
Well,
Michael, thank you. Let me move along to Charles. Charles, go for it, sir.
So in a few years, Elon Musk wants to send starships to Mars. I was wondering what dangers will the first humans have, and what we should do to terraform Mars before we go.
I wrote a book called Death on Mars, and I discussed this. I think the dangers for the first Mars
No,
crew
sir,
will-
I'm sorry to interrupt, but for somebody that has such power, you're so negative in the future idea of, humanity reaching out there. I'm sorry, please let me speak. Like everybody, like somebody tells you like futuristic, you go history. Like,
Okay,
future,
Lulu, I'm sorry, I have to mute you. Okay, I'm sorry. Can you go ahead, John?
I'm sorry. Where were we? We were
sorry. You were talking about you wrote a book.
The dangers, the dangers to the first people who land on Mars. If they're landing at Cydonia Mensa, where I believe they should, and looking around and digging into the rubble to find, some kind of artifacts. They'll experience what a lot of people experience when they go to the site of a massacre. That's my belief. And the psychological toll that takes is tremendous. This is why I recommended in my book that we establish basically a base camp on Phobos first to kind of give psychological support to whatever ground team is on the ground, that they can look up and see Phobos orbiting overhead. And it's kind of their link to Earth, link to humanity. The first people who excavated Pompeii, where there was a volcano that swallowed up an entire city of, there was Mount Vesuvius. One of the last comments by, I think it was Louis Stevenson, was "City of the Dead, City of the Dead." And he wrote that shortly before he died. Apparently the stress of finding all of these dead bodies and ruined architecture it took its toll on him. He was just an English Victorian gentleman. He just wasn't used to this sort of thing. And so I recommended that we send some pretty, I recommended we spend combat veterans, who are in the special forces, would be the first part of the special landing team, people who have demonstrated great psychological toughness.
Okay, interesting. Thank you.
It'll be tough on the entire human race. to discover that when this, if I'm correct and this is all confirmed, it'll be very tough on the human race as a whole. There'll be a lot of sleepless nights on Earth.
Awesome. Okay. Well, let me go to Jared next. Jared, go for it.
Yes, Jared.
Hey, John. Excellent talk. Really loved it.
Thank you.
I hope you'll stick around. My talk is going to have some plasma physics stuff and maybe some LA&L relationships.
Oh, great. Some plasma physics, of course.
Yeah, I think you could provide some excellent insights on, if you would. My question, though, is in the maps where you were showing the radioactive locations,
yes,
it looked like there was an area or two on those where there was the opposite. There was concentrations, negative concentrations, right? It was totally lacking in any of these isotopes. I was wondering if you could provide any explanations on that.
The global surveys of the abundance of radioactive potassium and thorium on Mars show that the surface is very much depleted. I mean, the surface has a hyperabundance of thorium and radioactive potassium relative to the Mars meteorites, which are supposedly parts of Mars, presumably from a few meters down in the surface, where they can be ejected into space by a larger impact. So it's all very peculiar. It's very, I guess I don't have enough information right now to really comment on what that could mean. It looks like there were just two sites of tremendous activity on Mars, followed by an antipodal deposit for both. And that's about all I can figure out from those pictures. But Jared, you've raised a very good question. I don't know how to answer it, unfortunately.
So not like they were mining all of the materials from that location only to then later explode those materials.
Yeah, there's no evidence for any cratering or excavation or anything at either of those sites. It's just smooth as, it's part of the very smoothest and uncratered part of Mars. So, like by the way, there's a strange black triangle hovering over your shoulder. Yes, thank you.
That's his,
by the way,
his unique Zoom background.
As anyone who's followed in depth the UFO question, parts of it read like a science fiction horror movie now, with animal mutilations and abductions and occasional military clashes. This is what we found on Mars is quite consistent with that, what we're experiencing in the UFO field, I believe. That the universe is a mixture of good and bad. Don't expect it to all be warm and cuddly. Some of it is warm and cuddly, but some of it also can be quite unpleasant.
Yeah.
That's what I think.
Well, thank you, Jared. Let me go to Bruce Cornett next.
Yes, Bruce.
Oh, Bruce, your mic is
We're
really
not hearing
faint.
you very well, Bruce. Turn up your volume.
Can you turn your volume? Yeah.
Oh yeah, it was way low. Can you hear me now?
Much better.
Yeah, I can
much
hear
better.
you now. Very good, Bruce.
Okay, my background in college was studying the Triassic Jurassic rocks of the Newark supergroup, age dating them by palynology, and I collected thousands of samples. I processed thousands of samples in the chemical lab to extract the pollen. But what I discovered during that period was that there was a mass extinction at the Triassic-Jurassic boundary that hadn't been known before. And why I'm talking about this is your 180 year date for basalt on Mars. Well, the basalts of the camp, the Central Atlantic magmatic province, that with the opening up of the Atlantic Ocean that occurred at that time, the age dates for there run from approximately 205 to 180 million years ago.
Was this the Great Permian? Was this the Great Permian extinction?
No, it's the Great End Triassic extinction.
Oh, okay. Well, yeah, we've lost track of our mass extinction events. There've been
Right,
so
or at
many.
least 6 of them in the history. And
Earth is rather accident prone itself, apparently.
what is important for your consideration is that the age date has been narrowed down by dozens and dozens of researchers who've analyzed the basalts, and they have concluded that the event happened at 201 million years ago. Now that's awfully close to 180.
Yeah, it is.
Secondly, in my first fossil digs in Massachusetts, discovered a fish bed that was at the Triassic-Jurassic boundary. And what was usual about it is all the fish are highly radioactive. And when I analyzed those fishes in my chemical laboratory in my parents' basement, I came up with radioactive cesium.
Cesium. Well, that's a fission product. Cesium-132 is a well-known strontium-90, cesium-132 is the kind of the pair of. So,
what is that doing at the Triassic-Jurassic boundary? On top of that,
it suggests that the history of Earth is complicated.
Yes. And the dinosaurs took off after that.
Complexities.
Dinosaur tracks increased by at least 50% right after that boundary.
Well, the dinosaurs obviously benefited from this.
Yes. And so did the plants that fed them, which became the dominant type of vegetation on Earth. So.
Oh, yeah. Well, the biosphere recovered even from this. And
I'm wondering if there could be anything connecting this extinction on Earth with the one on Mars.
Well, unfortunately, we're dealing with a lot of unknowns here. We have evidence for the civilization on Mars. It looks as though it was primitive, but we don't know its technological level. We certainly, if somebody came from outer space, from another star system, and decided to make an example out of Mars, kind of a pyramid of heads like the Mongols would do, it looks as though they decided to go hit Earth too then, even though there was no civilization there.
Could the blast on Mars have been so energetic that it hit Earth on one side? Because the opposite side.
Well, it's certainly possible, but it sounds to me as though they had a few bombs left over and they decided to just nuke Earth just to be on the safe side.
A recent development by paleontologists in China showed that China at this Triassic-Jurassic boundary showed no significant extinctions at all on the opposite side of the Earth. But on the Atlantic side, you had all of these animals and plants being wiped out.
That's very strange. Yeah, well, like I said, Kansas is stuck in the middle of Oz, actually. It's just, it's the island of the familiar in a sea of strangeness.
Yes, the Oz effect.
The Oz effect. So thank you very much for pointing that out. I was certainly not aware of that. Has anyone else noticed that and put it in the literature? By the way,
well, all of this is in the literature.
I can tell you that a lot of scientists, if they find something really weird, they just don't publish it.
Well, I published a paper on this radioactive fish layer at Triassic boundary on ResearchGate. I'll send you a link to it, and you can.
Thank you very much.
Okay.
Yes, Bruce.
Yes. I'm still here. Are you still hearing me?
Yeah. I'm still hearing you.
Well, anyway, I'll send those.
The story of Earth is apparently much more complicated than anyone guessed. Numerous extinction level events. One of them may even be recorded in the Bible and a lot of other mythologies is the Great Flood. Apparently with some catastrophic climate catastrophe, well, and you think what could cause that? Well, if somebody dropped, well, anyway, let's just put it this way. Once Earth is part of a living cosmos, even before that predates humanity, of course it predates humanity, then everything becomes really complicated. And, but we have to go out and engage the universe as it is. We can't wait for it to come to us, and we have to go out and meet it halfway.
I thank you very much for your talk today with all your slides. It clarified a number of points that I had questions about concerning the isotope and the ages.
Yeah, well, in particular, I did a thorough search of the literature to see if anyone had any explanation for the Xenon 129, which when I showed the Mars isotopes to nuclear weapons experts, none of who can be quoted, they all agreed that this was signs of a nuclear attack. They didn't explain why. They just said, yes, it's obvious. But I guess since the mainstream science community has no explanation for why the Xenon 129 would appear absent the Xenon 132 from longer-lived decay longer-lived isotopes decaying, that convinced me that, okay, this is a real problem, a real anomaly, and we have to look for another explanation, which the nuclear explosion offered.
One other point that I would like to make, if I may, I worked with Richard Hoagland back in the early 90s and saw all
very good, very good.
So I'm following up on
brilliant man. He made the face on Mars as familiar as George Washington on the dollar bill.
He sure did. And one of the things that I discovered is that it was through an image of the DNM pyramid that Michael Hanlon published for Mars, in the real Mars. And when I looked at that picture, he was presenting it as proof that the DNM pyramid was a natural formation. And as a geologist, I looked at that and I just freaked out. That's probably why I'm going bald.
Find me someplace on Earth where you have a pyramid-shaped mountain like that.
Exactly. But I saw clear evidence of mass wasting, collapse, the underlying sediments being squeezed out from underneath the weight of the pyramid, and one of the ridges on it sliding down the side and creating an arc of deformation around the side of the pyramid. And
I'd like to see those pictures. If you have them, you could send them to me.
I have a web page out already on it, so I'll send you that.
Good.
One. And
Please
basically,
post everything in the comments because I absolutely am loving all of this, guys. Amazing, amazing work.
Yeah, Bruce, if you could paste that in comments. Yeah.
My the stuff. Okay, here. Let me go. Find. Oh my God.
Yeah, and if it's okay, Bruce, I'd like to move on to Harold also because we're starting to push up against our time.
I'll just go to
right.
Chat.
Okay,
Right,
Bruce, thank you again, sir.
Thank you.
Okay, Harold, go for it, sir.
Oh, amazing presentation. Thank you. My
Thank you very
question
much.
to you, with all your research, I mean, obviously you have spent a lot of time studying Mars. My question for you is this: is there any analogy? What benefit would be going to Mars? Like when Kennedy made the moonshot, we benefited with all the great technology, everything that was developed. Now, if you had to give a speech on the great moonshot going to Mars, the same as Kennedy made the moonshot, what would it be like? What would be the justification? What would benefit would be going to Mars and establishing scholarship? What would it be like? Can you make a small speech right now?
I would say that based on what has been found, what the evidence on Mars of this horrific tragedy, that we are going to Mars to investigate as thoroughly as possible using people, human beings, digging through the ruins in order to increase the probability of our own survival. Our survival as a species depends on us now understanding our place in the universe and improving it. Right now we are, a young, rather primitive species, and we have to get better. We have to become like the Federation in Star Trek.
Well,
that's my belief.
I agree with that.
That will increase the probability of our surviving.
That's a good argument, and I agree with that. But let's say that we decide NASA or whatever decide to go to Mars. What kind of benefit in terms of technology and knowledge to humanity would be taking that trip? What do you think would be like? Would it be something like in a Star Trek?
It will lead to an explosion of all kinds of technology, from information technology to propulsion, power technologies. Everything will explode due to this, as it did when Columbus discovered the New World. It led to a revolution in Europe and in thinking about the universe. And the naval, the merchant marine targeting instead of the Mediterranean to target the Atlantic as a place to travel, and all of the things, because the Atlantic is a much stormier ocean than the Mediterranean. It led to just an explosion of thinking and technologies in Europe when Columbus made his discoveries.
Oh, actually, now you've been good. I hope many are listening to you.
And this is empowered by the Queen of Spain, Her Majesty Isabella.
Okay, well, so let me do this. I'm going to go to Thomas Anderson really quick. We're going to try and squeeze through here. So Harold, thank you. Let me go to Thomas.
Hello.
You guys went too fast, man. I had just stepped out of the room.
Oh dear.
Yeah, so we're almost out of time. What was your question, Thomas?
Okay. Well, the first thing I wanted to comment on was the Federation thing. That's why I've been working on replicator technology, because I don't think if we move forward toward transportation technology and weapons technology, that we can move forward, with fearlessness. Instead, we'll move forward in fear, with the most basic fear of, going without. So instead of ending up with a federation, we end up with an empire. Top-down approach.
I'm half Viking, so fearlessness is a state of mind. It doesn't have necessarily anything to do with reality. It's a determination that you're going to go make your way.
Right. Well, like I said, though, if you have no fear of doing without, you have plenty of resources to work with, because there's always more to be gotten. and we begin, basically we hoard the one thing that we can't make more of, which is
Oh,
room, right? Get rid of all the
we have to
clutter.
learn from the mistakes of our own history.
Right. Oh yeah. Right. What, and not just
not
our
repeat
history,
them.
but the history of like all evolution. I mean, squirrels gather nuts and they end up with nuts that rot because they're afraid of going without for the winter. And it's just an instinctual thing. So, you know, to break
Well,
free
even
of that.
rotten nut is better than no nut at all, don't you think?
Right.
You're a
And,
squirrel?
and in that environment, that's, you know, that's what enabled all of the species to eventually culminate in what we are now, right? If you go by evolution. So develop the technology to manufacture and compact it so that you have it on your desktop. You want to try out a design for a warp drive? You can use that device to build a bigger device and then print those parts out and try it yourself and not be limited with, oh, do I have the money? Do I have the manpower? Can I do this? Can I do that? You know, no, you just go ahead and try it. Open source everything. Now, this is just what I'm seeing for the future.
Oh yeah, no, you're talking about creating an environment where innovation and experimentation will be encouraged rather than discouraged.
Right, and almost unlimited, because the technology I'm working on isn't just a replicator; it's a refining and energy harvesting technology.
Thomas, we're almost out of time.
Right.
So.
Well, let me get to the question. The stuff that you found there, could that stuff and those aspects of Mars not be caused just as easily by a massive amount of like mining, like strip mining and whatnot, and preparing to move because the planet is about to become uninhabitable, where they, you know, moved, say, from Mars to Earth and just strip all that away.
There's no evidence that the hot spots of thorium and potassium I mean, they were under a kilometer of water when apparently this thing happened.
So the amount of time
no
that
evidence
since
for
that,
any mining there or anything. It's smooth.
right? Okay. Well, I'm just looking at the size of the planet and the massive amount of oxidation, but yet there's almost no oxygen. It's almost all carbon dioxide that's left behind.
Well, Mars is red because it's highly oxidized. You look at pictures of Earth, of the Sahara Desert, it's red too, for the same reason.
Right.
Okay.
Yeah, that's why oxygen's the second or third most abundant element. It's locked up, though.
Sagan pointed out that meant Mars used to have photosynthesis and then quietly backed off that opinion.
Well, yeah, we found oxygen on signatures on other planets, and they realized, wait a minute, carbon dioxide can be broken apart by UV rays from, you know, the stellar body too. So you can't really count on plant life being, or what we consider plant life here, to be the contributor. There might be something else.
Well, what you get is carbon monoxide then.
Okay.
Right.
Well, yeah. So
anyway, yes.
Yeah. I should apologize for having to cut it short. We're at the top of the hour, and actually we have another presenter. So what I want to do is I'm going to mute everybody out here. So again, I want to put this thing back on gallery view, and everyone, please give Dr. John Brandenburg another applause, an enormous applause. Sir, thank you so much. Thank you so much. Okay, so what I want to do now is our next presenter. This is a little bit different for us, and that's why I'm so excited. But let me do an intro first here. Okay, and I'm going to put this back on speaker view. So we have tech entrepreneur Rupert Wade. He's actually he's also into high frequency gravitational waves. I've been bugging him to present on that, but today he's going to be discussing strategies that inventors can use to fund their ideas. Now, he's an experienced engineer, strategist, and entrepreneur with a passion for big ideas and the drive to see them through. He's the founder of applaud.cc. He also holds a BA in electrical engineering, and he has some experience in nuclear power systems. So, I'm really excited to have him with us because he's done kind of the business side of things. And this is something that he's talked with me a bit about, different strategies that inventors can use, innovators can use to find funding. So without any further ado, Rupert, welcome, sir.
Hey, how's it going, everyone? How are you?
Welcome. And let me hand things over to you, and thank you again for presenting.
Yeah, no problem. It is a tough act to follow. Let me say that when we're talking about potential prehistoric life on Mars, and then we switch gears into startup funding for entrepreneurs on a Saturday afternoon. So challenge accepted, but I will try to make this super engaging for you guys. And also, if you have any questions, just feel free to just chime in. Let me share my screen right now. Okay. Can you all see my screen?
Yeah. No, it looks great. Looks great.
Okay, so you see the first slide.
Yeah, it's the TLDR startup funding for inventors.
Yes, awesome. Yep. So the point of the TLDR, with the Plod, what we do, period, on a high level, what we do is take complex information and synthesize it down into a way that's easy to understand. We do that for life skills workshops. We do that for a number of workshops that we work with other companies, enterprise clients. And so this is a 7-week presentation that we give to students that's condensed down into a 1-hour presentation, hence the TLDR. Okay, so just to give you guys a rough outline of what we cover, I'll give you an intro, talk a little bit about my background and how, from electrical engineering to education to, alternate propulsion, how did I get here? We'll talk a little bit about traditional funding strategies. We'll define what deep tech is. Just to poll the room, is everyone familiar with deep tech by any chance? Okay, all right. So, and then we'll also talk about some challenges and strategies that deep tech entrepreneurs can work through in order to make their ideas come to fruition. All right, let's get started. Okay, so my background, oddly enough, right out of high school, I went straight from high school into investment banking. I wanted to be a doctor. But then my first internship right out of high school, I realized that there were some individuals that are making the salary of a doctor per month. So I jumped on it. The only thing I had to do was take a 6-hour test. And I worked in specifically venture financing, venture capital, where you saw where companies came in, super passionate inventors, really, really interesting teams. They come in with these super cool ideas. And, I got to see from the other side and see what goes into actually funding an idea. What do investors look for, right? Because having the idea is one thing, but actually making it into a product that can be marketed and sold, that's a whole different story because you've got to go through, production, right? Okay. From investment banking, I didn't choose the best time. I worked in finance from 2006 to 2009. If y'all remember, something happened around that time. It was like the Great Recession, right? So not the best time to be in finance. However, I learned a lot and I got a tremendous amount of experience. From there, I switched gears and actually went to college after that for electrical engineering. From there, I was a nuclear systems engineer for electrical distribution at 9 Mile Point nuclear station in Oswego, New York. And then I moved to electrical distribution in New York City, into engineering consulting. I did a stint in restaurants during COVID. And now my most recent company, I'm in education technology where, our goal is to really teach 1 billion people life skills and quantify it and objectively certify it for the masses. But how did I get here, right? In 2005, I fell down the UFO rabbit hole hard, right? Went down there, got lost and came out the other side. And what I realized was that there was still a tremendous amount of information available for alternate propulsion, right? There's still a tremendous amount of things to learn and to discover in this field. The field is super nascent. And there's like, what you guys are doing every single Saturday, right? You're, completely dedicated engineers, working through in these ideas that may not be mainstream, but that's how, massive movements start, right? They start small, they start in a garage, and they start, things like this. Okay, so we will go into, I'll just give you guys a quick overview. It's a short video on traditional startup funding. That will give you a much better description than I could ever do, and it's animated, so I think you guys will really like it. And it's about as simple as I could probably get it, just so that it's still not, so it stays interesting and it's not boring for you guys. All right, let me see. Can you guys hear that? Can you hear the video? Tim, can you hear it?
Sorry about that. No, actually, I can't. If I remember right, there's a thing with Zoom where you actually have to install a plug-in to play sound. I'm not sure if you have done that or not. Oh yeah, you know, actually, Rupert, you know what? You probably already do if you've played this before. If you want to stop sharing, reshare, and there's a little checkbox that for sound.
Okay. I see. Yep, I see.
Yeah.
All right. Let me
I've been bitten by that one many times myself.
Oh yes. Where is it? Okay, here we go. Share sound right here. Optimize. Okay.
The product, the service. No one has done.
How's that sound? Is it good?
Yeah, that sounds great.
All right, awesome.
It before. Unbelievable. It's so painfully obvious. Can you pull it off? Maybe. You're two friends. You are excited. Design a logo, design a name. All fun and games. Design the concept. Things get serious. You decide to make this a company. You need a structure. A legal structure. How much will that cost you? In the US, incorporating a company will set you back anything between $25 and a few $1,000s. That's in part registration fees, which largely vary depending on where you are, and legal fees, which vary depending on how fancy you need your first shareholders agreement to be. Your incorporation turns out to be on the pricey side. Also, you need to rent a server in order to develop your product. Therefore, you decide to collect some other people's money for it. This early in your venture, who on earth would give you their money? You will get it from family, friends, or by crowdsourcing it. Usually, a newly incorporated company issues 100,000 shares, which are equal pieces of ownership. You need to decide who will get how many of those. You agree on 40,000 shares, or 40% of the company, for each founder, and 20,000 shares, or 20% of the company, for a well-off family friend who buys them for $50,000. It's called an investment, and at such an early stage in your startup, it's called a seed investment. The money he pays now belongs to the company. If the company fails in the near future, which statistically speaking is the most likely scenario, you will probably never see a dime of it again. $50,000 for 20% of the company puts the value of your enterprise at $250,000, which puts the value of your 40% at $100,000. Not bad. Please sign here, here, and here. Congratulations, you incorporated your company and finished your seed round of investment. A year has passed. You're having a successful beta trial with customers. Time to hire a few more people. Rent not just a server, but a small office space. The $50,000 of seed capital only got you so far. Time to collect your first big round of cash. You will do this in a so-called Series A round. You're looking for an investment of $1. This time, you're contacting angel investors and venture capitalists, also called VCs. VCs are people who work for venture capital firms, which raise venture capital funds. They take other people's money, which they then invest into young, risky companies, such as yours. Angel investors are individuals who professionally invest their own money into young companies. Often, they successfully sold their own startup many years ago and are now looking to support early ventures. You contacted a few VCs and angels. Some of them you found online, some you got in touch with via friends and colleagues. You sent them mails. You sent them a business plan. Usually, they don't care much for the business plan. They want to see the team. Is it competent? The idea. Is it special? They know it's not easy. What have you already achieved? Is it promising? What could you achieve? Can you dream big? You set up some Skype calls. A bit of small talk, a lot of business talk. Describe the vision. Easy. You've done it countless times by now. They ask you tough questions. Have you heard of that other startup which does a similar thing? How are you different? You spark interest. You have second calls. You have third calls. You meet them in person. They might invest. Time to talk valuation. There is pre-money valuation and post-money valuation. The pre-money valuation of your startup is how you currently value it. The post-money valuation is the pre-money valuation plus the investment you're looking to collect. This This is usually the one that you reference when you negotiate, because the investment divided by the post-money valuation equals to the investor's share in your startup. Investors want a low post-money valuation to get more for their money. You want a high post-money valuation to keep a larger share. You suggest a post-money valuation of $8 million. For the investor who would put in $1 million, this would mean a 12.5% stake in your company. A few weeks down the road, there are two offers on the table. One VC offers an investment of $1 million for a post-money valuation of $6 million. An angel investor you talk to offers to invest $500,000 for a $5 million post-money valuation. The offer of the venture capitalist sounds like the better deal, but the angel has great connections in the industry. It's called smart money. What do? You decide to go for both. You tell the angel that you have a standing offer of $6 million post-money valuation, but you would really love to have her on board. She agrees to invest at a $6 million post-money valuation. Great. How's the cake split this time? Let's do the math. Together, the VC and the angel will put in a total of $1.5 million into your business for a $6 million post-money valuation. This means that they will own 25% of the company. You, your co-founder, and your family friend used to own 100% together. With the new investors coming on board, you will be diluted. After the Series A investment, your cumulative share will only add up to 75% of the company. This dilution happens proportionally. Does this mean that you have fewer shares now? No. Here's how it works. Just like your company issued the first 100,000 shares when you incorporated it, it will now issue more shares for the new investors to buy. A company can create shares just like a central bank can print money. The total number of shares of the company just changes, while your number of shares remains the same. How many shares does the company issue? If 100,000 shares are now only 75% of the company, it means that 100% of the company will now be equivalent to 133,000 shares. Therefore, the investors receive 33,000 newly issued shares for their investment. Since they pay $1.5 million for their shares, each share is now valued at $45. Your 40,000 shares are now worth over $1.8 million. Congrats. This whole process of a company issuing new shares to receive cash is called a capital raise. If things go well, the Series A won't be the last capital raise of your startup. There will be a Series B, a Series C, a Series D, and so on. For each investment round, the company valuation will hopefully increase. Also, each time your company takes in new cash from investors, you will be further diluted. Remember how I said that your number of shares remains the same though? I lied. Actually, there will usually be stock splits along the way, which convert each single share anyone holds into multiple shares. Hence, your number of shares is doubled or tripled every now and then, along with everyone else's. The purpose of this and many other things that are determined in the term sheet are a story for next time. You don't care much for legal work anyway. Your primary interest is in growing your business, which is now on track to reach new heights. It has been 6 years since you founded your company. You have successfully completed 4 investment rounds since then. You launched your product by now. Guess what? Customers love it. You're a huge success. The big blogs write about you and whatnot. Most importantly, last quarter, your company has not been losing money for the first time. The business made a profit. Time for the exit. Exiting the company is investors' talk for selling their shares. Everyone who invested cash into your business since the beginning has been quietly dreaming about a big profit. The earlier they invested, the bigger of a risk they took, and accordingly, the bigger of a profit they will get if the company really takes off. There are usually 2 ways of exiting a company: selling to one of the big guys or offering it on the stock market. If you sell out to a big company, the investors will usually sell all their shares at once. You and your co-workers, on the other hand, usually won't. Whoever buys you needs you people to stay motivated to run the whole thing. Therefore, your shares will be transformed into shares of the company who bought you and then made available to you over time. This is called vesting your shares. If you leave early or you don't reach some milestones you agreed on, then you won't receive all your shares. The much cooler way to exit is to become big enough so that you will be able to sell your company's shares on the stock market. The process of doing this is called an initial public offering, or in short, IPO.
What's an IPO? What's an IPO? I still don't know what an IPO is.
Don't believe Martin Scorsese. How it works is painfully easy. In essence, an IPO is just another capital raise. Once again, your company will issue new shares, only that the investor who buys them this time is neither an angel nor VC. It's the public. public. The day you go public, your company dumps a bunch of new shares on the stock market. From then on, people can buy and sell them among themselves. Furthermore, you now hold tradable paper, almost as good as cash, the price of which goes up and down every day. You can sell your stock into the stock market at market price anytime, with the exception of IPO lockup periods, which are a topic for another time. You floated the shares at a starting price of $64, and they shot up to over $70 on the first day of trading. Due to stock splits you did along the way, you are now sitting on 10 million shares of your company. Your personal wealth is over $700 million. You could cash in, but do you want that? It feels like yesterday that you two just had a vision. Now, you're 1 in a million. There's a lot you achieved and yet endless things to do. Even though investors call it an exit, for many founders, it's just the beginning.
Okay, clear as mud, right? You guys got all that? All right. So let's go into the next slide here. All right. So basically, what happens here is when you start off with your idea, you are the only founder. You have 100% of your company. As you progressively if you take on a co-founder, your ownership decreases over time, right? After that first initial period where you and another co-founder are there, when you're actually starting to try to raise money, this would be when you have angel investment from a rich uncle, friends that are in tech, that have started business in the past, that are looking to do certain investments. This is where you'd allocate a certain percentage of it. And then you'd also put aside some percentage for what's called an option pool. So all that means is that in the future, when you hire employees, you're gonna set aside stock for them. And as the video showed you guys, as you progressively grow from your seed round to your series A and B, your stock as the founder decreases. The VC stock generally stays the same, and your option pool changes as well until you reach an IPO, and a certain portion of the stock goes to the public, and this is where you see a lot of those valuations happen, right? But that's just a general idea as far as like how startup funding works. But let's talk a little bit more about, what are the alternative sources of funding, right? Because not everyone is going to be able to go down this route, especially if you're trying to do something new in the area of propulsion, right? These things are super expensive and they're super hard to build, and potentially low likelihood of success to a certain degree. Okay. Oops. Okay, so let's talk about the different methods. The number one and best method to fund your business is via customers. Customers do a lot of things, right? The one thing they do is give you validation for the product that you're trying to actually sell. And they also give you money, right? They give you validation money, and they also give you honest feedback as well. The second best thing would be personal capital. This is like how much money you have saved. There are certain founders that use credit cards, loans from a bank, what have you. I think for everyone on this call, I don't think bootstrapping is a viable option. It's very hard to bootstrap, a new type of jet engine. It's very hard to bootstrap, an electric car from scratch, right? You need some general, you don't have those parts laying around. You have to buy the parts. You have to deal with manufacturers to a certain extent. One interesting thing, I think, for everyone on the call, I think one avenue that will be truly beneficial for you guys are looking at grants. There are a number of grants, like from the National Science Foundation. There are a number of other resources where you get free money. This is money that you do not have to pay back because your idea is so cool, right? And so I think those are, and I'll give you guys a list of different resources that you can use, in order to, where you can apply and you can see whether or not these grants actually fit what you're trying to do. The other options, you've got crowdfunding. This is Kickstarter, Indiegogo. Here you have to have, to a certain extent, a product, but it's not necessarily guaranteed, not necessarily written in stone. If you've got a good description of the product, if the product is a good, compelling story, chances are, you can see some success. And there are a few other ones here too that I'll touch on. Pitch competitions. Those are, when generally you'd have your team figured out, you have the rough product that you're trying to build figured out, and then you go around the country, or you apply to these competitions and you actually give a presentation for and compete with other startups for the ability to win a small grant, sometimes $10,000 to $1,500, $200,000, right? Bank loans, we talked about that before. These can be in a number of different ways. We don't have to get into it, but loans are, just like what they think, right? Just like what it sounds like, right? You borrow money from a bank with the expectation to pay it back. There's some different types of loans that you can take from a bank where you can lock in like your company valuation, and those are things that I can provide some resources about as well. Now, last but not least, is crypto. Now, if I was going to do this presentation, I actually did it 6 months ago. I did not include crypto because of the fact that it was just still so new and there weren't really many avenues for funding entrepreneurs, right? Non-scammy avenues, right? Because for the most part, all the ICOs that happened in 2017 through 2020, a lot of those ICOs, ended up crashing and burning, with some exception. But I think crypto offers a really unique opportunity, right? And it's really specific for a marketplace. So like in the chat, I saw that you guys were passing around, sharing links from ResearchGate. ResearchGate is actually one of those companies that is using crypto currently to incentivize the different researchers that submit academic papers. So, one thing, imagine if you had a forum very similar to this one, where, for every upvote that you get, it would be, real currency that each individual that participates in the community could be part of the upside of that company, right? So you can have an alternate propulsion conference, kind of like a civilian skunk work, so to speak. And, everything would be decentralized and it would be voted for by the people, and the people that actually get the most votes would actually be able to convert those votes into currency, which can be converted into money. So it's still super nascent, but I think there's some really interesting opportunity out there in crypto. But what's beautiful about it is that it's so new that with just a little time and effort, anyone can really become an expert, because the knowledge curve is still relatively has still a relatively low slope. Okay. So the two things, if you remember anything from this for funding, right? It's dilutive versus non-dilutive. All that means is, money that when you get it, it affects your valuation, and money when you get it, that doesn't affect your valuation, right? So a grant from like the National Science Foundation, that would be considered non-dilutive financing, because they'll give you that money for free and you don't have to pay it back. A VC investment, let's say from like a seed fund like Y Combinator, or you go to any kind of other VC firm that specializes in deep tech, they would to a certain extent be dilutive, where your valuation would be changed and the amount of stock you own would decrease based on that investment. So just something to think about when you guys get to that point. All right. So now, what is deep tech? You guys did, I didn't get to see the show of hands. Who here is familiar with deep tech? Put your hand up or just click the button on Zoom. Okay. It doesn't look like, okay. All right, Philippe. Familiar with deep tech. All right, so let me explain deep tech. Deep tech is another word for hard tech, tough tech, science tech, frontier tech. There are a lot of different nomenclatures, right? There's a lot of different words to describe that. But all it means, it's something that's very expensive to build and low. And even if you build it, right? Even if you do all this and you gather the funds and you put in the time and effort to build it, it may not even work, right? And, that is what deep tech is to a certain degree. Here are a number of different sectors that would be considered deep tech. We're talking AI, material science, robotics, informatics, quantum computing, drones, clean energy, space tech. I am fairly confident that 99% of the presenters that are here would be qualified as a deep tech founder, just because the areas that you guys are working in are so new, so nascent, and generally speaking, for space tech or any kind of propulsion technology, you need a lot of money, a lot of time, or you need a really, really rock solid team in order to get it off the ground. But that's not again, this is not set in stone, but just generally accepted practice. Okay. You guys have any questions so far? You guys can chime in if you do. Okay, let me just go through. All right. All right. I don't see any questions. Okay, so I will keep going. All right. All right, so let's talk a little bit about a few challenges in deep tech and, you know, just kind of what you guys run into. Okay. First and foremost, startups are extremely hard, right? They are very, very hard. It's very, very hard to start a business. It's even more hard to start a startup, right? The difference between a small business and a startup company is that a small business, you know, generally speaking, growth is fairly consistent over time, right? So, you know, like if you have a restaurant can be considered a small business. However, if your restaurant is growing at 10 to 50% every single month, that is a startup restaurant. John, do you have a question?
Okay, sorry about that. So I had that set so that people would not, sometimes people accidentally interrupt. You guys can unmute yourselves now. So, and
Okay.
that's,
Yeah, I just wanted to clarify a dilutive versus undilutive investing. You know, dilutive obviously is people invest in your company in return for shares of it. That dilutes your own ownership, right?
Right.
Okay, and then non-dilutive is where they just give you a big block grant and say, like a government funding agency gives a grant and just says, go make this a success and report back to us.
Exactly.
Is that-
Exactly.
Okay, very good. Thank you. That's,
Yep.
Of course, I'm used to the latter, you know, the latter form of going to the government hat in hand and getting the big hat and getting money.
I mean,
Thank
hey, no
you.
problem. No problem, John. Yeah, and also like one other thing too, as far as like dilutive financing, you can have dilutive debt as well. So you can have what's called a SAFE, which is a simple agreement for future equity, where a company can give you a loan, right? But you know, your valuation would be affected by the amount of money you take in for that loan. So I don't want to get into the weeds of that, but that's another aspect where, and there's some situations where it's more beneficial to do a SAFE. Yeah.
Yeah, revolving credit line sort of thing.
Not necessarily a revolving credit line, but more so, you know, if let's say the company did not want to give up much equity and they wanted to, or let's say you were planning a big hire within the next few months and you know that you have a certain amount of stock that you want to allocate for your future employees.
They play with the variable rate.
Excuse me?
Growth. They play with the variable rate for growth. And that's how they, you know, always keep that portion.
I have no idea who is that.
sorry, that's Lulu. Sorry.
Hi. Oh, hi there.
You know, I have a few things because, you know, I was studying the Series 7 and, you know, I took the insurance.
Awesome.
Agency,
Me too.
You know,
Yeah, me too.
qualifications. And so I know a little bit. You know, you've got like, though, different kinds of money. So it's not what you're saying is like two ways. Not really. It's like, you know, a whole array of ways of what money, you know, really is. So, you know, talk about generational wealth. Generational wealth is supposed to be like origin certificates that are never, ever meant to be cashed in, but always promoted for this, you know, the continuum sustenance of what is called a civilization. And, you know, rules and orders and whatever you want to call it, like a you know, when you take a bond, you're taking something of generational entrustment, you know, and you build on that. And that's what creates the value system. And that's supposed to keep track of time, to keep track of, you know, what is the latest technology. And it's issued on these little things, you know, of detecting, you know, where the level of technology was and it timestamps it. You understand? So, you know, and then you've got the money that it's called disposable income. And then you've got, you know, the money that's supposed to be, you know, a building block in your civilization, like for agriculture. You know, agriculture bonds are, you know, they're not really, you know, those are supposed to feed the populace. So they stay as a continuum. So when you talk about, you know, those kind of stocks, you can't dilute those. those are fundamental. Those are elementary. Those are,
Well,
they're
yeah.
kept
So
in the
let's
system
try to
as a
stay
parallel.
focused. Let's try to stay focused on funding for innovators.
And I swear to God, I could teach all of y'all.
I know, but I
Yeah.
mean the problem is you're kind of getting off on a tangent. Okay, so I'm sorry about that.
Yeah, no problem. Yeah, there's a lot to unpack. I would say that yes, there are definitely multiple ways to fund your company, but it boils down to two things where it's either dilutive or non-dilutive financing, just for simplicity's sake. But there's a plethora of different options. And I think what Lulu you're referring to were the difference of investors. Yeah, I took my Series 7 when I was 19, 17, 18. So I can't say that I remember everything, but yeah, there are different levels of investors that are allowed to invest in certain different things. Hey, Philippe, you had a question?
Yeah, well, I'm not sure if you're done with the presentation, but I just want to have a link to your firm. Is it TLDR? Is that it?
No, the company that I work for is called applaud.cc. Yep. And I'll give you guys the email at the very end if you guys want to continue the conversation. And I also work on a podcast to showcase different entrepreneurs in the deep tech space. So
yeah, well, Rupert,
yeah.
if I could jump in, oops,
Yeah.
sorry about that. And you know what? Let me remove the spotlight here since we have other folks. There we go. We have other folks that are asking questions. So one of I think the big areas for our community is risk, right? And I know since you've studied HFGWs, I know that's an area that you've probably explored as well. Like the risk to return and how I'm wondering how would that impact investment? And for things that are naturally riskier, like this area or energy or anything like that, how can innovators pursue money in those higher risk brackets?
Yeah, I have, that is exact, I was going to get to that. If you give me 3 slides, I would get to that exact same question. Okay, awesome. But you read my mind, Tim. Awesome. All right, I love it. Everyone's super engaged. Okay, all right, so back to the presentation. Okay, so startups we established are super hard, right? Deep tech startups are much harder, right? And here's why, right? So Elon Musk, the proverbial man crush for every engineer, has he said this about starting a company, right? It's like eating glass and staring into the abyss. And if you feel like you're up to that, then start a company. And I would submit to all of you guys on this call that starting a hard tech company is harder than that because you're working on technology that technically doesn't exist yet. And so that has its own challenges that we'll talk about. We'll talk about those risks and we'll talk about how you guys can mitigate some of those risks with a number of case studies. Okay, so here are some of the big challenges that deep tech entrepreneurs face, right? The main risk, you've got technology risk, you've got a timeline risk, you've got overall just market risk, network bias, and domain expertise. To a certain extent, the last 4 are investor-specific concerns that you'd have to deal with. And the first one, the technology risk, is basically what you'd be working on, what you guys are currently working on now as you're trying to build a future. Okay, so the big thing with tech risk, right? It's anytime you're trying to invent something new, right? Something completely new, how do you prove that it works, right? And so generally speaking, you have to figure out how you want to do the technical evaluation for your specific idea, right? Additionally, you've got to determine whether or not you want to use a third party or you want to use the subject matter expert that is associated with the firm that you're trying to get funding from. The caveat in this case is that there may be a certain extent of reviewer bias, right? So let's say you were, for example, building a car that ran on water and you were trying to get an investment from ExxonMobil. It would be very, very hard for you to, I think that to a certain extent, there would be some concerns about reviewer bias there because this idea would completely undermine their entire business model. So as an entrepreneur in deep tech, you have to be mindful of that, right? The other thing is complexity. Generally speaking, these ideas are harder to conceptualize, and as a result, they're harder to sell. And so, you're not trying to boil the ocean when you're trying to come up with a new idea. You want to really just find a small beachhead. And so the example would be thinking about Tesla. When they came out with the very first electric car, they didn't come out with a number of different models all at once. They came out with the Tesla Roadster, and they used the funds from that to move into adjacent markets and to progressively build out their manufacturing. But if they tried to say, hey, we're going to build an SUV, we're going to build robots, we're going to build a sedan, a mid-sized car, and a hatchback all at once, the company would have died before it even got off the ground. And the last big risk that I see for deep tech entrepreneurs is what's called the intellectual property risk, right? To patent or not to patent, right? That's the big question. And there are different situations where they could be beneficial, where it might be beneficial to have a patent, and it might be beneficial to not have a patent as well. You know, when you do create a patent, you are basically taking your entire idea and creating a recipe book and putting it out to the public, right? Maybe that's not beneficial for you, right? Maybe you're concerned about there are certain countries overseas that may use that and take your idea and copy it, right? And so you might want to go the other route, which is a trade secrets route. But then you have to be super mindful about your hiring practices. You have to be super mindful about who you bring on the team. And then you've got to just make sure that there are a bunch of different forms of paperwork that can administratively control who has access to your ideas. All right. So the other thing is timeline, right? So the average startup, generally speaking, takes about 5 to 10 years to get off the ground. For a deep tech startup, and this is a guideline, we're talking 10 to 20 years. And that's because you're looking at manufacturing issues, you're looking at supply chain issues, you're looking at a number of different hardware associated issues that you wouldn't necessarily have with a software company. Okay. And let's get to the risk portion, right? Okay, so the other thing, we talked a little bit about the technical risk, right? Anytime you're dealing with atoms versus bits, it's always going to take much longer and it's going to be more expensive, right? You also have the challenge with when you're in a lab environment versus in a production environment, right? So building in a lab is different than trying to manufacture it. We saw that with Tesla when they went through production hell. Right. And the other thing too is like the systems risk, right? So you're looking at how can, oftentimes with a lot of these nascent technologies, you have a bunch of different new systems that are working together. And, you know, the challenge is getting them to work together all at once, right? So it's like the difference between like a symphony orchestra and just a garage band, right? You need all of these different components to work together in unison in order to make this product work. Okay. The other thing is business model, right? Who is your customer? How do you price and sell it? It would be really hard for, let's say, Netflix to, when they came out, I think it was 1999 when Netflix actually started. They actually started giving out DVDs, right? It was DVDs that they would sell by mail. It would be hard for them to price their monthly online approach where people come in and stream because the technology wasn't invented yet, right? And so as a founder in this area, you have to kind of be able to look around that corner to think about how is the technology going to evolve and how is your customer going to evolve and how are you going to price and sell it? And last but not least, you're looking at long sales cycles, right? So if you're building something for an enterprise client, if you're a startup, you're moving fast and you need money, you know, fairly quickly within a 1 to 2 year time frame. When you're dealing with enterprise clients, let's say you're dealing with an airline, or you're dealing with a utility, or you're dealing with any of these like larger incumbent industries, their sales cycle sometimes can exceed the life of your company. And that has happened numerous times, right? And so you've got to be super mindful of that, of like what your sales cycle is going to look like down the road. Okay. The other thing here, when you're dealing with funding, right, is network bias, right? So most VCs, for the most part, they rely on their own external network, right? And their track record for knowledge, right? And they're not at, you know, the bleeding edge of any new technological development. And so your general investments are going to take your due diligence that venture capital investors are going to make, going to need to take in order to invest with you. Sometimes that's going to be a little bit longer than if you were a traditional software company, because they may have to bring in other people, you know, that are specialized in that industry. And maybe you're the only one. And so that's another challenge too. Okay. So here's a quote from Sam Altman. He is the founder of Y Combinator. Does anyone know what Y Combinator is? Just like show of hands. Okay, Tim. Okay, I got one. All right. Okay. All right. Okay, Jared, I see you too. Awesome. Okay. So Y Combinator, for folks that don't know, it's an incubator. They provide about $125,000 for seed funding. And Sam Altman was one of the founders of Y Combinator. And the reason why he said to a certain degree that hard tech companies are easier to start is because once you have the technology figured out, generally speaking, smart people want to work on things that are challenging and want to work on big ideas. So if your tech works, your hiring, your investment, and your flexibility with investors generally is a lot easier than if you created another photo app to share pictures of dogs. Not saying that I have a problem with any photo app that shares pictures of dogs, but you just have a much easier time to raise funding. Okay, let's talk about some strategies. And the way I'm going to break this down is we're going to go through some case studies on how you guys can, on case studies of actual companies that have gotten funding, that started with tech that was hard to build and is actually successful now. Okay, so here's one. Boom Supersonic, what they're doing is they're building a replacement to the Concorde, right? And New York City to London in 3.5 hours, right? Obviously, the founder of Boom Supersonic did not start out working on this company. He started with just a normal, I believe it was a file sharing app. He made an exit and then he was able to roll into this company. And because of the fact that the idea that he was working on was so compelling, he was able to pull in a lot of talented engineers. So one strategy, right, when you are working on a new technology, something super nascent, is that you want to have a team of top advisors. You want to try to find and assemble a team of leaders in the field. If you are the smartest guy in the room, that is fine, but you need to find people that are the second smartest, in this specific topic. The other thing too is building computer simulations, right? And Tim, that's one of the things that we're doing with some of the the HFGW research, right? That was the biggest challenge for us. It's being able to build an adequate computer simulation, for the high frequency gravitational wave generation and detection. And the other thing, the last but not least, is building a portable model. So what Boom was able to do, they actually built a plastic model of the plane, and they used this coupled with their simulations, coupled with the backing of their team of top advisors, and they went to different airlines and were able to actually get contracts with those airlines, right? And so so this is one strategy that can absolutely work, and it has worked in the past. Okay, let me go into the chat. Let me see if there are any questions really quick. I see Founders Fund. Okay. All right. Okay. All right. So here's another one. Astronis, right? Astronis, what they're trying to do is build really small, low-cost satellites for wireless internet. So very similar to what Starlink is doing, but they wanted to do that. They want to do that at scale as well. So their when they started, I think it was like 5 years ago, in order to send one item to space was $10 million, right? So imagine you're in your garage and you want to develop a satellite, but the only way that you can do it, you need $10 million, right? That's a big challenge, right? It's a very hard ask. So what they did, they were able to build a very, very small prototype, and they were able to launch it into space. And the total cost for them to launch that small satellite into space, granted, it was no frills, it didn't do anything, but it showed that they could launch something into space, and they spent $50K on it. And that was enough leverage for them to be able to take that experience to investors to show, hey, we're a real company. We're actually working through this, and we need more funding in order to continue to build out our idea, right? And so it's being able to just eliminate that risk traditionally, systemically, as you're trying to build your idea and build it out. Okay, let's go to the next one. All right, so here's another one, Ginkgo Bioworks, right? What they're doing, they're using genetic engineering to produce bacteria with industrial applications. I spent probably about 2 hours researching this company, and I still really couldn't figure out exactly what they did. This was the most simple definition that I could come up with. But however, the way they were able to be able to actually build out their company is what they did with something called pre-sales. And so they actually went around and they sold their items before they even manufactured it. And the way they did that was with something called letters of intent. And I'm going to get into this in a little bit, but I think for a lot of hard tech founders, I think letters of intent are a big unlock for you guys, because that'll do a bunch of things, right? It'll get you better at actually selling the product. And it would also, and the thing about letters of intent, they look like a legally binding document, but they're not. But customers take them seriously. So traditionally, it's harder to sell it because any customer will tell you, okay, yes, I will buy your product. But when you put a piece of paper in front of them that says how many exactly will you buy, at what date, what specs, that's when you start to get some more information. And that's when you have the opportunity to possibly refine your idea some more. So Ginkgo Bioworks is a really cool example of that. And last but not least, my personal favorite, Gravity Industries. You know, what these guys do, they create portable jet suits. I mean, it looks, if you've ever seen these videos on YouTube, it's absolutely next level, right? Their initial idea was to create these jet suits for the masses, right? As a form of like personal transportation. But they realized at $100,000 a jet suit, it wasn't very feasible for everyone, and they couldn't get the technology any smaller. And so what they did, they made a pivot, right, to custom suits and to flight experiences. So what they do now, they have one suit or a bunch of suits, and they have it at a fixed location, and people pay $5,000, you know, for a 3-hour flight experience, right? And so this is an example of, you know, just really, you know, just out of the box thinking of how can you take your idea, how can you get it funded, and how can you generate customers given the initial conditions that you have. But they also, another thing that the CEO did really, really well was compelling storytelling. If you go on the website, it looks like next level, super futuristic stuff. And who doesn't want to be a part of the future, right? Okay. All right, so let's talk a little bit about letters of intent. These, I think, as I mentioned before, these are going to be super important. Like when you guys actually build out your product, I think that this would be this is like one of the least utilized strategies for deep tech entrepreneurs, right? Letters of intent, right? And so a good one, it details the number of units that your customer will buy, you know, the price that they'll pay, when they'll buy it, and the specs that your product needs to achieve, right? And like, so why is this important, right? Why is this such a big deal? Why would we even need this piece of paper? Why would we need this document from our customers? Well, it gives you a roadmap. It tells you exactly what your customer wants. It tells you exactly the timeline that they want it in, the price that they'll pay, and the number of units they'll buy. And you can use this as a reference point when you go to investors. You can say, hey, we have 1,000 letters of intent from X number of customers so it shows that there's a tremendous amount of interest in this product. You know, we need X amount of funding in order to continue to build out to this next phase. And so I think letters of intent are super underutilized. And, you know, once you guys actually build out an MVP, I think this would be a really cool strategy. And it's one that's worked tremendously in the past. Okay. Tim, did that answer your question by any chance?
Yeah, absolutely. Absolutely.
Okay. Does anyone else have any questions so far? Philippe.
Yeah, and we're pushing up against the top of the hour, and so, but you know, you've mixed the questions in. Normally we do kind of a Q&A session. We can still do that. It's completely up to you.
Okay, I'll answer Philippe's question, and I'll just keep moving. I've only have a few more slides.
Yeah, Philippe, go for it, sir.
All right, thanks Tim and Rupert for this great presentation. It's really awesome. So I did present my company on the C++ ISO mailing list at some point, and there's a lot of guys from Intel over there, and then we talked to Intel. We presented them our solutions that optimizes Python code and makes application crash proof in C++, and they said no, they were not interested. And then a few months after, they came up with their own solution to optimize Python. So they kind of embrace and extend our solution a little bit. It's not exactly the same thing, but kind of did that. So do you suggest like to partnership with other companies before aiming these big tech companies, or because if they see that you're weak, they're just gonna step over you?
Right. So the question, Philippe, I just want to make sure it's, do I think it's beneficial to partner with smaller companies before you try to partner with larger companies because of the risk of them stealing your idea?
Yeah, or just thumping you.
Yeah, I mean, I think it all depends. I think it really depends, because what you could do, it's if you have, like, let's say you're going into an industry, into an industry where there's a lot of competition. Generally speaking, you don't want to be in an industry where there's a lot of competition, right? You want to be in an industry where there's minimal competition. Look at Amazon when they first started, and with AWS, look at Tesla, so you want to have that, like that head start. But if you are going into that industry, what you could do, you could try to play competitors against each other. You could try to work with like smaller companies, like you said, and build up some and kind of operate in stealth mode to a certain degree. But I think it all depends on the situation, and depends on what you're actually trying to do, and like what you're. Risk, someone infiltrating your company, stealing your idea, or you trying to pitch the idea and someone, making some kind of some very, very similar idea. So I think it depends.
Yeah, our first solution is patented, because it's kind of we can read the code, so we had no other solution but to patent it in North America. So but yeah, thanks, I appreciate it. And if you have like a contact information, that would be great.
Yeah, it's on the last slide of this email. Okay. And John, then I'll keep moving.
Am I okay? You can hear me now?
Yep.
By the way, I'm enjoying your talk very much, Rupert.
Thank you.
This is reality. How to take these ideas we're discussing and turn them into real growth economically. Right. Let me just clarify one thing. The letters of intent that we want to seek, like the Boom people did, are so you can then take them and show them to investors that there is basically a good market for your idea, if you can get it to work.
That's correct.
Okay, good. Just wanted to make sure I was clear on that.
Yep.
The letters of intent are not financial commitments. They're basically bragging rights.
Yeah, I mean, so the thing is, the really sneaky thing. Bragging rights are important. the sneaky thing about letters of intent, and the really subtle aspect of it, it looks like a binding document, but it is not, right? And so customers take them very seriously. And so And so what happens is you can, this will be part of like your customer discovery. Like when you get into that whole point, when you're lead generation, customer discovery, and like closing, and your customer development cycle, that'll be like super useful information for you. But like near term, your letters of intent just basically, they give you leverage with investors, and they give you some super, super warm leads for you to follow up with when your product is getting close to development.
Very good.
Okay.
Thank you.
No problem. Okay, let's talk a little bit about how you guys can fundraise, right? So I found this meme online, and I think this is like a perfect example of how you should not try to fundraise, right? You don't want to go as a deep tech entrepreneur, go from zero revenue to $100 million Series A, regardless of how good your idea is, right? Because, well, it's very hard, very, very hard for an investor to give you that much money on a seed round. So we don't want to do that. That's not a good idea. Okay, so I'll give you an approach that I think is much better. this is generally an approach that you want to go with, right? And so as you notice, you still raise the same amount of money, but what happens here is that you break it down into steps, right? And so a good entrepreneur, a good founder, scientist entrepreneur, what they can do is get super maniacal on the milestones that you hit. So let's say, you know, you get your pre-seed round and you say, in order for me to, and you build, in order for you to raise your first seed investment, you'll have to, let's say, build out your engineering simulation, you know, to a certain extent. And then, you know, with your second seed investment, let's say you build your first MVP. And then for your Series A investment, let's say you start developing your first, you know, 10 or 15 customers. But this, and even that's not, you know, set in stone. But the whole point is, and the whole like big picture when you're trying to raise money for an idea is that each level you want to eliminate risk, right? Because like what you don't want to do is take $100,000 from an investor, and then 6 months later, you ask them for $2 million, but you've made no progress whatsoever. You've closed no customers and you've done nothing different. That is generally a sign that, you know, you're not managing the company well, and that you're not, you know, focused on growth as well. So what you want to do is just like really good deep tech entrepreneurs, what they do is they try to maniacally eliminate risk. And you want to get down to the bare bones minimum thing that you can do, that milestone that you can hit for each of those seed investments, each of those stages of fundraising. And if you can do that and you can do that consistently, you're off to the races. Okay, so last quote, certainty of death, small chance of success. What are we waiting for, right? This quote was from Gimli in Lord of the Rings. And, you know, so, you know, I do feel like, you know, granted, you know, it's extremely challenging to be a deep tech entrepreneur, right? You're working in a field that is absolutely nascent, right? It can be a lonely road at times, but, you know, in order to change the world, we're not going to do things that are easy. We're going to do things that are hard, right? And so I have a tremendous amount of respect for all of y'all that are on this call, that are just continuing to try to build the future, because the people that think they can are the only ones that actually do. So with that, I'll leave my email and I want to open it up for questions for all of you guys. Philippe, yeah.
Okay, so let's do this first. Let's do this first. So everybody, so if you guys want his email, write that email down. What I'm going to do is in just a moment, but it's rupert.wade@applaud.cc. Okay, so now I'm going to stop screen share as is customary. And let me put this thing on gallery view. Everyone, please give Rupert an enormous applause. Rupert, thank you so much. The business side of things has been completely neglected in our conference. That's something that we need to focus on. I mean, we should do so much more on that, and we've neglected that. And you're the perfect person because you have experience in HFTWs. You know this community, you know this industry, and you know funding. So thank you again. Thank you so much for presenting.
Yep, absolutely.
Okay, well, so yeah, let me go to John has this hand up. Let me go to John, and we're in Q&A session now, like official Q&A session, I guess. So, John, you're muted, sir.
Okay.
There we go.
Let's say I've made a method to get warp drive so we can get to Mars in a week rather than 10 months. Now what do I do? I got it working in my garage.
So, well, that's great. So I guess you're saying if you have a working
this is, of course,
prototype,
hypothetical, of course.
Right. So
I don't even have a garage. In a conventional sense.
Yeah, I mean, so like, I guess if what you're saying is like, if you have a working prototype and you have, and you're absolutely certain that it works, how do you get funding from there, right? I think what you can start with free money, which is there are grants from the National Science Foundation. There are a number of different grants from a number of different places. There are also a number of different startup incubators that focus specifically on deep tech entrepreneurs. There's one that's the Google X Prize was one. MIT has their own incubator called The Engine. There's another incubator called Hacks. And what I'll do is I'll put together a Google Doc with a bunch of these different resources so that you guys have access to them. But, you know, once you've actually got the technology and your MVP build out, I think the first step you want to go for is try to find funding that's non-dilutive, meaning find funding that does not affect the amount of stock ownership that you have. Because generally speaking, since you're the one that's inventing the idea, you want to keep as much control as possible. So I would say that, you know, go through an incubator, and then from there, you know, build out a team, and then set up some milestones for how you want to go from an MVP to actual production, right? Because at that point, you'd want to start thinking about manufacturing. You'd want to start thinking about parts availability, supply chain issues, you know, hiring, growth, you know, marketing. There are a number of different things, but the first thing you want to focus on is try to get some more free money in order to build out a team.
Free money. I like the sound of that.
Me too.
Okay, so you start with the grants and incubators. Okay, good.
Yeah. And this is not set in stone. It's all dependent on your idea and kind of what you're trying to do in the future. But I think generally speaking, you know, you want to go for non-dilutive financing first, you know, so that way you can minimize the amount of influence that you have in your company down the road. I think we saw Charles
Very
next.
good.
Yeah. Yeah.
Very good. Thank you.
Okay. Yeah. And Charles, go ahead, sir.
Hey, can you see me? Can you hear me?
Yeah. Yeah.
Hey, it's my first time on the APEC meetings. This is very exciting for me. I decided to join. I saw John's name on here. John probably doesn't remember me, but we worked together at NASA 20 years ago at Kennedy Space Center in the Electrostatics and Surface Physics Lab. Anyway, just hi, John. It's nice to hear you again, if you remember me. So this is a great talk, Rupert. I definitely enjoyed it.
I do remember you, Charles.
You do? Oh,
You were
that's
working,
wonderful.
I can't remember. It was a guy with a very Hispanic sounding name, I think.
That's right. That's Dr. Carlos Calle. I've taken over from
Yeah,
him
yeah,
as the lead of the electrostatics lab. Yeah. Yeah. So Carlos and I
Mars
worked
is
together.
one big electrostatic generator. I love it.
Yeah. So is the moon for
But
sure.
anyway, pardon me.
No, you're fine.
Pardon me.
But no, this is great. You know, this is the first time at this conference. I had a couple of questions. I've blown away by this conference so far. I really enjoyed it. I've seen some of the other talks, but so for Rupert, I don't know if I have so much of a question other than just a comment. I do have, in addition to my NASA work, I do have a side company that does have propellantless propulsion technologies. And you know, we looked at the market. You know, we can generate thrust, we can generate high vacuum, we can do the little spinner things and all that jazz, and we can do it in Faraday cages and all that jazz. You know, the typical scientific method. But the thing that I question is, how do we, as a community, tell the world that this is actually real? That's the biggest thing I think we have to overcome, because until we get to unity, which is basically, we know, lift an object up by itself under the gravitational force, how do we demonstrate it other than actually going to space, showing people that it's real? And then when we go into that market, you know, what we found, we've been doing this for 6-7 years now, and it's a slow, dramatic increase in thrust. You know, we've come, you know, 4 orders of magnitude, but it takes a very long time. And so my question is, other than the satellites market, where is the customer base other than small satellites or satellites itself? Because, you know, the Starlinks are up there, they're going up every day. The electric thruster community is well established, hard market to get into. I'm just looking for what other ideas are there other than satellites, if there are any, and just waiting to hear your answer if you've had a chance to think about it, Rupert. Thank you.
I mean, I would propellantless thrust. I would think in aerospace. I think that would be near term, without really like understanding a lot more about the idea itself. You know, as far as finding the customer, you know, and that's the thing, right? It's, for the most part, anytime you're building something that's like super, that's within the deep tech sector, right? Where it's something completely new. That's the challenge that a lot of the founder entrepreneurs have, right? It's finding that first customer, because it's usually what people do is, what we have happen especially if you're an engineer first, is you build the idea and then you try to find the market for it. But the really cool strategy and the pivot that a lot of successful engineers do is they find the market and then they tailor the idea for that specific market, right? But if you're looking for, I would think, like, if you're trying to get some kind of additional interest in it, maybe getting some third-party validation or some measurements, right? There's Dr. Martin Timar out in the University of Dresden, and he's built out some of the most, precise propellant measuring devices like on the planet. And so he's working at a university. He's a source of truth there that you could use as a reference, right? Just having some independent, I think, third-party validation of those claims, I think that'll, be very good to give you leverage in order to at least get some more seed funding and to try to build out the product and when you get some more results. And also engineering simulations as well, if you do have some. Those would help as well.
Yeah, that's fine. We have the theory, we have the experiment, we have the modeling, we have the startup funding. It's just a question of, okay, when we go look for customers, who are the customers? Who are they going to be? Who's going to pay for this? How are we going to get into the market? How are you going to, break into the market? Because, until we get to Unity, there's not a huge market out there. Most of these satellites have already chosen their propellant systems, and so it's just a question if maybe there's someone else that we're just not seeing. What are the use for this propellant technology?
Yeah.
What's the use of it?
Well, we can definitely continue the conversation. You can shoot me an email, and we can talk a little bit more. Just so I can try to understand a little bit more about what you're doing, and then if you'd like, we can talk a little bit and chat a little bit more in the future.
Okay. All right. Thank you.
Yeah, absolutely. I think Harold.
Yeah, I think Harold was next. Harold, go for it, sir.
Yes, well, the John Bueller had the same kind of question. What I do is propellant propulsion, and I have my device, the concept demonstrator, 4 patent pending. One of them about to issue soon, and I have demonstrated that thing I've been looking into, because I can provide enough thrust to move a satellite. That's the market I'm going through. My question is that several years ago, I went to a incubator, and they were asking me, questions like, how many cells do you have? Show me your books. Let me see the cells. And I said, well, look, I'm just started. I have a concept demonstrator, and I want to do this, but they said, well, no, you have to have cells. Now, what kind of question are incubator asking now at this stage? Because I have a new technology, propellant propulsion. I got lucky that nobody had that idea, even though it's a well-established science. And when I wrote my patent, that's what I did. I put what is there, the principle and everything, and I did the experiment. And I have videos on YouTube. So what kind of question are incubator asking today is about somebody come out with a new product and showing the market?
Yeah. So the question is like, just let me make sure I got the question. It's what questions are incubators asking nowadays compared to, when you went in several years ago? I think it depends on the specific incubator, but the big blocks, right, is what's your idea? Who's your team, right? Do you have results, right? Were they objectively verified? And what is your vision? Who is your target customer? Now, most engineer entrepreneurs in the sector, they always neglect the target customer approach, which is why I think it's really cool, to start thinking about those letters of intent, right? If you build out that MVP, thinking through it, you have an MVP, you have an actual a product that actually works. I think the big unlock would be to say, hey, we have people that are willing to actually try to buy this product. We have people that are interested in this product, because to a certain extent, incubators, they don't really know, you're the expert, right? You are the one that have developed the idea. And so they just need some type of validation to show that what you're saying actually makes sense and that it's objectively verified from some kind of third party, right? Because if you're talking about completely new physics, completely new technology, you're the only one on the planet technically that would understand it, right? But how can you convince someone else to buy that? And how can you actually build a business around it so that that incubator can make a return, right? Because that's what they're doing. They're investing in you a small amount now, so that in the future, when your company is valuable, they can make money off of it, right? A certain percentage that you would agree to, obviously, but that's the whole thing. So if you keep that in mind, if you can show that your company is going to grow, show some objective validation of your idea, of a demand for that idea, I think that'll take you a long way, as opposed to just waiting for that question to be asked to you. You know what I mean? So you can take it head on. So just to recap, right? The team, your vision for the company, the fact that it works, objective validation, right? And to show that there's some level of customer interest in the idea, albeit small, but just to show some kind of traction.
Oh, thank you.
Yep, you're welcome.
Okay, so let me go back to Phil. Phil, go for it, sir.
Hey, hello, that's me again. I think you know me. So the National Science Foundation, I tried to contact them like 3 years ago. Obviously, I'm from Canada, but now I've got an American umbrella company I can use. But how long? They never really replied to their email. And how many times a year do they have, like, are they doing funding? And what's the range they can offer?
I don't have any specific information on what their range is and how many times a year, but I'm sure on their website, I think it's yearly. I have no idea what their investment cycle is, because I'm not directly involved with them. So I would say that you'd have to really just check out on the website and see what that application timeline is, because those dates potentially change over time, and the criteria could change as well. So I think the website for the NSF would be like the best source of truth.
Okay, and what is it I wanted to ask? I forgot sorry, I forgot my question, but thanks.
No problem.
Right.
And I think,
yeah, so let's go to Shrish next. Sir? Oh, where'd he go?
Yeah.
There we go. Okay.
Yeah. So, nice presentation, Rupert. So I just had a question on, what you mentioned about Boom, right? In terms of they assembled a really good advisory board. So I'm looking for some pointers or any insight into that. How does one go about assembling such an advisory board?
Yeah, it's in the same way of like, how does one hire a top tier team, right? I think there some parallels in that advice would be reach out to your own individual network, right? For one, you'd want to find experts that are in that field, right? Subject matter experts within whatever specific sector that you're working in. So if you're like in high frequency gravitational waves, right, there are really only one or two experts in the field, but tangentially, right, you'd want someone that is familiar with communications, familiar with advanced communications, LiDAR, radar, and things like that. So you'd want to find people that are experts in areas that are adjacent to the area that you're working in. So that way, because like it may be hard to find somebody that's an expert in that specific thing, because it's new science, right? Like you're the only one. So you'd want to find people that are leaders of their field and leaders in related fields, right? And just
okay.
Yeah.
Okay.
Mm-hmm.
Yeah, I think that's one of the challenges. I'm sure this is a normal challenge for anyone who's doing something new, especially in this area of propulsion. Finding people. Yeah, I agree. No one in the direct, only the entrepreneur knows what they're doing specifically, but got to get that kind of validation through this advisory board, and getting that reach is the big challenge. So anyway, thanks.
Yep. No problem. And social media is also your friend as well, right? So, you know, we're in an unprecedented time right now where the leverage that you have, it can be with your phone, right? So if you're good at storytelling, good at networking, you can widen your circle, and you can use LinkedIn, you can use there are a number of discussion forums. There are a number of different online communities where you can try to garner that community support, and then you can use that as leverage to reach out to some experts. So like, for example, when I was working through, you know, with some of the work for high frequency gravitational waves, the only person I knew was that was familiar with it was this guy named Kip Thorne. And so he actually did the signs for Interstellar, the movie. And so I reached out to him. I sent him an email, and I just asked him to kind of review some of the work, and you know, granted, you know, it went to a certain extent, but he was able to give us, you know, some like really unique information. So you know, don't be afraid to reach out to these folks, because like in academia, it's very different than like if you're like the CEO of a company, right? Like with academia, these people's phone numbers are just right there on the paper, so you can just call them up, which is absolutely insane, right? So,
so do they respond to such cold calling kind of stuff?
Maybe not, but it's, you know, there's only one way to find out. You know, and so you can either email, you can call, but you know, really just the approach will depend on what you're trying to do, what kind of information you're trying to get. But you know, I think just utilize the information that you have and try to widen your network, and don't be afraid to reach out to people that you don't know.
Okay, that's great. Yeah.
Awesome. Well, thank you, Shrish. Let me go to Jeremy next. Jeremy G.
Yes, can you guys hear me?
Yeah, and can you turn your camera on if that's okay?
Yeah. Yeah, I had a question regarding what do you call it? Whenever you're if anybody knows any technical things about frequency input, like around extremely low frequencies, around like maybe even 20 hertz or something, is it possible to detect any like wattage, even if it's just like 1 watt, if it like is produced when you're starting to slowly increase the signal?
Oh, okay. Well, let's try and focus this in a little bit on what Rupert is presenting on, right? So
okay, we're still in context. Okay.
Yeah. So let me do that. So Jeremy, let me go to Charles, and I'm going to put your hand down. Give some thought to, you know, what you might want to. Okay. Okay. Let me go back to Charles.
Yeah, I just wanted to add, if you can hear me again, the NASA SBIR program also can be used to get funding as well for small startup companies, right?
Yep.
Not just NSF or Department of Defense or DOT. You know, the federal government does provide funding for these things too, which you can also, you know, make use of. There's been a lot of big changes at NASA. A lot of the naysayers on this technology are gone. So this is a new age for NASA.
That's awesome.
So,
that's awesome.
You know, and if you have a topic that you think might be worthwhile, you know, I am a subtopic manager for some areas. So whether it's instrumentation or testing methods, or, you know, basically the propulsion itself, just let me know, and you know, we could always put out a solicitation for that, and the government would have to respond and send out calls. So that's another avenue that you can have access to for funding. But just wanted to add that to your list, Rupert.
Yeah, thanks, Charles. And you know, what's awesome is that I had a list, and the SBIR program was on there as well. So I put together this Google Doc, and I will share it with Tim after the call with a number of links for non-dilutive and dilutive funding sources that you guys can peruse at your leisure. And I think there's got a couple more. I see Charles and Mike.
Yeah. Let me see. Well, so we were just with Charles. So let's go to Michael after that. Michael, go for it, sir. And can you turn your camera back on?
Yeah. Hold on a second here.
His archaeologist gear. There we go.
So, Rupert, I enjoyed your little presentation there. I got a so I'm trying to approach this whole thrust thing from a different avenue. Everybody's like looking at bigger stuff, like you're talking about stuff in orbit and space. And I have several patents on a thing called gravitomagnetism. I don't know if you ever heard of the term.
I have, yep.
Yeah, and Martin Tajmar used it in some of his earlier papers. He talked about it. And
Tajmar, yeah, I've spoken to him.
And so I've communicated with him by email. Essentially, I have the patents and stuff. So what I'm trying to do is find a way to get it so that it's anybody can have it. Anybody can have their gravity diode. And so essentially if it'd be okay with you, would it be okay to do a share on this one, on this computer, Tom?
Yeah.
Tim? Are you okay with that?
Yeah, go for it.
Okay. Hold on, there it is, share screen. Okay, do you see that there?
It's just starting now.
Okay.
There we go.
Okay. So now what we have here is an image of in your computer, there's a thing called a hard disk assembly, and it has this little disk that's spinning around, and you write on it. And there's this zone near the center of the disk where there's these little nanobumps that are made with a laser. And when your computer is turned off and there's no power, the read-write head is sitting over that zone. They call it parking your head. And so essentially, what I discovered is those little nanobumps produce energy called gravitomagnetism. And so what my invention does is it takes those little nanobumps and it maps them out, and then it breaks them up into sectors. And so this is like in the background of that little figure of the nanobumps and the disk is basically the steps that it goes through to make what's called a private key. Private key is a mutable identity. It can't be changed because it's based on what's called topological features that exist only on that disk platen. So essentially what it does is it creates a map of the surface of the disk, and then it creates sectors, and it creates a number that it then matches against a public key, like your password on your bank account, your PIN number or something like that. That's a public key. And so what it does is your data then is essentially immutable. If somebody else with a different computer got your PIN, for example, and tried to access the data, it wouldn't be able to because the disk platen on their computer would have a different pattern that wouldn't match. And so now the reason I want to do this is to make a new cryptocurrency, okay? That it's like Bitcoin, but instead of mining like they do now, which essentially is they have these special computers that try to solve a problem. And that's what Bitcoin uses, and it uses a lot of processor and memory. And they have these big farms of servers that use huge amounts of energy. Instead of using energy, this device collects energy and it stores it on your computer in the battery. Because most of the time when your computer's running, that little disk is spinning, and then the head sitting right over that texture zone, and it's not collecting the energy, it's just wasting it. And so that's what my invention is. And I have a patent pending to do just what I'm talking about. Now, I tried the approach on, hey, I got this invention, and you can do like propulsion and all kinds of nifty stuff with it. You can do like space-time metric engineering, stuff that's pretty wild and far out there. But how do you get it accepted?
Mike, I'm going to have to talk to you about this project later, because I think I can give.
Yeah. Let's try and Michael. Let's try and focus this back in. So I think what you're saying is what is your approach for funding
like for this? That's exactly my question.
And it sounds like you've refocused your idea so that it might appeal more to conventional funders.
Yeah, so that there's a customer essentially.
Rupert, on the crypto investment strategy.
Well, I want a customer. I want a customer base. That's
Well,
it's like hey, satellites are great, but how many customers you got?
I think it's a really cool pivot to. It's almost like an analog blockchain in a way. I think that's super cool. I mean,
Mike,
right off the top of my head. Yeah, I think that it's you'd have to find people that would benefit from from the increased efficiency, right? The higher security. I can think right off the top of my head, probably military applications, possibly, without kind of like diving into it and being well read on it. But I think if you're pivoting into an area that it seems like it's higher security, right? More efficient. I can just think near term, it would just be like some kind of telecommunications play, right? Or some kind of military security play, potentially, right? But that's just off the top of my head, just thinking about it without like being very well read on the software and like how it's built out. But the very first thing, right, is like you'd want to make sure that you have, and it seems like you've got a patent pending. That's awesome, right? And just like try to find any sector, find one specific sector and start talking to people in that sector to see whether or not there's a need for it, right? And if you can find who, and when you can triangulate where that need is, then you can go to those individual people and say, hey, this is what I've got. I think this is better than the current solution that you're working on, which is X. What would you be willing to pay for it? Or that's when the letters of intent can come in, where you can say, okay, we're in the early stages of production right now. This is our timeline. Once we go into full production, once this is live, would you be willing to be a customer, right? And then you collect those letters of intent, and then that's how you can use that as leverage to get more funding to build out your team and to grow the company.
Okay, thank you very much, Rupert. I appreciate your answer to my question, and I won't take up more of your time, but I appreciate it, and I appreciate your thoughts on it. Okay.
Yeah, and if you have any questions, shoot me an email.
Okay, will do. Thank you.
Okay, and Michael, thank you. So let me go to Charles now.
Charles Crawford, or okay. Yeah, hello. I was wondering, what are your thoughts on non-disclosure agreements or NDAs?
Yeah, non-disclosure agreements. Generally speaking, anytime an investor looks at an NDA, it's like a red flag, because and that's just, I didn't create that rule. That's just kind of like the general consensus in like Silicon Valley and with startup funding. Just because there's that old school thought, right? Ideas don't matter, it's execution, right? And when you're first realizing and like communicating with like investors and VCs, you've got to make the process as easy as possible, right? Because like here's like the general flow chart of how like you would reach out to a VC, right? So you find the company, the VC that you want to work with, then you find someone that knows that VC, and you reach out to them to possibly get an intro, and then from there you would then get the warm intro from that person, and then that's when you'd send an email out with just like a short, like a 1 or 2 sentence description of your product, what you're trying to do, what your goal, what your mission is. If during that point you shove in an NDA, it'll kill the relationship before it starts, right? So I'm not familiar with like any situations where like a VC has like signed an NDA. But I mean, it could have happened, but the general consensus is that, you know, NDAs are usually a red flag for venture capital investors.
Okay, so you should avoid them completely or wait until later?
I think you could, I would try to avoid the NDAs, you know, because like, here's the thing, like if, you know, someone signs an NDA, how do you know they're not going to just like, that individual person is signing the NDA, right? But if they're a VC investing in like a number of different companies, how would you know that they didn't tell one of these other competitors to actually start working in technology that's associated with that, right? And so the time that it would take you to pursue the legal battle throughout that NDA, you can actually be taking that time to build your company and to innovate, right? And so I think that's the best strategy. Anytime you're dealing in hard tech, you have to be at the bleeding edge of the innovation, and you got to move super fast, because that's why, to a certain extent, Tesla, you know, they're open source, they open source their patents, right? Because they've been moving so fast and they innovate so fast that by the time a company actually catches up to them, they're working on a completely other idea, right? So it's a roundabout way to answer your question. I wish I had a more firm answer, but you know, you want to kind of focus on the innovation as opposed to trying to lock in just this one iteration of your idea, because additionally, an NDA kind of just tells an investor that your idea is not going to change, right? Because your idea is going to change over time, right? You know, it's going to evolve as you get customer interest, as you get more information, you get more money, you get more people on your team, you're going to innovate, right? And so you want to index towards innovation and not necessarily towards secrecy.
You know, Rupert, also, again, I'll step back from moderation for 2 seconds. So in my experience, and I've had people approach me, like with APEC, they've had me approach me with NDAs, but also with technology I've developed and stuff. And the perspective I use is kind of like a market maker, right? Like I would say that, you know, if it's compelling and it's demonstrated and you're, you know, making news headlines worldwide, right, then you can do the NDA and get away with it. But for the most part, what I've seen is, you know, if you're looking for funding and you're kind of in startup mode, most VCs, if you give them an NDA, they'll just walk, because you're not a market maker, right? You can't dictate to the market what it is. You have to accept what they're willing to do. And I did some volunteer work for a blockchain company, and they tried the NDA, and it was the same thing. It was just like, okay, well, we're not going to sign it, so have a nice life, you know?
Yeah. And the thing is, like, you know, if you want to get an NDA signed, right, you have to have some kind of leverage. Like, have you started a company before? Did you have a successful exit? What have you built before? So like you said, Tim, if you're starting out cold, you want to make it as easy as possible to reach out and to connect with these VCs.
Yeah. Okay. Well, let me go to Thomas again, sir.
Am I coming through?
Yeah, you are now, sir.
I don't know if this is going to work or not.
Uh-oh.
No camera?
Well, no, the camera is mostly working.
Mostly working?
Yeah, it's upside down.
Oh, am I? Weird. Weird, okay. I've actually got the camera upright. I must have inverted it at some point.
I thought it was like a new invention.
Yeah, that was like
demonstrated.
Nope, just misuse of an old invention in software. I was just going to say, on the NDA thing, if you have to get somebody to sign an NDA, you're explaining it far too in depth that you're going to basically overload the person with information, and they're going to zone out long before they ever get to the point where they, show an interest in actually jumping in on it. So you're probably not going to give them enough information that they could use that information to go and spill the beans to someone else anyway. So you'd want to save the NDA for later, whenever whenever it's people who are coming in to work on it and whatnot, so they don't get the information and walk away, to go to somebody else who has, more money, and then, end up screwing your investors. Because it's going to be your investors are going to be more, they're going to be the ones that are at greater risk. So, I mean, I would concentrate on trying to trim that down to where you're, like he said, storyteller. I don't think it's so much a storyteller, but can you be concise and entertaining enough that somebody doesn't fall asleep or zone out or stare off and look at something else or not being so crazy that basically they're too focused on your antics than your information. So
I've been approached with the conference with American Anti-Gravity, stuff like that, with people who want an NDA before they'll even tell me what it is, right? And it's like, I got something really big here. You got to do an NDA first. I'm like, who are you? Do we know each other? Right. So maybe there's some dating rules involved there. It's like, let's get to know each other a little bit. So, what are you working on?
Right. Yeah. I was gonna say, if you're just dating, you don't need a prenup.
Yeah. Yeah. Exactly.
Yeah, and that's when you really got to refine that elevator pitch, right? But just have a one.
Yes.
You should be able to describe your idea in one sentence, right?
Right.
If you need 3 or 4 pages, then you've got to trim it down.
Right. It's something I've struggled with on my deal. Like I said, my focus on replicator technology, but I almost always forget to even integrate that. Hey, look, it's also a refining and recycling system too. So you have say old electronics you don't want. Say you have a busted LCD TV. You can feed that in pieces and it'll literally break it down and sort all the materials so you can use it to print out a bunch of cell phones or something, and an energy harvesting system so that it's portable. That's the important thing. Bring the technology that is in big factories all the way down to where it can be sitting on a desktop or on in a garage, or you can print out bigger parts with the little ones so you can line the inside of a garage so you can print a car. Or print an even bigger one so you can print a whole house and do it, So, and I've got a bunch of other stuff that once I've got their attention, rotary systems that basically can burrow through the ground, refining the material that they're going through while printing whatever system, like a cellophane system or something like that, so it won't collapse. So you could just build whole, networks of tunnels and whatnot while you're collecting material for people to live and leave printers behind in all these nodules off the side, so it's like a bunch of bronchia. It can go any direction you want to go.
It's like the movie Screamers. That movie freaked me out.
Right. The big thing is, it's focus on the ability to do before we start looking at what we want to do.
Yeah.
If you don't have the game plan of how to get to wherever it is you're trying to go, it doesn't matter how much you know about where you're trying to go, because you still can't get there.
Yeah.
Yeah. And you got to start small. Start off with a beachhead, just one small beachhead, and then you can tangentially move to different markets.
Here's the other issue though with any kind of investing. I've got some people who've already kind of helped me out with the finances and whatnot on some of this stuff, but they all understand that this is not going to make anybody any money. What it's going to do is put a piece of technology in their hands that can allow them to do things no amount of money could allow them to do. See, so and the ability to just spread it
generate
like a virus. If somebody has one of these pieces of technology, chances are you're going to be going home infected with one that you're going to be installing in your home, and now you'll be able to do all that stuff too. So,
yeah, that's almost like crowdfunding, right? I think that's almost like crowdfunding.
Kind of, yeah.
They donate because they want to use it. Yeah,
they want to see it happen. Even if they're not going to use it themselves, they have ideas. They know somebody could use those ideas, even if they, can't get around to it or whatever. Like one of the guys that heavily invested is not with us anymore. He died on April 2nd, and he knew he was close. His brother had died only a few years after he and I met, but he just, even though he didn't have as much to give as other people have, he poured a lot into it. Like, I've got laser engravers and, high voltage equipment, all sorts of stuff like that I just haven't had the room to work on it. So that's why I was concerned about whether the camera was going to work or not, because I'm breaking everything down. I'm getting ready to move. My truck just broke down. I've got sitting at a friend's house that's going to do transmission work. I'm going to have to rebuild the transmission because we can't even find one. So lots of slowdown. So I didn't. There's something to warn everybody here too. That's I've been in communication with. If I'm out of the loop for a week, 2 month, I'm just basically getting resettled. So
well, Thomas, let me go to Charles next. Let me go back to Charles. But thank you again, Charles.
Yep. Back to NDAs. It makes sense for customers and people investing, but you mentioned the first thing you should do is get it verified. Say like a MIT professor that wants to rebuild your invention to prove it works. Should you get the NDA with them?
I think if from a non-investor standpoint, I think there could be an NDA in place in that end, right? Because, there you have another individual with the resources and the time and the relative similar knowledge base to reproduce your idea, especially if they represent an entire university with an endowment fund behind them. That could be something that you could bring up. But I'm not very well versed in that specific aspect, but I can see how you could negotiate that as part of, gaining some kind of near-term traction or working with another external organization that's science-based as well.
Yeah. Okay. Well, so let me go to, and let me see, we've got about 15 minutes left, and I see Mark Sokol with scales, which is awesome. That's awesome.
Yeah,
I can see
this is for later.
Okay.
Rupert,
Good.
yeah, just wanted to add on to NDAs. I had an idea about an NDA. Like if somebody shows up to you with some great idea that he claims will, make whatever happen. If you can put in the terms of the NDA that first the device needs to work for this paperwork to be valid, and second of all, if there's no improvements on the technology in a certain amount of time, our agreement is null and void. Because one thing I'm afraid of with an NDA is they'll just whisper a whole bunch of stuff in my ear, and now I can't talk about it anymore. That can include the sky is blue, or things that I've already known. I mean, most of these ideas have already been talked on APEC, but including that kind of language may protect you or promulgate the technology versus you come to a balance between protecting the IP and forcing the technology to advance as quickly as possible.
Yeah, I get what you're saying. Like it's almost like a forcing function. Like if it actually does work, that's when I won't talk about it. But if it doesn't, then what's the point? Right.
Yeah.
Right. And also, if we're not advancing this within a year from now, if this technology didn't advance, if it just sat here and nothing happened with it, also this paperwork's null and void because now something has to happen here.
Yeah.
It sort of like starts the race.
Yeah. I think
so you can use an NDA as a pushing function instead of a blockage.
Yeah, that's a good point.
Yeah, that is interesting. So let me go to Robert next, and we will come back to Mark in a few minutes. See a dog walking behind me.
Thanks, Tim. Hi, Rupert. Sorry I didn't get all your talk, but what I got is very interesting. Things I didn't learn when I joined Amway. I'm a trained engineer. I tried to start my own business drafting. That's generally what I've been trained for and easiest out of all the disciplines I had in school. But when it comes to finding customers, I've been helped with an organization run by the state, but when it comes to finding customers, you're on your own. They didn't even give any pointers where to go to. It's and I'm not very articulate. I find, I'm sure there's a lot of people, introverts, who aren't well spoken, who have great ideas, but just don't know how to start, or if they're heard, they just don't know how to attract attention. And I learned a lot in the Amway training, I had to say, but life happens. After my parents passed, I lost all interest, especially when my mother died, because she was my only customer.
Okay.
But to find, I've been to networking groups and everything, nothing. I just didn't have the tools to learn how to find customers. I thought I was doing the right things.
Yeah. I would say that. So I guess, so Robert, are you I guess like figure out like what's a good strategy in finding customers, given a current idea? Or
I thought I was doing all the things I could possibly do. ENET, the Entrepreneurs Network. I went to their meetings. I've been to job employment meetings I've already been going to. I knew some people, but it's a type of environment. There was no people that would want to take. I had to find, I didn't have the environment to hook on to the right people who knew people who would have businesses or people who could use my skills as a draftsman. Because I bought a commercial version of SolidWorks and it cost me a pretty penny. I still use it. I'm glad. I don't regret getting it, but having my own business, I was hoping it'll pay for itself. But because it's partly me, I'm fighting my own personality, and that's another sad thing.
Yeah.
I mean, I can train myself to do it over time. I took a public speaking course in college, but still.
So Robert, I think this is the time, like so when you run into this kind of issue, and this happens a lot with like a lot of entrepreneurs, right? Especially like if you're focused on building the tech, this is where you'd have to now find someone with a comparable skill set, right? So if you're an introvert, you absolutely need someone that's an extrovert. If you only want to build, you need someone that only wants to sell. If you only want to sell, you need someone that only wants to build. It's very rare to find someone that's a combination of both. So yeah, I agree 100%, that happens a lot, right? Where, because it's a lonely road to try to start everything on your own. Yep.
It is. And it's like I said, it's a lot of people who don't express themselves, but they really have great ideas who could have gone to the path of being millionaires, if you want to put it that way.
But now there's resources too, where Y Combinator has like startup school where you can network with other potential co-founders, and you can work on test projects to determine whether or not there's a match. So, it's almost like, you don't want to marry the first person you meet. In the same way, you don't want to, take on the first person as a co-founder that you meet via the internet. It's like literally the same thing. So, there's a lot of things you can do.
I didn't know this, and the state, they're just they pretend to help you, but
yeah. So let's move on to Charles Bueller. Robert, thank you again, sir. Charles.
Okay. So I put my camera back on here. Oh gosh, what's going on here? So yeah, Rupert, let me take my glasses off. So I have one final question here. So my team, I want to know if you had any experience with this, but my team wants us to go talk to a billionaire about this technology, which sounds great. Sounds awesome. But I can imagine that it's got a lot of drawbacks as well. So I didn't know if you had any experience with this, or if you had any thoughts on this in particular, this idea.
Like what stage are you in? Are you pre-seed? Have you raised any money yet? Have you built a prototype? Developed customers?
We build hundreds of prototypes, but we've been funding it internally. 200-300K ourselves. We've tried to hold off on VCs and angels as long as possible.
Yeah,
but that's kind of where we're at. So, the next step is to see what my engineers want to do. They just want to quit their job, and they think some billionaire is going to come in and pay them to do this. And that's, I understand that we have an outstanding technology, blah, 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 blah. And that's what everyone here is doing and working on. But the question is, there's not a lot of, technology out there that anyone should ever expect to get fully funded to do research 100% of the time for something, because some of this stuff can take years or decades to develop, except for this technology, everything that everyone is working on in here. That this technology, I've worked on thousands of projects over the years, but this type of technology is deserving of, full-time research funding. Very difficult to get. But I didn't know if you had any experience talking to people like this, of that caliber.
And in finance, during my time in finance, we worked with like a lot of family offices, like really, really rich people. They won't be writing you a check like, you know, from their bank account. They'll have a group of people that manage their investments through what's called a family office. And some of those family offices actually feed into VC funds. But if you're, you know, basically going to just one individual, I would say, I don't know. I mean, you know, I don't know if they're going to fund the entire project to the end. I think what would be really valuable is, you know, defining some milestones for the project, for the development, you know, from prototype to actual manufacturing. And how do you plan to eliminate risk for each of those milestones, and how much money would you need at those specific milestones? If you can get super, super specific on that kind of plan, and also be specific on what your target customer would be, I think you'd be in a good spot to at least, you know, get some, some additional seed funding. I think there is a little bit of danger, right? If you give, you just tell your entire idea and just from end to end, you just let the entire cat out the bag. You talk about your entire product roadmap. I think there is some challenge there. But you know, as far as near-term funding, I think what I've seen like successful businesses do is, you know, you develop a roadmap and then you break down the incremental milestones that you want to hit. So like if you're going to go into this meeting, it would be, you know, hey, you know, this is what we've built so far with this prototype. Our vision, you know, for our customers X, you know, we're hitting a roadblock now where we want to, you know, our plan from the prototype, we want to go into manufacturing, and we need this kind of machinery to help in our manufacturing to eliminate, you know, this risk. And so that's the conversation. That's how you want to target that conversation, as opposed to, you know, this idea is going to require hundreds of millions of dollars. You know, we need, you know, X amount of money, you know, so the more like tactical, you know, you and your team are, and like, you know, if you're leading your team, the more tactical you are with the plan, I think, and the more you can break up that investment, I think that would increase your likelihood of success.
Well, thank you, Ruben. I appreciate it.
How about timeshares? Like, they give off in the real world loans to timeshares. You buy them for a vacation for your family, you know, like 1-2 weeks out of the year, and there's funding, like you take a loan. So they give it a value, numerics value of, you know, time and value. You know, how do you value that in your equation?
Timeshares.
Yeah, because the end in my observable
equity,
in my experience,
yeah.
I experienced that these things, like at the end, they're worth nothing, and you know, like you almost have to pay to get it out of your name, and you know, so you don't incur on it registration, you know, fees and things like that. But you know, at the end of the time, something got built, and you know, it exists, and you know, there is a modernization of that, you know, space that, yeah, one person at the end will still, you know, according to your scale, which you showed us on, you know, your process, at the end, like, you know, one person still owns the actual material thing, and everybody else dissipates or gets so reduced to the point where, you know, they just don't want it, you know?
Yeah, so I guess, so Lulu, I guess the question is, you're saying what strategies can you use to minimize the amount of dilution in the company when you get funding?
Well, I'm saying, like, these already exist and they're incorporated into our financial structures and profit, you know, for creating something or an idea. And this creates, you know, structures, not hypotheticals, like, you know, time where people actually can, you know, use as investment, like, you know, paid, you know, you already like prepaid that material into existence for, like, you know, the amount of weeks for your family a year, or, you know, I had one of those, so I know, I've used it, so I know exactly the structure. You take out a loan, you pay taxes, and, you know, they give you the interest, and you deduct it, and so forth, you know. But it comes to a point after you pay it, you know, like they do not, for example, deduce the tax ratio, because now you're not, you know, the mathematics stays the same, but like the value gets less and less and less because there's no, application of the revenue that they're collecting as tax and maintenance into upgrading it. Get it?
Yeah, yeah.
So
Yeah,
they
so
play
there's
with
a
all
risk there. Yeah, there's definitely a risk, right? There are a lot of companies, right, that so there's one company that recently went bust, a company called Fast, right? And their idea was
I'm talking about like current stock market companies such as, resort hotels, such as the Hyatt, Hyatt, such as the Marriott, such as the, they do sell you those timeshares. I've got like the booklets that could show you, but applicability of, transference of points and this and that, they always manipulate it down to a core. I have paperwork to prove it, to play with this. At the end, it's just, it was wasting, my energy. They say time equals money. Well, guess what? I was exhausting my, time and energy on, a system that's incorrect.
Yeah.
Yeah. So
yeah,
I let it go. Simple as that.
Okay. Well, Lulu, thank you. Let me move along. And let me see. We have Michael and Harold, and we've got about 3 minutes left until Mark comes on. So let me go to Michael really quick, and then I'll jump to Harold really quick after that.
Okay, just a couple things. NDAs only have meaning if you're willing to sue. So if you're asking for money, obviously you don't have enough money to sue.
Michael, actually, if I could jump in real quick. Yeah, I would say, and this is from my corporate career, right? But in an entrepreneurial perspective, any contract is limited by enforceability. And so, I mean, it's NDAs, it's money splits, it's anything. It's anything you do is limited by enforceability. And one of the things that I found in certain industries is, that's one of the things that companies will look at is like, okay, how enforceable is this? Yeah, we'll make a deal with you. Are you willing to enforce that? And there are a lot of
enforcing isn't cheap.
It isn't. It isn't. And that was what I meant, where a lot of those things you're talking, you may $50,000 to $100,000 in lawyer fees. And and then it's like, okay, are you going to make your money back on enforcement, or are you just going to let it go? So
yeah, and the other thing that it costs you, right, is your attention, right? So like if you are, you're starting something completely new, you are in a race, right? You are running. You may have a very, very small head start, so the time that it would take for you the time and the money that it would take for you to actually enforce this NDA that you put into place, it may not be beneficial to you, or it may be, but it depends on your situation. So yeah, you're spending time that you're taking away from building your product, and you're also spending money that you take to actually grow your product to enforce an NDA for a previous iteration of the product.
Yeah. Now the other issue, other thing observation I have, you brought up about, you might not be good at sales, and the company that comes to mind is Apple, and Steve Jobs and Steve Wozniak, where Steve Wozniak was the creator, the maker. Steve Jobs was a salesman.
Yeah, absolutely. So that's the power of having like a really, really rock solid team, right? Of having those opposite skill sets, that yin and yang. It's really super hard to do that. It's hard to find a co-founder that can understand understand, not only conceptually understand the idea, but like be comparable in skill set that you can work with, right, over the course of the long term, right? Because it's kind of like a marriage. But yeah, but it's easier now than it was in the past, right? There are a number of like online communities, there are forums, there are, we can utilize technology now to have a wider reach for people, not only just within the same country, but around the world. And we see a lot of like startup teams, they're actually doing that now. There are a lot of companies that are completely decentralized, right? Like Coinbase is one company where the company is like decentralized all around the world. and a number of startups as well. So you can utilize technology to find that talent, but it's still challenging. But when you do find someone, the best thing for you to do is to do something called like a time box project. Meaning, it's a project that you'd work on for the first 1 to 3 months. You have a goal, and that'll do two things. It's almost like an interview, and secondly, it'll teach you a little bit more about this person. How does that person handle stress? What their motivations are. Are we a really good fit? Because just because they have competing an opposite skill set as you doesn't mean that you guys can actually work together, because your personality may not, you may butt heads.
Yeah, so it's like marriage, like you said.
Yeah.
So thank you. I wanted to make sure I said thank you. Your presentation is very helpful, and I appreciate it. I'm sure a lot of us other participants in this conference appreciate it too. So thanks again.
Absolutely. Yep.
Awesome. Well, thank you. So we're about 2 minutes over. Harold, do you think you could make it super quick, and then we'll go to Mark?
Yes.
And my apologies for the time crunch.
I second that what Michael Boy said. Great idea. But my question is this. Most venture capital, they refuse to sign an NDA. Many experts that have the skill to value an idea, they don't want to sign NDA. Many books, they say, if you're going to have a great idea, start up, get an NDA. Why is it when everybody's against NDA, yet it is a recommendation that investors want to see that if you disclose the idea to an expert, they want to see an NDA, yet they don't sign, the investor don't want to sign NDA. Why is that advice so common?
Yeah, I mean, I guess it depends on the book that where you're using what you're using as a reference. Like I've read a lot of info when it comes to trying to fund really big ideas. Generally speaking, from what I've read, the NDAs are not really a good idea when you're reaching out to a VC. But as I mentioned with Charles, if you have a situation where you are trying to get some third-party validation for your idea, where you're trying to work with an institution, work with a college, work with another entity that is not going to be providing an investment, but is going to be providing more so a independent verification. I think that's where an NDA would be useful. When you're trying to move into actually getting an investment now, most VCs, they're just, again, we want to make it as easy as possible, and most VCs won't want to sign an NDA just because it's just a hassle and they just don't want to be bothered with it.
Well, yeah. Many experts don't want to sign an NDA, but thank you for the advice. Great presentation.
And Harold, thank you, sir. Thank you very much. Phil, let me put your hand down. We're just about out of time. So I want to put this thing back on gallery view. Mr. Rupert Wade, sir, thank you so much. Thank you so much. The business aspect of this has been so neglected. I cannot thank you enough for helping us understand that. And I mean, if that's something that you'd like to come back and talk about in the future, and of course, as you work with HFGWs, I'd love to have you talk about those as well, because that is another topic that has been sorely neglected in our conference. So
yeah, absolutely. I'd love to come back. Yeah, give me a time and a place, and we can do this again. And if you guys have any other questions, just shoot me an email, and I'll try to get back to you. Definitely.
Perfect. Thank you again, sir. Okay, so let me do this. I'm gonna mute everybody out, and now I'm gonna go to Mark Sokol, who is gonna do lab updates. If there he is, Mark. She's all yours, sir.
One second. It sounds like we're having a little reverb. Oh, it's in that. Okay, that should be a little bit better. So basically, we have continued work on this gyroscope contraption over here. Was inspired by Mike Gamble and his work with gyroscopes at Boeing. Tom Butler over here has assisted with both the build design and the software. So we've come to a point where it's pretty much complete. The software can be tweaked a little bit more, but we set it up on a bed of ping pong balls, so it's pretty resistance free, and the force measurements you're seeing are over there, actually two axes. The red being lateral left and right. So we don't expect much movement on the left and right, but up and down, which is the blue measurement, should be showing some either positive or negative force. That's where I'm pushing it. Basically, these force sensors are on one side, and on the other side, there's a constant spring action. So although the object's not going to be moving, we are going to see slight, changes in weight that are commensurate with the amount of thrust being produced. We did run this on a test stand earlier in the week. I posted a video on YouTube. It was moving around, following the direction that, as expected. Other people did note that, the surface needs to be perfectly level, which is why we're actually working right now on getting a section of the lab perfectly flat level, so we'll be able to see whether, for future tests, we'll just be able to set it down on this section that we know is perfectly level and, use the same ping pong test to try it out. So without further ado, we're going to power it up. With these two switches. Should we have to hold this down? I think it'll be fine. So programmed in a small period of no movement. I'm just going to help it start up. This was to give the motor some time to there they're going. So the motors right now are spinning up. We're going to use the sleeve of your jacket. Yeah. Start collecting the data. It's not. Please don't pick it all. So there you have it. There's the data is right over here on the top left. We are seeing larger spikes on the blue. The blue, of course, is the I believe, yeah, the blue is the lateral force. So it'll be up and down. So that's the direction we are expecting force. And we see there is more. It's all shifting towards the negative side, and this was zeroed out before the test. So I do think there was some results over here. As expected, it is sort of a pulsing effect. Let me see if I can zoom in on this.
Well, so Mark, my question is, are you going to put me under NDA for this? Yeah, sorry. It looked like the ping pong balls might have been getting held up in the grooves on that box.
My dog hated it.
The box is it's made out of this really smooth material on the floor, on the base of it. I don't think they're held up. They're not touching each other. They're like placed in there sparingly. I'm not too worried about the friction on the base. And we can see from the data, I would just ignore the red because we're not really expecting any effect on the red side. It's really the blue that we're looking at in terms of force meter number 2, it is, I think. Yeah, force meter number 2. That's the one that matters over here. And you can see the reverse spikes are much less than these long pulse, pulses of inertial movement that are going up to like 6 newtons of force. It will be very interesting to see how this works out once we get our level floor set. We have a team over here still working on that. So it might be sometime tomorrow when we get that done. But the results so far are looking pretty promising. The goal is to get a device like this fine-tuned using a setup like the rig we have over here. We're going to be playing around with this, with various settings in the software, different pulse lengths for the forward and return. This is sort of like swimming gyroscopes through space. And we'll compare notes with different setups. The goal is to get it to go up a couple degree incline, and if we can do that, and present that in Albuquerque at Tesla Tech, that would be quite an achievement. That would be pretty cool. But so far things are looking pretty positive for this experiment. We shifted away a little bit from the Alzaphon experiments right now because this was so close to being done. So I just jumped in, gave Tom a hand, and we popped it out in the last couple of weeks. The Alzaphon experiment still set up right now. I see David Alzaphon is here in the crowd. He came to see what was going on over here. So we do have your experiment still set up. We saw some pretty weak results, nothing close to 80% weight loss. Strongest results were with very thin film materials. And I intend on diving down that path a little bit more. I think George Hathaway mentioned as well that the skin depth of X-band radiation is very shallow in any material like aluminum. So you really need very thin layers in order to see any effect. So we're looking into a vapor deposition system that will allow us to try very thin layers of various materials. You can layer on top of each other or capacitor formations. And with that, we'll just put that in the EPR machine or in the dynamic nuclear orientation rig and see what happens with that. David's asking if we're able to get into the 3.3 gigahertz range. Yes, we are. We have 200 watt amplifiers that go all the way from 400 megahertz to 12,000 megahertz, 12 gigahertz. We have, so 3.3, I think that's the S bands. George Hathaway was thinking of doing it in the S band as well. Very large waveguides if you want to do a waveguide version of that. Which direction was the rotor spinning? I think Harold put that in the chat. For the gyroscopes, they're spinning in opposite directions. So their outsides are spinning downward like that. But if you were to twist these forward, they would both be moving like the tires of a car to move forward. So that is all, folks, for now. Hope to have a bigger update for you guys in 2 weeks.
Mark, I have a question real quick. Is that a two-phase type of instrumentation?
What are you asking about?
Like, is it two sine waves going in on each other? Like, since you got two different directions going.
Are you talking about the chart that I have above me?
Yeah. Yeah.
Oh, those are not waves. Those are well, they kind of are waves. Those are movements in this entire rig. Like if I move it, like this, if I move this around, you see that these are force sensors over here, 2 force sensors giving me the X and the Y of its movement.
Okay, I see. Okay.
So really, we're just concerned with the Y. I just wanted to see if there was anything happening on the X. Nothing's really happened. Oh, actually, no, this is the Y. This would be the X. So we're really only concerned with the X movement, the left and right in this configuration, because it's expected to move in this direction. This direction was here just because you need something that, to stabilize it, and we had an extra force sensor.
Yeah. And so, like, what's the limit, though, how far it can go before it starts clipping, I guess, as far as, like, distortion-wise?
they're able to go up to 10 newtons of force, which is about a newton of force is 100 grams. That would be yeah, like a couple pounds of thrust before it would start going over the edge. There's a switch that allows you to go to 50 newtons. So this is on the sensitive setting.
Yeah.
Right?
Yeah, but that's good that just fine tune it more slowly and get it up there.
Right. Well, what we're actually fine tuning is there's a chip board over here that it's sort of like a robotic chip for robots with PWM.
Yeah.
And Tom over here has been programming it, working with the people at Palolo, right? Mm-hmm. Yeah. So it's really just changing the settings on that. That's what we mean by programming, and then we'll power it up on this apparatus and see whether it created more thrust or less thrust, and what we're looking at.
All right.
Mark.
Hey, Mark. Mark.
Yeah, go ahead.
Hi.
Both of them.
If I understand your graph, the blue lines above the zero axis is going away from the camera, and below is going toward the camera.
The blue line is
Mark, if I could jump in. So I think this was some of the confusion. So you've got the blue and red. One of those is sideways, right? One of those is like your y-axis, and then one of those is front to back. That's the x-axis, and that's where you're expecting to see the motion. So one of them's lateral, it's side to side, and maybe something happens, right? Because it's shaking. And then the other one is forward to back.
Exactly. And I'm gonna see if I can zoom in over here onto the.
Okay, so you're just trying to make it less sporadic. So
the red represents side to side, then.
Yeah, I see. That's cool.
Mark.
I'm understanding this. Like, this is pretty cool. So this is fine tuning. You're just trying to get a bit smoother curve. So.
Yep, pretty much.
I'm gonna do the same attempt with a cell phone. I'm gonna try. I want to start at 1 hertz.
What are you working on?
Like the same thing, kind of like similar to what you're doing, like with just fine, tuning the curves and stuff. But I want to use like the cell phone at a very low vibration, like 1 hertz, and then I'm gonna try to see if I can have some measurement scheme of detecting any like a wattage meter or some similar deal, and just try to use less wattage possible to get to a higher frequency. So, but I'm gonna try to start off at a very, very low type thing. But like all I'm doing right now is extra reading on it. So, I'm kind of new to this, but it seems pretty simple a little bit. It doesn't seem too hard. It's like X and Y axis, right? On a circle line, you got your degrees that it's rotating, and those angles are the fine tune, and you just gotta match all the phases right, different time variations, and so this is very fascinating. So, and this is why I didn't really care for cash. So I hope you understand what I'm getting. I'm pretty sure.
No, I really don't.
Oh, well, you got like. Go ahead, Sarah. I was just.
Go ahead. You say you're not concerned about the red. That has no bearing on your goal for this experiment.
Yeah, the red measurement is, in this case, it would be the y-axis. We're only expecting movement on the x. So if I found a way to remove it from the chart, probably should try doing that.
So you just allow just a free move on all axes parallel to the floor or the surface of the table.
Yeah.
I think it's interesting. You have significant lines in the red, even more than the blue.
That was just from us. Yeah, I think I was adjusting it manually.
You were adjusting. Okay. All right. Thanks.
Yeah. Mark, Harold, I have a question. If both of the arms were pointing forward in the same direction, and looking from your side, they say they were both spinning, in the same direction, let's say counterclockwise, how much force do you expect to be producing? You know, they were just pointing forward, stationary, just only the wheel spinning. How much gyroscopic force do you expect that will be producing, let's say, toward the X direction?
I don't really know. This was based off of Mike Gamble's concepts that he talked about several times at APEC. So he said that it works best with up to 15 degrees of movement, and that at a certain point there's a lower return on investment. Like you don't really get much more effect by going any farther than that. So that's really what we're sticking with. This is basically at its core what it's supposed to be is a angular momentum device that converts angular momentum into linear motion. So it's supposed to go against the conservation of angular momentum and find a way to achieve that through complex pulse spins.
Yeah, that's what I'm doing with trying to do with the cell phone is, you know, fine tune the angular momentum where it doesn't, you know, clip in the signal. You know, if you're doing like Fourier analysis, like on an oscilloscope, so like, you know, you're trying to use less energy or wattage. That I was just trying to tell you what I was trying to get across, like, say, you know.
Yeah. Well, guys, so let's go to open discussion. You want to do that?
Sure. This is the relevant data, by the way, from the x-axis, and you can see right over here between the two ones. That's the 0 point. So there is more thrust in one direction than the other, but there is a little bit of a return pulse. I also posted a video on YouTube showing this device scooting across the table on a similar platform of ping pong balls, and it was just able to swim around. It was pretty cool. It's a little scary when it's up and running because these rotors over here have a lot of angular momentum to them. If they come in contact with flesh and bone, they can be pretty nasty. And we've had one gouge out a wooden table before when it fell over. So we try to have something handy to remove that energy from it. So we're in open discussion. Anyone can
So Mark, it looks like you have more spikes in the opposite direction, but larger spikes in the direction toward the camera. Is that correct?
Yeah. So I just changed, guys, if I could jump in real quick. I just set it, I removed the spotlight from you, Mark. So, I mean, you keep talking about this. It's totally cool. But so now it'll show Robert who's asking questions and all that stuff.
Right.
Oh, okay. So you're gonna, yeah, Robert, you're gonna have to look at the screen again. Yeah, there is, in terms of number of spikes, I'm not sure that there's more of them in the opposite direction, but there's definitely bigger magnitude and bigger overall energy, force in the negative side of the scale, which seems where we're seeing that forward momentum.
It'd be interesting doing a general energy analysis to see if there's more energy going toward one way than the other.
I've always noticed that though in a lot of vibration analysis systems using they would test on just different objects that for some reason that this graph line would always go to the right when it gets up there near like past the megahertz range a bit. For some reason it always veers off to the right, you know. I don't know if that's any relevant what I'm trying to I mean, like I said, I'm new to this. I don't know all of this all the way.
This is gyroscope propellant, propulsion, you're probably talking about some RF stuff.
Yeah, but it's the same thing. It's mechanical resonance. It's all the same, thing. I mean, it's just the model of physics I follow is just mechanical resonance, and it's just that electricity, infrared, UV light, gamma rays, and the whole EM spectrum is just all the same thing. It's just the more pulse rates you go, the more that the energy transforms into whatever phases. So, hold on.
Hey David, how are you?
Oh, sorry, I had to do something, but go ahead.
Oh, me?
Yes,
fine.
David, how's it going?
Oh, it's going great. I know I've been absent from the discussions for a long time, but I'm glad to hear things are moving forward on recreating the 1994 experiments.
Yeah, we've you probably have to watch a couple of the past updates that I've done on it. I promised you that we'll run the experiment and we'll stick enough energy into that waveguide that if we don't see weight loss, we'll burn it, and we did. Yeah, we had a sample go up in flames, and then we added temperature sensors to the box, and I mean it's a much more sophisticated setup right now with a lot of different variations to the setup that we've added, and we've seen our best results have been with really thin film aluminum.
Thin film aluminum meaning what? A sample that weighs very little is?
Yeah, it weighs very little. Like the Mylar aluminum emergency blankets that the Red Cross uses. It's very thin aluminum layers, and RF is able to penetrate that.
Do you know that as long as you're able to induce dynamic nuclear orientation in that thin layer, whatever is in contact with it should experience a transference of dynamic nuclear orientation from that layer?
Right. So what I did was I put a little pebble of osmium, which is the densest metal in existence, and surrounded it with that aluminum foil stuff. And we saw some weight loss, and it was precisely at the 28.025 gigahertz per Tesla. Right when we reached that sweet spot, we saw some movement and a little bit of weight loss. You got to replicate that experiment again. We were using an analog scale at the time, and the problem with the analog scale is that when you see the weight loss, it's moving, and if the sample's moving, it's losing its sweet spot already. It's losing that little spot at the center of the magnet. So we're going to replicate that experiment with a digital scale, so you don't have that much of a movement issue.
What was the pulse width in that experiment?
I shifted it around, but it was somewhere around like between 2 and 10 milliseconds.
Yeah, okay. In the 1994 experiment, you had a completely different frequency, and you had a longer pulse width. And I was wondering if your pulse width would shrink as you went to a lower frequency. But you have the ability to push it around and see where it seems to work.
That's what we're going to do.
Of course. Well, so you have the Tesla conference coming up, and then afterwards, perhaps you'll be going back to the Alzafon effect, as you call it.
Well, we're going to work on it again in a little bit. Right now, it's April 23rd. The Tesla conference is at the end of August, so we got a couple months until then. It's in Albuquerque, New Mexico. If you'd like to join us, that's Tesla Tech in Albuquerque, New Mexico. It's hosted by Steve, I forgot his last name. Really nice guy. We've been there last year. Tim Ventura is probably going to be joining us. I'm going to be presenting there as well on the latest research, and From all the conferences I've been to, I really like this one. I think it would be a good choice for you, David, if you wanted to come down and meet some cool people. And it's not just going to be Alzafon. There's a couple other experiments going on there, and they have a water powered car. Free energy devices, great food, great company. It's really nice, and it's not too expensive either.
Sounds great. We'll see. I don't. It's all new.
Hey, Mark, do you have a link for the conference?
Yes, Tesla Tech. Tesla Tech. Let me just do a Google search.
Tesla Tech is usually August. It's usually the end of August, beginning of July. Or sorry, end of July, beginning of August.
I thought it was more like the end of August or middle August.
He might have changed it.
Yeah.
But like I said, Mark, I think your experiment is probably near the best approach to get to like anti-gravitic effects. What I'm trying to do is like you have your dot on a circle and it's going around, you have that like one rotation depending on the degrees, right? And the more like the different angles you have, like say you picture you have your sine wave going up and down, and then it kind of like it goes up like a curve. You would measure a curve, going up, and it would, the sine waves would go up that curve, and depending on the angles, that you would have a straight line drawn through those sine waves, like that would actually determine the phase alignment, and that would, make it more energy efficient. That would allow you to like line up all the amplitudes, correctly. Like that measurement would determine, the phase alignment better. Depending on like the angle, the angles that the point is at. Like say you would have your 2 points. You would have one point that's going around, and that's your pulse rate, right? The dot on the circle. Mathematic wise, and the faster it goes, the more more frequency you have. Just using one sine wave as an example, and then you have another point on the circle, and that point doesn't move. That point will help you draw a straight line through the through the sine wave curve, and like you're trying to see like angle measure out where all the theoretically where all the wave crests, the dang it, what do they call it? Crest and troughs meet, exactly in phase. So that would make your less energy requirement needed. You wouldn't have to jam, like 1,000 watts until you just get a high frequency. If you catch what I'm trying to say.
No, I don't catch what you're trying to say in relation to this mechanical device, which can only be discussed in terms of RPM and angles of movement.
That is. But that what I just said is angles of movement. It's RPM, and it's just like you're setting.
The frequencies that this is moving back and forth are very low there.
But it's the same concept. It's really the same thing. Like you said, angular momentum. Angles on a circle. It's the dot is spinning around, so that's literally the same concept. I'm just saying what you're doing is like what I'm trying to do, but I'm using like a math scheme. This isn't, alternating current measurements in like, regular circuit boards and stuff. Same thing, a lingo the electricians use. So, like using that circle measurement phase thing would determine better energy efficiency. So, you would require less power to get to a higher frequency. So I don't know if that helped. The study of angles, on measurement line. For phase alignment, so you should really check it out. That's just the research I've been digging up. So,
so Mark, you talk about.
Go ahead, Robert.
You talk about Steve Ellswick.
Yeah, that's Steve Ellswick at Tesla Tech. So
I spoke with him several times. I feel sorry for him. He lost his business partner several months ago. Last year.
Great,
so he's doing it on his own.
He's doing it mid-August, so it's August 10th till the 14th. So if you can make it there,
I don't think I'll make it.
Register before May 31st and you'll get 25% off.
Yes, I know that. Yeah, I know, but still, I may not be able to make it. I got so many other things going. Life happens, but I'm hoping to visit your lab fairly soon.
Love that. I gotta run, guys.
Well, it was nice talking to you, Mark, man.
Take care, Jeremy.
Help out. Yeah.
Yeah, I think we're actually kind of winding down for this evening. Yeah, so you know what? Why don't I stop recording now? I'll do that, and I mean, so let me do that. I will stop recording for this evening.
Recording stopped.
Okay, there we go. There we go. So yeah, I mean, it's pretty mellow. I mean, I don't know. If
well, Tim, since it's just